So, good evening to Ananda. Good evening. So, we'll wait for a while, 1 or 2 minutes, and then we will start the next problem. Actually, next problem. In the previous class, we have started with the LG fault, right? Earlier classes, we discussed about three-phase fault, little bit on alternator, as well as RL circuit of a transmission line, right? So, after that, we have done some problems on the three-phase fault, and we have seen how to do fault analysis on a loaded system. Loaded system. Yeah. And after that, we started with the LG fault, particularly unbalanced fault, what we said, and we have seen the procedure, how to do that unbalanced fault analysis. Okay, so and we are solving some problems on that unbalanced fault, so-called LG. So, and the same way, we are going to take up one more problem here, one more problem in the LG fault analysis. Yeah. Yeah. So let's start with the next problem. Next problem in this single line to ground fault analysis. Yeah, just you put a message to me, Supraja, to this number. Just put a message to me to this number, to my mobile number in Telegram. I'll do that, what you have asked. Yeah. So I'm taking up this problem. This PDF file is with you. I'm going with the question number 10 here. Question number 10. So in the PDF file, go through this. Yeah. See that? See this question? See an isolated neutral Y connected. Isolated neutral Y connected three-phase synchronous generator rated for 11 kV, 100 MVA. Has the sequence reactances X1 equals to X2 equals to 3X0, 10 ohms. The alternator is operating at no load condition with rated voltage. For single line to ground fault on the phase A, means you have a phase A to ground fault on the conductor, and find healthy phases voltages in the absolute form. Means if the phase A is getting fault, remaining phases will be healthy. Non-faulted phases, or you can say healthy phases here. Those are nothing but obviously phase B and the phase C. So we have to find phase B to ground voltage, phase C to ground voltage for this particular fault. Okay, let's look at the data what they have provided first of all. See, the first statement itself, you should be very, very careful. It is an isolated neutral bi-connected three-phase synchronous generator. So we have a three-phase synchronous generator. What do you mean by that isolated neutral? What do you mean by isolated neutral? Zn is equals to infinite. Neutral is not connected to ground. That's the meaning. Zn will be equals to infinite. Okay. So this is connected. This ratings are 11 kV, 100 MVA, as we are saying. 11 kV line to line voltage, 100 MVA three phase, 100 MVA three phase. Okay. Reactances of this generator, X1 equals to X2 equals to 3X0, that is equals to 10 ohms. The meaning of this will be X1 equals to 10 ohm, X2 equals to 10 ohm, 3X0 equals to 10 ohm. In that way, we have to write X1 10 ohms, X2 10 ohms, 3X0 value again 10 ohms. The meaning of that will be X0 value will be equals to 10 by 3 ohms. This is the way how we have to write the reactances given in this manner. Okay. Alternator is operating at no load condition with rated voltage. Rated voltage means obviously terminal voltage will be 11 kV line to line. If you want to take in per phase manner, it's 11 by √3. Okay. For a single line to ground fault on phase A, find healthy phases voltages. See, to calculate these healthy phases voltages, first we should find out symmetrical components of phase A, phase B. Symmetrical components of phase A means VA1, VA2, VA0. These three voltages we have to calculate first. Later on, we should move to phase B and the phase C. Okay, yeah. So let's move with the next slide. So as it is a single line to ground fault on phase A, the sequence networks connection will be sequence networks connection. I am directly moving to the sequence networks connection. As it is a LG fault, positive sequence network, negative sequence network, zero sequence network connected in series. Across that, we have to keep a short circuit because he didn't mention any fault impedance in the problem. So I can say this is a positive sequence network up to neutral, and this is a pre-fault voltage, EA1 you can call, which is nothing but terminal voltage before occurrence of fault. Terminal voltage before occurrence of fault, because he didn't set any load on the system before the fault occurrence. Okay, so this is JX1. I'm calling only reactance is given in the data, so resistance is neglected. So this terminal voltage VA1 and this current will be IA1, positive sequence. Negative sequence network also we have to draw up to neutral. It is neutral, and this impedance will be JX2. Terminal voltage will be VA2, and this current is IA2. Zero sequence network. Up to neutral, we should keep JX0. And then neutral to ground. How much is the Zn value given in the data? Infinite. Zn value is equals to infinite means we should keep 3 times of Zn here. So how much is that value 3 times of Zn? That will be equals to infinite. That will be equals to infinite. So these are the, so this will be the terminal zero sequence voltage VA0 and current flow is IA0 in this one. Okay. Now we have to make all these three in series. We should connect. All these three in series like this. And then at the end, we are going to keep one short simply because it was a solid fault. We are saying this is a solid fault. We should keep this one short in this manner. All of you getting this? Okay. Yeah. So how much is the current flow in this circuit? Anybody please tell me. What is the positive sequence current value and negative sequence current value and zero sequence current value? How much is that number? 0, because we have an open circuit here. open circuit here, we don't have any current circulation in the loop. But if you have any doubt, just to write this is EA1 voltage by JX1 plus JX2 plus JX0 plus infinite. So EA1 by infinite, that number will be 0 obviously. Okay, now what is this VA1 value? VA1 value. See, his interest is not to ask how much is ground current or how much is a fault current or anything. Just what he's asking is simply what are the healthy phases voltages in the system. That's it. Okay, so what is VA1 value from this KVL application? VA1 value is nothing but EA1 minus IA1 into Z1. EA1 minus IA1 into Z1. Z1 means JX1 here. You write in place of Z1, you can keep this as JX1. So IA1 value we keep 0. So it will be simply EA1 itself. That value will be simply EA1 itself. What is EA1 value? Pre-fault per phase voltage. EA1 is nothing but pre-fault per phase voltage. VPF per phase. How much is that value? Anybody? 11 kV by root 3. Because he said that the alternator is operating under rated condition. Rated condition means obviously 11 kV is a line-to-line rated voltage of the alternator. Per phase voltage in the sense we should call that as 11 kV by root 3. 11 by root 3 kilovolts, and you assume this voltage as a reference. You assume this voltage as a reference means you can call 11 by root 3 at an angle of 0 degree in terms of kilovolts. In bracket you write chosen as reference. Chosen as reference. I think all of you comfortable with this. Okay. So this VA1 value will become obviously 11 by root 3 kilovolts at an angle of 0 degree. 11 by root 3 kilovolts at an angle of 0 degree. What is VA2 value? VA2 minus IA2 into JX2. As already we are saying IA2 is equals to 0. So definitely we get this VA2 value as 0. So negative sequence post-fault voltage. Negative sequence post-fault voltage will be automatically 0. Okay. So I'll write to the next slide. Next slide. VA2, if you write, so it will come to be minus IA2 into JX2. So it is 0 into JX2 means J10. So it will be 0 into a finite number. 0 into a finite number. It will be obviously 0 in terms of kilovolts or volts. What is VA0? Anybody? Can you tell me what is this zero sequence voltage VA0? Minus IA0 into JX0 plus infinite. So zero sequence voltage is minus IA0 into JX0 plus 3ZN means infinite. Already we know zero sequence current value was 0. So this is 0 into this whole number is infinite only. What do you mean by this 0 into infinite here? What do you mean by this 0 into infinite? It's undefined. 0 into infinite is undefined. It is undefined. See, what you have to understand from this undefined term is are indeterminate. Indeterminate or undefined. The meaning of this is we can't say the value of zero sequence voltage by using this equation. We can't say the zero sequence voltage by using this equation. But you see from the network. You see from the network. As we have applied a short circuit here, we know VA1 plus VA2 plus VA0 value equals to 0. From that, it is possible to get the value of VA0. Okay. So as we are unable to get it from equation, I am looking into the circuit now. Looking into the circuit. So as we know from circuit analysis, VA1 plus VA2 plus VA0 value is equals to 0. VA1 value we know some number. VA2 value 0 and VA0 we don't know actually. So that zero sequence voltage will come to be minus VA1. Zero sequence voltage will come to be minus VA1. Else you write this is minus of 11 by root 3 at an angle 0 degree in kilovolts. Like this you can say. This number will be minus of 11 by root 3 at an angle 0 degree in terms of kilovolts. I think all of you getting this one. All of you getting this one. It's not Shushma. It's not 0 into anything. We can't say it is 0. 0 into infinite is indeterminate. 0 into any other number, non-infinite value, that will be equals to 0. Yeah. Okay. Next, if we know all the three sequence voltages, VA0, VA1, VA2. Now we have to find the values of VB and VC. We know already the equations of VB and VC in terms of symmetrical components that we apply here. Okay. Yeah. So let's say first phase B voltage, post fault voltage, phase B voltage in bracket post fault condition. That's the meaning. Post fault condition. VB. What's the formula for this? VA0 plus alpha square VA1 plus alpha VA2. Okay, VA0 value we keep minus VA1. We'll substitute the numbers later. First you do this one. Minus VA1 you keep here for VA0 plus alpha square into VA1. Okay, VA2 value 0. VA2 value it is 0. So in the next slide, you take VA1 common, you will get alpha square minus 1. Okay. Yeah, you please complete this one quickly. Please complete this one quickly. Yeah. So can I move to the next slide? I think so. So now you can write the phase B voltage as VA1 common, and you will get this as alpha square minus 1 number. What is this alpha square minus 1 number? We should do it from phasor diagram analysis or your rectangular method of calculation. I can say alpha square. Okay, alpha square, and we have to take minus 1, and it will be VA1 into, I think it is root 3 at an angle minus 150 degree. You please cross check that. You please cross check that. Root 3 at an angle minus 150 degree. Minus 150 degree. You please cross check that once again. So what is the value of VA1? Already existing root 3 at an angle, so 11 by root 3 at an angle 0 degree. That is in kilovolts directly. It's not in per unit, directly in terms of kilovolts. No issue of base or anything here. Root 3 will be cancelled out, and it will be simply 11 at an angle minus 150 degree in terms of kV. 11 at an angle minus 150 degree in terms of kilovolts. Clear? That's the value of phase B voltage. And again, phase C voltage in the post fault condition. Post fault phase C voltage. Phase C voltage. So you can take up this equation for VC. VA0 plus alpha into VA1 plus alpha square into VA2. Okay, so you please calculate this number also. Calculate this number also quickly. So you can get VC is equals to VA0 is minus VA1 value plus alpha into VA1, and VA2 number is 0 you can keep. So you take VA1 common, and you will get this as alpha minus 1. And you have to take alpha minus 1. First you substitute VA1 value, else VA1 into first alpha minus 1, it will be root 3 at an angle of plus 150 degrees. Okay, VA1 number is 11 by root 3 kilovolts at an angle 0 into root 3 at an angle plus 150 degree. So root 3 will be cancelled out, and it will end up with 11 kilovolts at an angle 0 degrees. 11 kilovolts at an angle 150 degrees. 11 kilovolts at an angle 150 degrees. So this type of questions is possible to ask in the exam. This type of questions are possible to ask in the exam, but without doing these many calculations also, we can say that, because it is one of the conclusion actually. Whatever I'm discussing, it's a type of conclusion. How it is so means we will be saying further also, right? See, first of all, in this particular case, what is fault current value? How much is the value of fault current? 0, right? We don't have any fault current. Even you have a phase A to ground fault, fault current will be 0. But there exists some voltages for the phase B and the phase C terminals, outcoming terminals. Okay. So I will move to the next slide. To discuss about this thing. even a bit elaborately in a simple way. So I'm taking up the next slide. For example, we have an isolated neutral alternator here. Isolated neutral alternator. Isolated neutral alternator. Kindly observe. So I am showing the three-phase diagram of alternator now. Three-phase diagram of alternator. So this is a phase A, and it is phase B, and it was a phase C of alternator like this. And neutral is not connected to ground, as we are saying. Yeah. So like this, we have three outgoing terminals, ABC. Three outgoing terminals. I am showing ABC. Next thing. These are the internal voltages here. Internal EMFs. Internal voltages. Let me write these numbers to you. Internal phase A voltage, phase B voltage, phase C voltage. I am writing EA. EA. So it's a 11 kV by root 3 at an angle 0 degree. 11 kV by root 3 at an angle 0 degrees. Okay. So EB is 11 kV by root 3 at an angle of minus 120 degree in kilovolts. Internal voltages are balanced. Internal EMFs are balanced. Phase C voltage is 11 by root 3 at an angle of 120 degrees. 11 by root 3 at an angle of 120 degrees. These are the phase A, phase B, phase C voltages. Next one. Next one. So it's operating at no load condition, means phase A current is 0, phase B current is 0, phase C current is also 0. And what will be the terminal voltage of phase A, phase B, and phase? Anybody please tell me? No fault. No fault. No fault on the system, and it was a healthy system, which we feel healthy system. We are going to call this one. Can anybody tell me what will be the phase A, phase B, phase C outgoing terminals voltages? Outgoing terminal will be equals to internal voltages, right? Will be equals to internal voltages, obviously. Means I can say VA is nothing but 11 kV by root 3 at an angle 0 degree in kilovolts in the healthy condition. Phase B terminal voltage is 11 by root 3 at an angle minus 120 degree in kilovolts. I'm saying you again and again, we have not considered the fault here. No fault on the system. Again, you say that, sir, earlier case you said VB 11 kV, but you are writing here 11 by root 3. I'm saying you again, it's a no fault condition. Phase C voltage, it will be 11 by root 3 at an angle of plus 120 degree in terms of kilovolts. Like this will have VA, VB, VC. Immediately in the next slide, same diagram I will copy. I will take phase A to ground fault. Means I will make that phase A VA voltage equals to 0. VA voltage is equals to 0. I'm going to make. Okay. Yeah. You please complete this one first. Please draw this quickly. Yeah, internal EMF will be always balanced, right? Internal voltages will be always balanced. Yeah. So in the next case, I am saying isolated neutral alternator, same thing. Neutral alternator with LG fault. LG fault on the phase A conductor, of course. So this is the thing I'm showing you. These are the phase conductors which we have called phase A, phase B, and it's a phase C. And I don't know about this IA current right now. B current and C current, I'll keep like this. Internal voltages will be remain same. Internal voltages will be remain same. Those are not going to be changed. Now, I'm taking phase A to ground fault, something like this. After taking that phase A to ground fault, phase A terminal voltage was fallen down to 0. Phase A terminal voltage was fallen down to 0. But this ground current, what you are saying now, ground current, what you are going to say now, it won't find any closed path in this circuit. It won't find any closed path in this circuit so that we don't have any fault current value in this particular situation. We don't have any fault current value in this particular situation. Clear? So IA value will be remain 0, but B and C currents are 0 because those two conductors are in the open mode. B and C currents are 0. Why in the sense? Those two conductors are in the open mode. Okay. What is the value of phase B voltage? And what's the value of phase C voltage? These two things we are interested to know. These two things we are interested to know. Okay. Don't pick up the answers from previous calculations we have done. Don't pick up your answers from the previous calculations what we have done. Okay. I'm asking one very, very simple question. Yeah. So I'm asking one very simple question to you. Just tell me. If simply I show one conductor to you outside in the three-phase line, phase A, phase B, phase C, three conductors here. I'm asking you to measure one of the conductor voltage, maybe phase B voltage now. With respect to what terminal you measure that voltage? I'm asking only what is one conductor voltage. With respect to what reference you measure that conductor voltage? With respect to ground, not neutral, because we don't know whether the neutral potential is 0 or non-zero. So we used to measure always that potential with respect to ground or zero potential. Good. So now this B to ground you have to measure now. B to ground. Ground is nothing but this terminal only, right? Just look at me. Look at this board. B terminal to ground means ground is this point only. So whatever the value you have here, that is your phase B voltage. Terminal voltage, terminal voltage, this value. Okay, this point and this point are same. This point, and this point is also same. Na? So now this VB, if you apply KVL to this loop, plus 2 minus VB, and then you have plus 2 minus EA, and then you have minus 2 plus EB. So it will result into EB minus EA in my view. Is it so? EB minus EA. Is it correct or not? I need your response here. I need your response. If you apply KVL starting from this terminal B to ground is nothing but A only. If you apply KVL to this loop, positive to negative VB, and then again positive to negative EA. So VB plus EA minus EB is equals to 0. So that EA minus EB, if we take to the other side, it will turn to be EB minus EA. And how much is this value, EB minus EA? So it is 11 by root 3 at minus 120 degree. Okay, minus, and you have EA 11 by root 3 at an angle of 0 degree in terms of kilovolts. Yeah, you please get this number how much? Anybody please tell me what's the value of VB here? It will result into 11 kV at an angle of minus 150 degree again, as it is the same number we got in the symmetrical component state. As it is, we got the same result as the symmetrical component state. Okay, Bhavani, we don't have closed path for the current flow, right? We don't have the closed path for the current flow. IA we took 0. We don't have the current. We don't have the closed path for current flow. KVL. Yes. Fine. How 150? You do that calculation anonymous certainty, you will get it. You take that difference, you'll get it. Next, what is the phase C voltage now? What is the terminal voltage of C? Terminal voltage of C means C to ground you have to measure. Na? So this point to ground is nothing but this side. C to ground is this one. And if you measure from C to ground, it will turn into EC minus EA. You have to apply that KVL. You have to apply this KVL from C to ground. And if you apply KVL, these two phases will come into the KVL loop. So it will come as EC minus EA. So what's the value of EC you have? 11 by root 3 at an angle plus 120 degrees minus 11 by root 3 at an angle 0 degrees in terms of kilo. So this number will come as 11 kilovolt at an angle of plus 150 degree in terms of kilovolts. I think all of you getting this one? Same voltages as we have taken earlier. Internal voltage will be always balanced, right? Internal voltages will be always balanced. That is a basic what we call condition we have taken already. If IA is 0, then VA not equal to EA. May or may not be. Sai Charan, you have to apply KVL, right? This terminal voltage you are measuring, right? Terminal to ground. Terminal to ground, how much voltage you have? 0, because you have a 0 impedance path. So fault current is 0. 0 into impedance is 0. 0 into 0 will be 0. 0 into 0 will be 0. 0 into infinity is undefined. Yeah. So see, in the earlier case, please listen. In the earlier case, means in the what we call non-faulted case, all the three terminals are experiencing same magnitude voltage. VA, VB, VC magnitudes are equal in numbers. Now, if you have a single line to ground fault on one of the phase conductor, single line to ground fault on one of the phase conductor, that particular phase terminal voltage is 0. Remaining two terminals, healthy phases terminals, voltage magnitudes become 11 kV. 11 kV. Earlier it is 11 by root 3. Now it is becoming 11 kV. Means the healthy phases voltages magnitudes are increased by root 3 times. Increased by root 3 times. For what condition you are talking this one? If you have single line to ground fault on a ungrounded neutral alternator or ungrounded neutral system. Okay? Yeah. So if you want, I will write that statement immediately. Later on, we will be concluding that. Let's take that statement, what I said. For LG fault on ungrounded neutral alternator, ungrounded neutral alternator, the healthy phases voltages will be increased by root 3 times. Increased by root 3 times. For LG fault on ungrounded neutral alternator, the healthy phases voltages will be increased by root 3 times. Or the healthy phases voltage magnitudes will be increased to their line-to-line voltage magnitude. Okay, so 11 kV by root 3 is a per phase voltage. How much is line-to-line voltage for you? 11 by root 3 into root 3, right? Means it is 11 kV. Following all of you. Or the healthy phases terminal voltages. Be clear about this term. Healthy phases terminal voltages will be increased to their line-to-line magnitudes. Okay, so to their line-to-line magnitudes, these voltages are increasing. Yeah, fine. Then what's the problem of this rise in the voltage magnitude? That we'll discuss, and then we'll conclude. Of course, we will discuss each and everything what I am saying now. See this. Listen. So I'm showing in the next slide. Look. So this is a simple alternator diagram I'm showing. 3 wires. Phase A, phase B, phase C wires you take. And it's a Y ungrounded neutral. Zn is equals to infinity. Let's assume that these lines are directly running on a transmission tower. These lines are directly running on the transmission tower. Maybe you choose this as a similar alternator, what we have studied earlier also. Similar alternator, what we have studied also, this one. Okay. And we have phase A corresponding cross arm, going to be called as cross arm, cross arm. Okay, like this we have 3 cross arms corresponding to the phases A, B, C. Corresponding to the phases A, B, C. So it's a phase A cross arm, phase B cross arm, and then this is a phase C cross arm. Actually, for this cross arm, we will be hanging some insulators. I'm showing that insulator in blue color like this. These are some insulators we are hanging to A, B, C like this. A, B, C. Now, you know, this phase A conductor, what we have, it is passing in this manner. Means phase A conductor is running and it's going through the number of towers by the support of this tower along with the insulator. And there's a phase B conductor which is passing something like this, you can say phase B conductor, and it was a phase C conductor. I am showing something like this. These are the 3 conductors passing on the tower, phase A, phase B, phase C conductor. All of you getting this one? All of you getting this? Okay, listen to my words. It's an ungrounded neutral system. Already we have done the mathematical calculation. Now, unfortunately, we have the phase A to ground fault occurred. And what is this phase A voltage becoming? 0. Magnitude of the phase A voltage will be 0. Now, in this particular situation of ungrounded neutral, what will happen to phase B voltage magnitude? What will happen to the phase B voltage magnitude? Anybody? Just now we have discussed, no? It will become line-to-line voltage magnitude, else you say it's 11 kV. Just from the previous problem. It will be increased by √3 times of pre-fault value. √3 times of the pre-fault value. Okay? If the pre-fault voltage is a rated voltage, then obviously it will come to be 11 kV. Now, what is this phase C voltage coming for you? Mod VC. This also comes to be 11 kV only. That also comes to be 11 kV only. Okay. Next thing. Very, very simple question I am asking you. Very, very simple question. See, if the phase B conductor voltage is 11 kV, phase B conductor voltage is 11 kV, who is experiencing that 11 kV? Who is experiencing that 11 kV? Anybody? Conductor B voltage is 11 kV. Who is experiencing that 11 kV? This phase B to ground insulator, right? Conductor to ground voltage is 11 kV, na? So conductor to ground is nothing but tower only, because tower potential is 0. A tower resistance is negligibly small. So the total 11 kV, what you said, conductor operating voltage, it will appear across this phase B insulator. And similarly, across the phase C insulator, you have the 11 kV, and across phase A insulator, you will have 0. Across the phase A insulator, you will have 0. Okay, but generally, these insulators of phase A, phase B, phase C, anything, overhead line insulators, generally designed on the basis of per phase voltage. But now a line-to-line voltage is appearing across that. Because of that, there is a probable flashover for this particular insulator string. There is a chance of getting the flashover for the insulator string. Okay, so in the next slide, what I am going to write is, if you are still drawing, please complete it quickly. You are still drawing, please complete it. If you have done, please raise your hands. Yeah, Ravikumar, you have a short circuit across the 3 voltages, right? You apply KVL in that loop. VA1 plus VA2 plus VA0. That's equal 0. Why? We have a short circuit across that. Yeah. So next, what I am saying is, that implies the healthy phases, insulators, overhead line insulators, better. Healthy phases, overhead line insulators are experiencing this line-to-line voltage magnitude. But these insulators are designed for these insulators are designed for per phase voltage. So to stop. So there is a possibility. There is a possibility. There is a possibility of insulation flashover. Flashover in phase B and phase C are in healthy phases. Overhead line insulation flashover. There is a possibility of overhead line insulation flashover in healthy phases. Okay, healthy phases. See that insulation flashover means simply I will show in this manner. So please complete it quickly. I will move to the next slide. Yeah. So if this is a transmission tower we are talking, and this was a conductor, and I am showing insulator here, overhead line insulator, something like this. So I will show simply lines sufficient. Right. Okay. Yeah. So now this conductor is experiencing over voltage. What we are saying now, over voltage, right? Because it is this insulator is experiencing a voltage more than its design value or rated value. So we do expect some flashover for this insulator string, something like this. We'll expect some flashover, something like this for this insulator string. So obviously this conductor, what we are saying, healthy conductor in the earlier case was grounded. Healthy conductor was grounded. And you see, C insulation is also getting flashover. Both B insulator was flashover, C insulator also getting flashover. What you can experience now? Anybody? Anybody? Please tell me. Yeah. It may be converted into a three-phase fault. First of all, this phenomena of insulation flashover, we are going to call as arcing grounds phenomena. Later on, what I will say is, if B and C phase insulators also getting flashover, I'm going to say this fault, what we said earlier as A to ground, converted into A to ground, B to ground, C to ground, means it is ABC to ground fault. Means it is three-phase to ground fault. Okay. Yeah. First, I'll write that statement. This phenomena is called as arcing grounds phenomena. Arcing grounds phenomena. Okay. So if arcing grounds occurs, on both healthy phases, then there will be then the fault will be converted into three-phase to ground fault. Then the fault will be converted into three-phase to ground fault. Then the fault will be converted into three-phase to ground fault. Okay. So there is nothing too difficult to feel here. Already I explained you in a sequence. If you have a single line to ground fault and an ungrounded neutral system, ungrounded neutral system. All the things we are discussing with respect to ungrounded neutral system only. And we said the healthy phases terminal voltages are increased by √3 times. I have proved two times. And I said the phase insulators what we have, these are designed for the phase voltage, per phase voltage. But now the line to line voltage is appearing across that. Because of that, there may be a possibility for flashover of the insulator strings. Okay, that phenomena is called as arcing grounds. What difficult to feel here? I don't know. Huh? Okay. And then you see, yeah, can't we design the insulators based on rate voltage? Bhavani, that's what I am saying to you. If these are designed based on the per phase voltage and line to line voltage is appearing across that, then there may be a flashover, I am saying. It may or may not be. It may or may not be. Okay. That depends upon your strength of the insulator. Depends upon the strength of the insulator. And as I said now, if phase B to ground, arcing ground occurred, for example, if you see in this diagram, just I will clear this one just by showing to you. Phase B to ground occurred. Phase C to ground also occurred. Already A to ground we have. Now B to ground happened and C to ground happened. So obviously you can say all the three phases are connected to ground. This fault is going to be called as three phase to ground fault. So earlier LG fault was converted into three phase to ground fault for a ungrounded neutral system. Ungrounded neutral system. Yeah. Next thing. I have to discuss some more things with respect to this arcing grounds phenomena. All the things what we are saying is on the ungrounded neutral alternator only. Next thing, listen please. For example, we have a delta connected alternator. We have a delta connected alternator operating at no load. Alternator at no load operation. No load operation. Something like this I will show. It's a delta connected alternator. Phases. So phase A or any one of the phase maybe. It's a second phase. Okay. We are showing one more phase here. One more phase like this. Next, I'll show these terminal names to you. I'll say it is plus minus, and if it's plus minus, it will be minus, and this is plus, and this is minus, and this is plus. Like this we have. I'm calling it is a terminal, and I'm calling this is B terminal, and this is C terminal. Like that I have taken. A, B, C terminals we have taken. Else better. One minute please. I'll show reverse symbols, because to get these voltages in a proper order, reverse symbols I am showing. This is plus minus. It is a ECA voltage. Okay, ECA voltage, and this top will be plus and bottom will be minus, and this is a EAB voltage. This will be plus and minus, and this is a EBC voltage. EBC voltage. Yeah. So this EAB value, it will be 11 kV at an angle 0 degree, something like this. But EAB value was 11 kV at an angle 0 degree. EBC value is also 11 kV only at an angle minus 120 degree. We are saying. Don't bother about the angles now. Don't bother about the angle. You think about only magnitude. ECA voltage is again 11 at an angle plus 120 degree in terms of kilovolts. These are the internal voltages of this delta connected alternator. Internal voltages of this delta connected alternator. What will be these terminal voltages you will feel now? What's the magnitude of phase A terminal voltage, phase C terminal voltage, phase B terminal voltage? Only magnitudes. I am not concentrating on angles now to not confuse you. With my angles. Just what is phase A, phase B, phase C terminal voltages? By √3. It will become by √3. It's not 11 kV. How many times I have to explain you? It will be 11 by √3 kilovolts. I am asking the terminal voltage, not the line to line. Okay. So it will be 11 by √3 kV magnitude. This will be again 11 by √3 kV magnitude, and it will be again 11 by √3 kV magnitude. We don't have a fault. No fault. No fault on the system. No fault on the system. Okay. Now in the very next slide, same diagram I will copy. I'll take phase A to ground fault. Phase A to ground fault. Then what will happen to phase A terminal voltage? Terminal voltage will become 0. Then what will happen to C? What will happen to B voltage? Yeah. Very simple. Just try to understand now. So I'm showing in the next slide. Same diagram. It's a delta connected alternator. Delta connected alternator at no load with the A to ground fault. A to ground fault. So phase A to ground fault was occurred like this. Phase A to ground fault. Then what is the value of VA now? How much is the value of VA? 0. Terminal voltage of A will be 0. Yes or no? Then what will be the value of C magnitude VC? And what's the value of VB magnitude? What's the value of VC magnitude and VB magnitude? Anybody? It will become 11 kV, 11 kV, right? C means C to ground, na? C to ground if we measure, that will be this value only. It will turn to be 11 kV magnitude. And B to ground means this voltage only. It will be again 11 kV magnitude. 11 kV magnitude. Means the healthy phases voltages was increased to the line to line magnitude. Healthy phases voltages was increased to the line to line magnitudes. Means, is there any possibility of getting arcing grounds phenomena on the delta connected alternator? Is there any possibility of getting arcing grounds phenomena on the delta connected alternator? Yes or no? Yes. Clear? So, in a simple way, in the next slide I will write. Please copy this one quickly. Please copy this one quickly. Still, we have not met any final conclusion. Still, we didn't met any final conclusion. First, we discussed about star ungrounded alternator. Now, delta. If it is star grounded, no issue. If it is star grounded, there is no issue at all. Apply KVL, anonymous attendee, you will get it. Just simply C to ground you have to measure, na? C to ground. C to ground means this is ground A, and how much is this voltage now? 11 kV only, right? B to ground. Ground is this point only. A itself is ground. B to ground means B to A. What is that B to A voltage? 11 kV in magnitude. Yeah. So let me move. So that implies there is a possibility. There is a possibility of arcing grounds. Arcing grounds on healthy phases in delta connected alternator at no load condition on healthy phases in delta connected alternator at no load condition for single line to ground fault. SLG fault, LG fault, A to ground fault, all these are synonyms only. Single line to ground fault. There is a possibility of getting single line to ground fault. When you are asking me same question, Bharat, I have explained this one many times while we are discussing about transformer little bit. So if it's a delta connected winding, for example, you see this one. If I am asking you this terminal voltage A, A means what? With respect to B you measure or with respect to ground you measure? With respect to, yeah, tell me please. With respect to ground or with respect to B? Again you are asking the same questions. With respect to ground. Now with respect to ground, how much is this voltage? Satish? With respect to ground, how much is this voltage, Satish? Tell me. It will be 11 kV by root 3. How it will be 11 kV? A to B or A to C, if you measure, that will be 11 kV. A to ground, if you are measuring, it won't be 11 kV, right? It will be 11 kV by root 3 in magnitude. Yeah, I'm not getting any response. Please tell me. For your delta winding, line to line voltage equals to phase voltage, I am not disturbing that statement. Where I am measuring this statement? Where I am measuring this one? At the outcoming terminals, right? At the outcoming terminals. But ground is not there. You take. They are thinking lines also are also delta. Yes. Yes, Satish. Sai Charan. Terminal is nothing but conductor with respect to ground. That's it. Terminal voltage is nothing but conductor voltage with respect to ground. Okay, if you have still a doubt, please ask me in a doubt session, Satish and all. If anybody having a doubt, I will explain you even more clearly in the doubt session if you have anything. Yeah, let me continue. Fine. Next thing, listen. So I'm taking up one more thing to you. Just observe here. Okay. So I'll tell this statement before moving ahead. If you have a single line to ground fault on a star grounded alternator, why grounded alternator? Is there any possibility of getting the arcing ground? Is there any possibility of rise in the healthy phase voltages? No, we don't have any rise in the healthy phases voltages. Means I can write this statement as simply for LG fault on Y grounded neutral alternator, there is no rise in healthy phases voltages, that implies no possibility of getting arcing grounds. No possibility of getting arcing grounds. Arcing grounds. Okay, done. Next. So I'm showing one question to you. Question in the sense, some single line diagram. I'm asking one question. In the next slide. For example, so I'm taking one single line diagram, SLD. Single line diagram. Just observe. It's an alternator connected to one transformer. Till now, we discussed only with respect to alternator. Now I'm discussing that in a generalized way, in a big system. Generalized way in a big power system network. Okay, so this is a line. We have transmission line wire. Other side also we have one transformer like this, and this is operating at no load. Open means no load. Okay, first this generator is a star grounded. And this transformer I am showing delta star unground, and this is a star grounded. Now, this is the location of fault. Single line to ground fault at F. SLD means single line diagram. Single line diagram. So LG fault, phase A to ground fault at F location. Phase A to ground fault at F location. Ground fault at F location. Okay. What will be the phase B and phase C voltages? Is there any possibility of getting arcing grounds? See, Dinesh, once after arc was happened, the fault was converted into a different fault, right? Then why you are bothering about it? Fault current is flow through, it is so arc occurs fault phase. I don't know what's your exact doubt, Dinesh. Are you clarifying your statement? Yeah, please tell me. Do you have any possibility of getting arcing grounds? No possibility. Many of you are saying. Somebody saying yes also. Okay, think. Listen. Why arcing grounds comes? We should go in a reverse trend. Why arcing ground comes? Nearest reason is because of rise in the healthy phases voltages by root 3 times. Okay, why that rise in the healthy phase is happening? Why that rise in the healthy phase is happening? Anybody, can you tell me mathematically? Anybody, please tell me. Anybody, why we are having that rise in the voltage? Because zero fault current. Okay, why you have zero fault current, Abhijit? Why you have zero fault current? Tell me, please. Very simple. Why you have zero fault current? Because your zero sequence circuit is open. Zero sequence circuit is open. That's the reason for all the things, right? Your zero sequence circuit was in an open mode. That's the reason why this VA0 is becoming minus VA1, and that is leading to rise in the phase B and the phase C voltage is what we have discussed till now. Means in that single line to ground sequence networks connection. If the zero sequence network looks as open, so obviously we can expect that we have the phenomena of the arcing grounds here. Following all of you. So in that sense, if anybody asks you, do we have any arcing ground or not at a particular LG fault location, what you have to do simply is you find out the zero sequence Thevenin impedance with respect to that fault location. Find out the zero sequence Thevenin impedance with respect to that fault location, and you confirm if the zero sequence Thevenin impedance is infinite, you don't have any, you have arcing ground phenomenon. If the zero sequence impedance is finite number, not equals to infinite, then we don't have the zero arcing grounds phenomenon. Okay, so let me check this one. Let me check this zero sequence network. I have to draw for this. Just try moving to the next slide to check that zero sequence network. First, you have a generator. Generator means up to neutral, we should keep zero sequence impedance of generator. Neutral to ground, it is solidly grounded, so we should keep 0. Yeah, this is generator representation. Transformer, delta star. Let me show open diagram first. First transformer, zero sequence impedance. Primary side delta connection means we should close a shunt switch here. Secondary side what connection? Star ungrounded. Star ungrounded means you should show this one open. Next, line, we have to divide that into two parts. First part of line, and then it's a second part of line. So it is a half of the zero sequence impedance, and this is a location of a fault, what we are saying. And other side, what we have, star unground, star grounded transformer. Okay, so I will show this zero sequence impedance of transformer. It is a ZT0 of 2. Okay, second transformer. Primary, it's ungrounded neutral. Secondary is a solidly grounded neutral. So you can short this. And other side, it's automatically open. So now, if you think with respect to this fault location, how much is that zero sequence Thevenin impedance value? Right? How much is that zero sequence Thevenin impedance value? That will be equals to infinite. Okay. So with respect to the fault location, Z0 equivalent value is equals to infinite. So if that Z0 equivalent is equals to infinite, yeah, Manish Kumar, you will you calculate the zero sequence current only with the zero sequence network? If the zero sequence network which is having infinite impedance connected in parallel may not have, see how if it's a single line to ground fault, there is no choice for you. You have to connect all the three sequence networks in series. That's it. There is no connection of parallel here, right? Now, yeah, you can say that, Vaishnavi, you can say that. Yeah, please listen. Z0 equivalent equals to infinite. That implies zero sequence circuit will be open. Zero sequence circuit will be open. Will be open. So, in the next slide, what I will say is for LG fault, the post-fault sequence voltages, voltages will be VA1 value will be equals to EA1 number, VA2 value equals to 0, VA not value is equals to minus VA1, else you can call that as minus EA1. That implies phase B and phase C voltage magnitudes will be √3 times of actual values, or will be increased to their line-to-line magnitudes. Line-to-line magnitudes, that implies arcing grounds occurs. That implies arcing grounds occurs on B and C. Then in delta, we have a possibility of arcing grounds. Yes, I discussed just now, Vinita. We are getting the doubt again. Just now I explained about delta also, right? Why there are no arcing grounds in a star grounded system means that zero sequence network was closed. We have some current flow and you don't have a high value of VA0. Okay, VA1, VA2, VA0, some probable numbers you get. You take one grounded system, Jadhav Pradeep. You take one grounded system, calculate the post-fault voltages of phase B and phase C, then you confirm it first. Okay. What if fault takes on B? Obviously, A and C will rise to √3. What's there in that? Simple thing. You take that circuit and analyze it. Three-phase circuit. Yeah. Fine. Next thing. So what's the conclusion now? The conclusion is obviously if Z0 equivalent is equals to infinite, zero sequence Thevenin impedance equals to infinite, for LG fault, there is a possibility of arcing grounds definitely in the system. Okay, done. Next. So this is one sort of conclusion you have to understand for the arcing grounds. Then how to avoid these arcing grounds? We are saying we have to go for the grounding of the neutral, or we have to maintain that zero sequence Thevenin impedance value as low as possible. Then it is possible to avoid the arcing grounds phenomenon. Before moving to that also, possibility, anonymous certainty, possibility, not 100%. I am saying it is possibility. I am saying you one more thing here regarding that same arcing ground phenomena only. I am saying one more thing. Listen. Number one, we have an ungrounded neutral alternator, Y connected to one short transmission line operating under no load. It's a short transmission line operating at no load. Okay, this is one thing. Second case, star connected ungrounded neutral alternator connected to one very long length of transmission line. Long transmission line, again, it is also operating under no load condition. So this is one, this is one. Yeah, you can make that type of comment on your own, Imtiaz, but I don't suggest it. Definitely alternator neutral has to be grounded. Transformer neutral also has to be grounded, because we don't know where the fault is going to occur. It may occur on the alternator terminals, right? For example, in the previous case, if the alternator neutral is not grounded, and if you have fault at the terminal of the alternator itself, then there's a possibility of arcing ground. Yeah, listen, please. Listen. In these two cases, definitely, if you have phase A to ground fault at this place, phase A to ground fault, phase B and phase C voltage magnitudes will rise up. Phase B and phase C voltage magnitudes will rise up to root 3 times in the first case. Second case also it will rise up to root 3 times. Root 3 times of what? I need a perfect answer here. I need a perfect answer from many of you, what I am expecting. Ungrounded neutral system. Ungrounded neutral system. Fault occurred from phase A to ground. Phase A to ground. Remaining two phase voltages will be increased by root 3 times. Root 3 times of what? Root 3 times of what? Root 3 times of pre-fault voltage. Root 3 times of the pre-fault voltage, not the EMF of the generator. Root 3 times of the pre-fault voltage. Getting me? Anybody have a doubt? Mangesh, please tell me. Pre-fault voltage. Okay, in the earlier diagram, maybe this diagram you can feel. What is EA1 here? Pre-fault voltage, right? EA1 is what? Pre-fault voltage we have to consider. Pre-fault voltage you have to consider. Okay, now tell me your answer, please. Tell me your answer. See, before occurrence of short circuit, we have some pre-fault voltage at this end, at the end of the transmission line. We have some pre-fault voltage at the end of this transmission line also. Else, I will write in a different color. Okay. Pre-fault voltage at this case is VPF1. You feel if you want. Pre-fault voltage. Pre-fault voltage. Else, one also I will remove. You confuse with positive sequence and negative sequence. Okay, here also I will have some pre-fault voltage as VPF. Pre-fault voltage as VPF. Anybody, I am asking one very simple question. If you have studied, you tell the answer. If you have not studied, just listen to me. How is a pre-fault voltage at the end of the long transmission line under no load condition? Is it a high value or low value? How is a pre-fault voltage? Pre-fault voltage at the end of the long transmission line under no load condition. Is it low or high? It will be high because of Ferranti effect. There is some Ferranti effect, right? Ferranti effect means simply, listen, Sai generating, listen here. Ferranti effect means because of the capacitive current flow in the transmission line wire. Because of the capacitive current flow in the transmission line wire, there is a possibility of rise. There is a possibility of rise in the receiving end voltage magnitude as compared to the sending end voltage magnitude. This we are going to name as Ferranti effect. Ferranti effect. Okay. See, if you have that Ferranti effect, and if you have that phase A to ground fault, what will happen to the phase B and phase C voltages here? Phase B voltage magnitude equals to root 3 times of pre-fault voltage magnitude, and phase C voltage magnitude will be equals to root 3 times of pre-fault voltage magnitude. As this pre-fault voltage magnitude is very, very high because of the Ferranti effect, more than 1 per unit, more than the rated voltage, definitely this VB and VC magnitudes will go high. It may not be 1.732 times. Root 3 is 1.732, right? It may not be 1.732 times. It's 1 point. So it will be higher than that also, higher than the rated line-to-line voltage. That may cause a severe arcing ground in this particular situation. Yeah, I am not getting this. Have you understood this or not? Please tell me. Rather than grounding, why can't we increase the rating of insulator to prevent the arcing? Obviously, government will not support to do that. Yes or no? Then we will become a bit inefficient engineers in the way of saving cost to the government. Yeah. So yeah, I'm saying again, please listen here. Somebody is asking me. Ferranti effect is more severe, particularly for long transmission lines. For short transmission line, we may not have any Ferranti effect at all. So in that particular situation, the pre-fault voltage of short transmission line might be 1 per unit or close to 1 per unit, you can say. But if it's a long transmission line like this, and the pre-fault voltage value definitely higher than 1 per unit, and it may be 1.3 per unit, 1.2 per unit in that manner. If that is the case, that 1.2 into root 3 per unit is a phase B voltage. 1.2 into root 3 is a phase C voltage. Because of that, the rise in the phase B and phase C voltage magnitudes will be higher as compared to previous one. This higher rise in the voltage may cause for the arcing grounds. Okay, so in this first case, if you want to write, this VPF magnitude may be close to 1, and this VPF magnitude might be definitely greater than 1. In bracket, you write Ferranti effect. Ferranti effect. So I'll write in the next slide. So the arcing grounds phenomena, is more severe on long transmission lines, associating with ungrounded neutral system. Ungrounded neutral system associating with ungrounded neutral system operating at no load. Operating at no load condition. So I think many of you have cleared these statements, what I have mentioned. So to overcome the issues of this arcing grounds and all, we should go for the grounding of the neutral. Yeah, yes, Gomati Shankar, yes. Right. So before moving to that direct point of grounding and all, first I want to tell you what are the different types of groundings. That we'll discuss. After that, we put our concentration mainly on the neutral grounding. Yeah. So I'm saying in the next slide. Types of groundings. Two types I'm saying here. Two types. Number one. It will be equipment grounding, or you can say apparatus grounding. Equipment grounding, or you can say apparatus grounding. Equipment grounding, or you can say apparatus grounding. Yeah. See, equipment grounding in the sense, for example, if you see one transformer outside, for example, if it's a transformer tank for you, right? So it's a transformer, and it was a tank of the transformer. Inside the transformer, we have windings and you have oil. And on the top of the transformer, we have some bushings and all for the incoming as well as outgoing terminals. Incoming as well as outgoing terminals, we will be having some bushings, something like this. Okay. So inside this transformer, we have some windings. Number of windings we have. It's a schematic diagram. Don't think about why star is drawn only 3 windings. Is it only 3 windings exist? I'm not saying all these things. Number of windings are there with some oil. Okay. See, listen here. See, definitely, wherever these windings, primary and secondary windings, are carrying their own currents. According to loading and all, producing some flux. Primary and secondary windings will produce a flux. So whatever the flux produced by the primary winding, it should link with the secondary winding, and secondary winding flux should link with the primary winding. To have the linkages in a perfect way, we are keeping the core. We are keeping that core to have the coupling between the windings as more effective. But still, even though you say it's a effective coupling and all, that coupling factor will not become one. Coupling factor will not become one. So definitely there is some leakage flux. There is some leakage flux from this winding which may link with the tank. There will be some leakage flux which may link with the tank. See, because of that leakage flux linking with the tank, listen please. Because of the leakage flux linking with the tank, definitely as it's a metallic body, experiences some EMF induced. Experiences some EMF induced. So if it's experiencing some EMF, maybe a less value, but still, if you touch the transformer tank, there is a possibility of getting shock. There is a possibility of getting shock. To avoid that one, to avoid that shock, we have to connect this tank body, metallic tank to ground. Metallic tank to ground. See, by grounding this tank in a proper way, we can expect that this tank potential will be close to 0, so that we can avoid the EMF induced in the tank. Else, even though you touch the tank, there is one short path for the current flow. Whatever the leakage current delivered by the tank, that will be grounded via this path, and you may not get an effective shock. All of you getting my point? All of you getting this point? So this the people will call as earthing. Okay, in the what we call nomenclature or notations, the people will call this as earthing. But in my view, grounding and earthing both will be same. But anyhow, in the way of outside talk, just you say, if you connect the equipment body to ground, you call that as earthing. Okay, so it is going to be called as earthing. Why we are doing this one? Why we are doing this earthing? For the protection of the personnel, or you can say for the protection of, or for the safety purpose, we are doing this. So this is done. For personal safety. So it's a transformer tank, metallic tank connected to ground. Yeah, just if you have any transformer just outside your house, just look at the transformer and you observe one GI wire, galvanized iron wire, that they are connecting to ground in a proper way, right? So that is going to be called as earthing. Yeah, next thing. Next thing we are going to say, second one, that is neutral grounding, or you can say there's a system grounding. Second one, it's a neutral grounding. Or you can call that as system grounding. Neutral grounding, or you can say that's a system grounding. Both are same terms. See, in this, what you do is, in case of a three-phase system or three-phase winding, maybe it's a transformer star winding or generator star winding. The junction point of the three-phase windings, that we are calling as neutral. So this is one difference. Many people used to ask me by a confusion, sir, what is neutral, what is ground? Ground is a thing on which you are standing. Earth, that is the ground, that's it. What do you mean by neutral? Neutral in the sense that is the junction of the three phases of your three-phase system. That's the neutral. If you connect that neutral to ground, I'll call that as neutral is connected to ground, means the neutral might be maintained at the ground potential, which is assumed as 0. Right? So neutral grounding in the sense simply connecting neutral of three-phase winding to ground. to ground, or you can say earth, no issue. Ground or earth. Ground or earth. Yeah. So now I will be extending our discussion with respect to this neutral grounding concept only. Neutral grounding concept. So what will be the purpose of that neutral grounding? That we'll discuss first. After that, we will see simply what are the different types of that neutral grounding techniques. That's it. So next slide, I'm taking up purpose. Purpose of neutral grounding. Neutral grounding. What is the purpose of the neutral grounding? Already we studied till now, na? Before discussing this previous topic, we studied about ungrounded neutral and so one thing I can say first purpose here, that is to avoid a rise in the healthy phases voltages. To avoid rise in the healthy phases voltages onto grounded faults. Okay, so to avoid it, we have to ground the neutral. That's the meaning. Okay, so to avoid rise in the healthy phases voltages, yeah, during grounded faults, Grounded faults means what are the different types of grounded faults? What are the different types of grounded faults we have? Different types of grounded faults. We have LG, LLG, triple LG. LLG, triple LG is there, but triple LG, all the three phase voltages will be zero. There is no LG phase. In the triple LG fault, all the three phases affected by fault, so there is no healthy phase at all. So I can say simply LG and double LG. That's it. Okay. Second one. Particularly for LG fault, I am saying. Many of the people are saying me earlier also, sir, if you have a single line to ground fault on an ungrounded neutral system, something like this. For example, this is a thing. You have an ungrounded neutral alternator, and you said that phase A to ground fault occurred. Phase B and phase C voltage has been raised. But how to identify this fault? How come I know that the fault has been occurred on the system? Generally, this short circuit fault is going to be detected by a circuit breaker and relay. Maybe relay, I will say something. Relay is a sensing device. Na? So we used to keep some relay on the transmission line wire. And if you have single line to ground fault occurred, but you don't have any current flow, means you don't have any fault current flow. So the relay will simply, it will be in the idle state. Because the relay is unable to sense that as a short circuit fault. Following all of you. So to make our relay or to make our protective switchgear, to sense that there is a short circuit fault, particularly for LG, I should provide neutral grounding to the system. Okay, so to provide a possibility, or you say for ungrounded neutral system, LG fault current is equals to 0. LG fault current is equals to 0. That implies relay may not sense this fault. Relay may not sense this fault. So to provide a possibility of fault sensing, the fault current shall be circulated. That implies neutral must be grounded, or neutral grounding is necessary. Neutral grounding is necessary. Neutral grounding is necessary. Okay. Neutral grounding is necessary. So it's a second aim or purpose of providing the neutral grounding. I will tell you the third purpose in a reverse way. Third purpose I am going to say. Of course, to limit that neutral voltage close to zero. To limit the neutral voltage close to zero. For that purpose also, I will say that. Third one, to limit neutral point voltage. Neutral point voltage to a very low value. To a very low value, neutral grounding must be done. Neutral grounding must be done. Yeah. So next purpose I am saying you. Next purpose. See the issue, Likita. As it is an ungrounded neutral system, kindly understand how I am saying these things. Yeah. See, whenever you have an ungrounded neutral system, you have a single line to ground fault. I am feeling that our relay is not sensing that as a fault. To provide the possibility of sensing of that fault, we have to provide that neutral grounding. Okay, we have grounded the neutral. Next issue, what I feel is that current is very heavy. We feel that the fault current is very heavy. And to limit that fault current, again, we have to provide some impedance between that neutral to ground. Okay, see, definitely, in my field, in my opinion, if you find a solution to avoid one problem, definitely one more extra problem will be created. One more new problem will be created. It will be an endless thing for anything, may not be in power system or anything. If you provide one solution to solve one problem, definitely with that solution, one more problem will be created. That problem now is heavy current. Okay, to reduce that heavy current, I will be providing some impedance between that neutral and ground. If you provide that neutral to ground impedance, again what problem will come? Zero sequence voltage may rise up little bit. Zero sequence voltage may rise up little bit. That may cause for little rise in the healthy phase voltages. Again, we have a problem. Following all of you. So we have to go in a compromised way. All the time. Yeah. Next thing. Next thing. Fourth one I am saying you. Fourth one. Just look here. Practically, distribution system, if you think, particularly secondary distribution system, household loadings or domestic loadings, these things, if you think, we have a 3-phase 4-wire system there. 3-phase 4-wire system means we will be providing neutral wire to the consumer also. Neutral wire to the consumer we will be providing. Okay, such a type of distribution system I am drawing here. See, this is one distribution transformer. Look, this is one 3-phase distribution transformer. 3-phase distribution transformer. So I am showing the 3-phase wires R, Y, B, phase A, phase B, phase C. Anything. So it's a phase A wire I am showing to you. It's a phase A conductor. And I'm showing phase B conductor, something like this. Phase B conductor. And I'm showing that phase C conductor, something like this. These are the phase conductors A, B, C. A, B, C conductors we have like this. Phase A, phase B, phase C conductors. And you have a neutral wire also provided. 3-phase 4-wire system. Okay, we have a neutral wire also. That neutral wire also I am showing something like this in the bottom end. Showing that in the bottom end, something like this. Okay. So this tank is connected to ground. Tank is connected to ground. From that only we are having this one. Let me show in a even more clear way. So we have this star winding. Shortly I am showing here star winding. I will clear this and I will show the star winding better. Okay, it will give more clarity to you. It's star winding, and this is A conductor, and this is B conductor, and this is a C conductor connected, and this was a neutral. That neutral wire generally connected to tank practically outside. Practically outside, it's connected to tank, and the tank is connected to ground. Tank is connected to ground. So obviously, neutral grounding, tank grounding, both will be same. Okay, you observe outside. You observe outside any transformer you see, simple distribution transformer, and obviously you see only one grounding. One grounding you observe connected to tank. That wire what we have is going into the transformer, and it is connected to neutral of that. Neutral, we will draw one wire connected to tank. Tank is connected to ground, means this neutral is also connected to ground. And it was a neutral wire which we are running on the distribution towers, distribution poles. Distribution poles. Yeah, you please tell me, have you understood this, what I said? Have you understood this, what I said? Please tell me. I need your response, please. Okay, good. Now, many of the loads in your distribution system are single phase loads only. Single phase loads. So maybe phase A to ground, some number of houses are connected. Phase B to ground, number of houses are connected. C to ground, also number of houses are connected. So I'm showing those loads to you. Phase A to ground, some value of load is connected. Phase B to ground, again some amount of load is connected. Phase C to ground, again some amount of load is connected. Done. Next. See, it is a definite thing. It's a definite thing to say. I can't sure that exactly this phase A number of houses connected, number of quantity of load connected, phase B to neutral load connected, phase C to neutral load connected as equal. I don't expect that phase A, phase B, phase C loads as exactly equal, because each and every house will draw their own power. So according to their demands, definitely phase A, phase B, phase C powers will be continuously changing. So definitely these three numbers will be unequal. So I'm saying some numbers to you. So first one, maybe 20 kilowatt, it is drawing the power. Phase B is drawing some 10 kilowatt power, and next one is drawing some 22 kilowatt power, like this. These are the powers drawn by each and every load. Okay, now neglect these wire impedances, line impedances, you neglect. Okay, you assume that these induced EMFs are balanced here. These induced EMFs in the three-phase distribution transformer winding, balanced voltages. So as this neutral is connected to ground, and this neutral is also grounded, obviously. Phase A will experience, means phase A load will experience exactly phase A winding voltage. Phase B load will experience exactly phase B winding voltage. Phase C load will experience exactly phase C winding voltage. All of you getting me? Means even though these loads are unbalanced on the phase A, phase B, phase C, even though the loads are unbalanced, definitely the voltages are balanced here because of the transformer induced EMFs, and the network connected between this distribution transformer and loads might have very, very low impedance in our expectation. This point you should be very clear what I am saying. So in this case, load voltages are balanced. Loads voltages are balanced because this neutral is connected to ground here. Transformer neutral is connected to ground, and this neutral wire is also connected to ground. So definitely this load will act as a star grounded load only. So star grounded source, star grounded load, even though loadings are unequal, the loads will experience equal voltage in the phase A, phase B, and phase C in magnitude form. Yeah. Yeah. So if both source and load neutrals are grounded, neutrals are grounded, in bracket, no impedance for connected line, no impedance for connected line means distribution line. Okay, then load will experience balanced voltages, even though load is unbalanced, even though the load is unbalanced, even though that load is unbalanced. Yeah. Load currents are unbalanced, we can say if you want. Okay. So if it's a grounded system, it's fine. That's what I'm saying you here. If it's a grounded neutral system, that's fine to me. We don't have any over voltage or under voltage. Load is getting supplied with the required. But see, in the same system, I copy this, in the same system, if that neutral wire was cut, disconnected, if that neutral wire was cut, or you can say disconnected, then what will happen? Observe in the next slide. If the neutral wire was cut, or disconnected, if that neutral wire was cut, or you can say disconnected. So if this is disconnected, what you can experience now? If this disconnect was happened, what will happen? What will happen now? Delta again we have a problem, right, Aishwarya? Delta again we have a problem. How can you ask that type of question again? In this case, you tell me please. In this case, tell me please. This neutral wire was cut, means source neutral is grounded. Source neutral is grounded. What about your load neutral? What about your load neutral? Not connected to ground, right? Load neutral is not connected to ground. Because of that, because of this unbalanced loading, these phases will experience unbalanced voltages. Okay, so in this case, unbalanced voltages will be experienced by this load. Unbalanced voltages will be experienced by this load. See, for example, if you talk these three loads in the form of impedance or resistance, in the form of impedance or resistance, if you talk, see, this first one is load impedance A, ZLA. Second one is load impedance B. Third one is load impedance C. Which load impedance is high in your expectation? Which load impedance is high in your expectation? Tell me please. Which load impedance is high in your expectation? Definitely, whichever the load having less amount of power demand, that will have a high impedance, right? Because power is nothing but V square by resistance value of the load. Power is nothing but V square by resistance value of the load. So whenever you are saying this power demand is very low, definitely load resistance is very, very high. Means this B phase load what you have, B phase loading what you have, that is of light loading. That's of light loading. Because of that, definitely I can say this loading impedance is very, very high. So B phase will experience high amount of impedance, means that load itself might experience a over voltage compared to the remaining two wires. All of you getting my point? We have to go with the voltage division technique and all to find out that. Okay. So I'll say in the next slide. In this situation of neutral wire cut, in this situation, the lightly loaded phase, will experience over voltage. That implies the loads kept under that phase will be severely damaged. The loads under that phase will be severely damaged. Okay. So actually this we are discussing in a reverse way. First we have gone for the grounding. We said there is no issue. If that neutral wire was cut, means if the load neutral is not grounded, better way. If the load neutral is not grounded, and moreover it is an unbalanced load, in that situation, unbalanced voltages will be experienced by the load. Particularly some phase may experience a over voltage, some phase may experience under voltage. Because of that, there is a possible damage for the loads. Okay. So final conclusion is to overcome the issue of over voltages, in supplying unbalanced loads, the load neutral must be grounded. The load neutral must be grounded. Load neutral must be grounded. So this is the purpose of neutral grounding. Another purpose of doing the neutral grounding. Yeah. So please complete it quickly. Yeah, somebody is saying that each home should be grounded and all. If you have that type of doubt, please ask me in the doubt session. Okay. I will discuss about that home grounding and all. There I can tell you exactly what's the difference. That's why we don't use delta, Aishwarya, to supply the three-phase unbalanced loads. That's why we don't use delta to supply the unbalanced loads. Lightly loaded because it's neutral grounded, right? Earlier, in the previous case, without that neutral wire cut, exactly this neutral was linked to this ground. So you draw the star winding elaborately. You draw this load and neutral grounded. This neutral is also grounded, common. So obviously this will experience exactly this voltage. This phase B will experience exactly this phase B voltage. C will experience exactly phase C voltage. But that's not the thing in the next case. You can't apply KVL to say this voltage is this phase A winding voltage. It may be a different number. Okay, next we can go for I'll come to your doubt anonymous activity. You come to doubt session and ask me that same doubt what you have asked me. That's what house grounding and all. Somebody is asking me each home should be grounded and all. That's a different thing. Not comparing with this one. If you have that, you can ask me. Yeah. So let's move ahead with the types of groundings. Means types of neutral grounding techniques. Till now we have discussed about purpose. Now I am moving with the types of neutral grounding. Neutral grounding. Types of neutral grounding. First one. Simply connect that neutral to ground with zero impedance. Connect that neutral to ground with zero impedance. That we can say as solid grounding or effective grounding. Solid grounding or effective grounding. Solid grounding or effective grounding. Effective grounding. Grounding means simply we will be connecting this neutral to ground with zero impedance, which is not at all practical, which we feel, yes or no? Is not at all practical. Why? In the sense, this neutral wire, ground wire, whatever you take, it will have some impedance, right? It will have some impedance. Okay. So even though you say we have a zero impedance between neutral and ground, definitely the connected wire will have some impedance. Yeah. Second one. Grounding this neutral with a resistor. You can say resistance grounding. Resistance grounding. So grounding this neutral with a resistor, something like Rn. Neutral resistance as Rn. Okay. Third one, grounding that neutral with a reactance, calling that as reactance grounding. Reactance grounding means star neutral is connected to ground with a reactance. I'll call that as JXN. Impedance is JXN. Reactance. Again, this is also not possible because this reactor, what you are connecting, that will have definitely some value of impedance. Sorry, resistance. Some value of resistance. This is also not possible, but still we will say it is a reactance of value JXN. Next type of grounding is a resonant grounding. Fourth one, a resonant grounding, or you can say this as a Peterson coil grounding. Peterson coil grounding, or some other name, I'll say arc suppressor coil grounding. Arc suppressor coil grounding. Resonant grounding, Peterson coil grounding, or you can say that as arc suppressor coil grounding. In this case, this neutral is connected to ground. Neutral is connected to ground with a reactor only. Here also it will be a reactor only, but that is a tunable reactor. It was a tunable reactor. It will be a tunable reactor. It will be a tunable reactor. And this reactor inductance value, LR, formula I am giving you, I am not going for any derivation here. LR is equals to 1 by 3 omega square into capacitance per phase of the system. 1 by 3 omega square into capacitance per phase of the system. It's a resonant coil inductance, you can call, or arc suppressor coil inductance. Arc suppressor coil inductance. Coil inductance LR is equals to 1 by 3 omega square capacitance per phase. Capacitance per phase. Okay. Next thing. For example, for the system, what you are providing grounding, for the system for what you are providing the grounding. If it is having low value of capacitance, if it is having very, very low value of capacitance, then definitely LR value will be high. Inductance of that reactor required will be large. If that inductance of reactor required is large, then obviously the number of turns to be kept in that reactor will be large. So inductor will become bulk. So size of the inductor will be more, means cost of that inductor is also high. At that time, this resonant grounding is not economical. It's not economical. Okay, fine. So I'll say that same statement. If capacitance per phase of system is low in number, then the required LR is large value. LR means resonant coil inductance is large value. That implies coil required will be bulk in size. That implies cost of coil is high. So that implies resonant coil grounding is not economical in this case. A resonant grounding is not economical in this case. Not economical in this case. See, if that is not economical, which grounding you have to suggest? To limit the current, which grounding is suggestible to you? Resistance grounding we have to prefer. If resonant grounding is not economical to you, then you move for the resistance grounding. Okay, so that implies in this case, resistance grounding can be used. Resistance grounding can be used. See, particularly if you think about a three-phase alternator, length of that equipment, physical length of that three-phase alternator is very less compared to your transmission line and all, I'm saying. Okay, so capacitance per phase of the alternator is very, very low in number. So I am saying for alternator, capacitance per phase is very low value. So obviously this resonant grounding is not economical. Resonant grounding is not economical because of these reasons what I have given here. So in that case, which grounding is preferable? I am saying resistance grounding. So I can say in a single statement, alternator neutral has to be grounded with resistor in the view of economy. Following all of you, in the view of reducing cost of grounding, we should prefer to go for the resistance grounding for the alternator. Okay, yeah. So I'll say for alternator, C per phase is low. That implies resonant grounding is not economical. Resonant grounding is not economical. That implies resistance grounding is preferable for the alternators. Resistance grounding is preferable. Grounding is preferable for the alternator. For alternators. Okay. Resistance grounding is preferable for the alternator. Yeah, later on I will tell some more reason why we prefer resistance grounding for alternator, maybe in the view of stability. There also, in the stability analysis also, I will repeat this grounding. Where we will use reactance grounding, where we will use resistance grounding. Those things we will discuss while we are moving to the stability analysis, particularly transient stability. Okay. So this is end of the single line to ground fault. What we are saying, single line to ground fault. As a final statements with respect to this fault, I'll tell some more thing with respect to LG fault only. After that, we will move to that double line fault. double line fault. Yeah, look here. Look here as an example I am saying you. See, this is one single phase system. Sorry, three phase system we have. Some connections for this generator, transformer and line. You assume like this. Okay. So at the end of this system, we have a single phase load. We have a single phase load, not a fault. Not a fault. Single phase load. Yeah, if you want me to elaborate, I will show this terminal, end terminal, three lines like this. Phase A conductor, phase B conductor, phase C conductor. Like this we have. These are the three conductors I am showing. And you have phase A to ground load. R load. You don't have phase B to ground load and phase C to ground load. So obviously, whatever the load current you feel, that will flow in the conductor A. And you don't have current in the B conductor and you don't have current in the C conductor. It's a single phase loading. It's a single phase loading on the system. Okay, anybody, please tell me how to calculate this load current. How to calculate this load current? Single phase loading. Single phase loading, I am saying. How to calculate this load current? Yeah. How to calculate this load current? Can we treat this as an equivalent to LG fault? We should feel that it is an equivalent to LG fault. LG fault. LG fault with fault impedance. LG fault with fault impedance. Yes or no? At the time, what we should do with respect to this load location? With respect to this load location, we should draw positive sequence network, negative sequence network, zero sequence network, connect them in series. Connect them in series. And across that, we keep 3 times of ZF. That ZF means you should keep 3 times of the R load. 3 times of the R load we have to keep. And you find out that sequence current. And 3 times of that sequence current is nothing but your phase A current, or you can say load current. Yeah. All of you getting this one? Tell me please. Getting this? But only one difference here. One difference here is, listen please. One difference here is what reactance you take for alternator in the positive sequence. Negative sequence and zero sequence reactances will be as it is. Negative sequence and zero sequence reactances will be as it is. How will be the positive sequence reactance of alternator to be considered in this load analysis? Means XD we have to take. It will be the steady state reactance we have to consider, not the value of subtransient, because it is a load analysis. It was a load analysis. All of you getting? Steady state. X2, X0 values will be remain same. X2, X0 values will be remains same. You have to draw positive sequence network with XD, Negative sequence network, zero sequence network. You connect them in series. Across that, we should keep 3 times of the load resistance. 3 times of the load resistance. And you find out the sequence currents. And in this case, you know, all the 3 sequence currents are one and same. All the 3 sequence currents are one and same. And 3 times of any one of the sequence current is a load current, or you can say phase A current. Load current, or you can say this as phase A current. Phase A current. Yeah. Next, one more simple thing I want to extend this. One more simple thing. Dinesh Roy, have you understood this? Dinesh Roy. Yeah, if you have completed, I will tell one more thing to you. One more thing, very simple thing, of course, very simple thing. negative and zero sequence impedances in the state, steady state as well as subtransient will be same. Only positive sequence impedance will change from one state to other. Yeah, kindly observe here. One more small example I am taking. One more small example to you to conclude this one. It is one system simply. We are thinking about fault only. Thinking about fault only. A, B, C. Three conductors. Outgoing wires open. It's open. Exactly. A, B, C, all the three are open. Not carrying any current right now. Not carrying any current right now. Just listen. Just listen. YXD means I said already steady state. Load analysis, steady state analysis, right? Load analysis, it's not fault analysis. Yeah. Come to this diagram. You have phase A to ground fault. A to ground fault. Phase A to ground fault we have there. You have to replace with 3 R load. Same analysis, no change, Mr. Anonymous attendee. Same analysis. 3 times of R load you should keep in the circuit. What type of fault is this? Anybody please tell me? Just it's a simple thing to answer what I feel. We have a system, 3 wires are outgoing. Conductor A was grounded, B and C are like this. What type of fault is this? Single line to ground fault. Any different name you give for this? Any different name? Any different name? Any other? Unsymmetrical is okay. Any other different name? Can I say it's a 2 open conductor fault? Can I call this same as 2 open conductors? Yes, my interest is very simple to tell you actually. My interest is to tell you only one conductor is carrying current, the remaining 2 conductors are not carrying current. If that is the case, it is an equivalent to 2 open conductor fault, but you don't call it. You don't call that as 2 open conductor fault in the study, but it is an equivalent. It's an equivalent to 2 open conductor fault. Means if somebody asks you this type of question, if you have a 2 open conductor fault, what is the relationship between sequence currents? What will be the relationship between sequence currents? All the 3 sequence currents will be equal because 2 currents are 0, only 1 current is existing. I don't know whether you have understood this or not. An equivalent to 2 open conductor fault. 2 open conductor fault. Okay, so in this 2 open conductor fault also, all the 3 sequence currents will be equal. Just for simple, what we call objective examination purpose only, I am saying this statement. So my interest is not make you to study the open conductor faults, just for the examination purpose. We have studied much thing up to this point. These conclusions, what I am making, might be helpful to you in the examinations. Yeah, next. This is the end of the single line to ground fault. All the aspects we have studied till now. Next, we will be moving to the double line fault. We will be moving to the double line fault. Have a break for 15 minutes. 15 minutes break. So after this break, we will be continuing with double line fault. Mostly today we will finish the double line fault as well as double line to ground fault. Some problems on that. Right? If possible, we will start a 3-phase fault also, because it will take very less time to discuss all these things, remaining things. Yeah. I have resumed the audio video on screen. Please kindly confirm. Audio video on screen once. So the next heading, what I'm going to consider here is double line fault, or you can say line to line fault. Yeah. Double line fault, or you can say line to line fault, or you can call phase to phase fault also. Phase to phase fault also you can call this. See, in the similar way, first I'm going to take a no load operating alternator, and we do fault analysis on that alternator first, and then we will extend to calculate line to line fault current at any place in the system. Okay, yeah. So I'm showing here a no load operating alternator. So phase A, phase B, phase C, phases ABC, neutral. So these are outgoing terminals. Okay, ABC outgoing terminals. This neutral is connected to ground with an impedance of Zn. Neutral was connected to ground with an impedance of Zn. And this is internal EMF of phase A, phase B, phase C. Terminal voltages we are denoting with VA, VB, VC here. Terminal voltages VA, VB, VC. Outgoing currents you have IA, IB, IC. IA, IB, IC. First I will say pre-fault condition. It's a no load operation. Pre-fault condition. Pre-fault condition. No load operation as it is of a previous one. No load means IA, IB, IC currents are 0. Phase A current is 0. Phase B current is 0. Phase C current also 0. And terminal voltages are nothing but internal voltages only. EA, EB, EC, whatever the voltage here, that itself will be the terminal voltages, which are balanced voltages here. See, if these voltages are balanced in the symmetrical components, you will get only positive sequence component here, only positive sequence component. And the negative and zero sequence components will be 0. As a pre-fault system is balanced, you get only positive sequence component of voltage. Positive sequence component of voltage. Okay, next thing. Fault we are going to take LL fault. Either you can take this LL fault on AB conductors or BC conductors, or you can take on CA conductors. Anyone you can take. But for easiness in analysis, I will take on BC conductors. BC conductors. Later on, I will tell you what you have to do if there is a line-to-line fault on AB, or if you have a line-to-line fault on CA. Okay? Yeah. So let's move. Double line fault, LL fault on BC conductors. On BC conductors. LL fault on BC conductors. Means this B and C are short circuited with zero impedance. First of all, we are discussing with respect to solid fault. With respect to solid fault only, we are discussing zero impedance. ZF is equals to 0. Next, first tell me, we have to think about voltages. Think about the voltages after the occurrence of fault. What is VA value? Non-zero. It's not connected to ground or not connected to any terminal. So phase A voltage will be non-zero. Okay. What about B? Not connected to ground. Nah? B is not connected to ground. So VB also non-zero. What about C? Not connected to ground. So VC also non-zero. But one relation what you can get here is, as B are shorted together, VB and VC values will be identical. So first I will write voltages here. VA non-zero, VB non-zero, VC also non-zero, but you can say phase B and phase C voltages are equal. Phase B and phase C voltages are equal. Next, let's look at currents now. Let's look at currents. This IA current will be as it is 0. IA current is 0. B current will be non-zero. C current will be non-zero. That we can write for currents here. Phase A current 0 because it is open. B current, we have a path for the current flow. We have a closed path for the current flow. B will carry some current. C also will carry some current. But if you apply KCL at this node, let us see. If you apply KCL at this node, IB current is coming down, IC current is going in. Means to this node, both currents are entering now. B and C currents are entering and it is not leaving out. Means definitely IB plus IC must be equals to 0. Phase B plus phase C currents must be equals to 0. Means we can get phase C current as negative of the phase B current. Phase C current as negative of the phase B current. I think all of you getting this. Clear? Phase C current will be negative of the phase B current. Next thing. See, what is a fault current in this circuit? Means simply current flowing in this fault element. Current flowing in the fault element, that itself is a fault current. That may be equals to phase B current. So IF is equals to IB, you can call. Fault current is nothing but phase B current. Okay, next thing. Now, as the system is unbalanced, we can say system is unbalanced. System is in unbalanced state. Now you convert these currents and voltages into symmetrical components. First take voltages. Symmetrical components for voltages. Symmetrical components of voltages, you can say. Symmetrical components of voltages. So you write simply that matrix VA0, VA1, VA2 matrix, sequence voltages matrix is equals to what you get? 1 by 3, 1, 1, 1, 1 alpha, alpha square, 1 alpha square alpha. This multiplied with voltages we have VA, VB, VC. Voltage you have like VA, VB, VC. And already you know VA is non-zero. You should not disturb that VA. VB and VC are equal. You keep as it is here VB and this VC you replace with VB because VB and VC are equal, we are seeing. You go with matrix multiplication. What is VA0? I'll write in the next slide. What's VA0? 1 by 3. Observe here. VA plus VB plus VB. So VA plus 2VB. It is phase A voltage. Sorry, zero sequence voltage. Positive sequence. 1 by 3 into, observe, VA plus alpha VB plus alpha square VB again. So VA plus alpha VB plus alpha square VB. So you can write 1 by 3 VA plus, you take VB common, alpha plus alpha square. How much is it? Alpha plus alpha square number? -1. Alpha plus alpha square is -1. So you can write this as 1 by 3 VA minus VB. 1 by 3 VA minus VB. That is a positive sequence voltage. And then negative sequence voltage VA2, if you write from matrix, 1 by 3, observe here, 1 by 3. VA plus alpha square VB plus alpha VB. 1 by 3. VA plus alpha square VB plus alpha VB. Again, if you manipulate this, finally you can get this as 1 by 3 VA minus VB. 1 by 3 VA minus VB you can get. Means what is the conclusion you can get from this now? What is the conclusion you can get? Anybody please tell me. Any observation you can get from sequence voltages here? Any observation you can consider? See, obviously, you can observe that positive and negative sequence post-fault voltages are exactly equal. Positive and negative sequence post-fault voltages are exactly equal. But we are not getting any relation between that VA0 and VA1, VA2. So simply you confine to this condition only at present situation. If there is anything needed further, if there is any more relation needed further with respect to zero sequence voltage, we will look into it. We are unable to get relationship between the zero sequence voltage to positive and negative sequence voltage right now. So simply I am saying VA1 equals to VA2 at present. Okay, let me write sequence currents. Sequence currents. Symmetrical components for currents. Symmetrical components for currents. Okay, symmetrical components for currents. You write that matrix IA0, IA1, IA2 matrix. Yeah, so it is equals to 1 by 3, 1 by 3, 1, 1, 1, 1 alpha, alpha square, 1 alpha square, alpha. This multiplied to, we have IA, IB, IC currents. Phase A current will be 0. Phase A current 0. B current I will keep as it is. I don't change it. B current I will keep as it is. C current will be minus I. That's what I have written earlier, right? IC is equals to minus IB, something like this. What is IN0 current from this? Anybody you tell me from this matrix multiplication? 1/3 0 plus IB minus IB. So it will be equals to 0. We don't have any zero sequence current here. We don't have any zero sequence currents. Yeah, I'm showing previous slide. Please complete it if you are still writing. Please complete this one quickly. Previous slide. Fine. What is IA1 current here? Anybody? IA1 current? 1/3. What you can get? 0 alpha IB minus alpha square IB again. So you can take that IB common. So IB by 3 into alpha minus alpha square. IB by 3 into alpha minus alpha square. What is that value? Alpha minus alpha square. Alpha minus alpha square. If you take, it will be J root 3. Root 3 at an angle plus 90 degree. Else you can say that as J root 3. So IA1 current is equals to IB by 3 into J root 3. So it will be J IB by root 3. J IB by root 3. It is a positive sequence current, IA1. Positive sequence current, IA1. J IB by root 3. Next one. Negative sequence current, IA2. 1 by 3. 0 plus alpha square IB minus alpha IB. Negative sequence current, IA2 equals to 1 by 3. 0 plus alpha square IB minus alpha IB. Okay, so you can take this IB common, so you get IB by 3. Here it is alpha square minus alpha. What is that alpha square minus alpha? Minus J root 3. You have to do that. Minus J root 3. How in the sense I discussed in the phase shift operator calculations already. So I said you many times, but still I am saying you again and again. Without having a revision of the previous classes, understanding the next class will be a bit difficult only. Okay, unless otherwise, if you have studied this subject a bit thoroughly. Okay, if you have not studied this subject thoroughly earlier, better have a revision for each and every day. Okay, fine. So I'll write this IA2 here, IA2 from this, and you have minus J IB by root 3. Minus J IB by root 3. So it's a current IA2. Then what is the relationship you can obtain between the currents? IA0, IA1, IA2 currents. What will be that relation? Very simple. We don't have any zero sequence current. IA naught is equals to 0. Positive and negative sequence current summation equals to 0. If you take up IA1 plus IA2, that will be 0, right? So positive and negative sequence currents, else, right? IA2 equals to minus IA1. Negative sequence current equals to negative of the positive sequence current. Not only that, IA1 plus IA2 value is equals to 0. So these are the relations you are getting with respect to currents here. These are the relations you are getting with respect to currents. Okay. Next thing. So if you have done, I will move ahead to the next slide to draw the sequence networks. After drawing the sequence networks, we should give connections among the sequence networks by following the relations. Okay. So I'm drawing the sequence networks here. Sequence networks. First, positive sequence network. We have only alternator. That's it. We have only alternator. So that alternator might be having positive, negative, and zero sequence impedances like Z1 per phase, Z2 per phase, Z0 per phase. Okay. So I'll say first the positive sequence network of alternator with respect to location of fault. With respect to location of fault. Z1. This is a pre-fault voltage. EA1, and this was neutral. So EA1 is going to be called as a pre-fault voltage VPF. And this terminal voltage I am showing as a VA1 here, and current flow in this circuit is IA1, and this is with respect to the fault location F. This is with respect to the fault location F. That's a positive sequence network. Okay. Negative sequence network with respect to the fault location, simply like this. It's a neutral, showing it is plus minus negative sequence voltage VA2, and this is negative sequence impedance, and this current I am showing as IA2, and this is a fault location. And zero sequence network also you draw in similar way. Up to neutral, you can keep Z0, and then neutral to ground, we have to keep 3 times of Zn. Neutral to ground, you have to keep 3 times of Zn. Okay, so this is the terminal zero sequence voltage. I am calling it is VA0, and here that current is IA0. And this is a fault location F, I can say. This is a fault location F. Yeah, so you please kindly observe. Here. You have to follow the relations, right? First relation, you have to follow voltage relation. What that voltage relation we have? VA1, VA2 are equal. What do you mean by that? VA1, VA2 are equal? What do you mean by VA1, VA2 are equal? What do you mean by VA1, VA2 are equal? I can say simply positive and negative sequence networks will come in parallel. Positive and negative sequence circuits will come in parallel. So that statement you can make. Positive and negative sequence networks will be connected in parallel. So I will join these two. The fault points has to be joined actually, because there is a point with respect to which you constructed the positive sequence network as well as a negative sequence network. That's it. Okay. We don't know about VA0 earlier also. Let's move further. Currents relation. IA0 value 0. Simply, I should say that this zero sequence current is 0 in the sense, zero sequence circuit must be in the open mode. Zero sequence circuit must be in the open mode such that you should not have any current circulation in the zero sequence network. Okay, fine. Next one. IA1 plus IA2 equals to 0. Observe here, by standing at this node, IA1 current is coming in this direction. IA2 current is coming in this direction. And if you stand here, IA1, IA2 both are joined to that point. There is no outgoing current. So IA1 plus IA2 will be equals to 0 automatically. IA1 plus IA2 will be equals to 0 automatically. Okay. That's it. That was already satisfied if you connect the two sequence networks in parallel. Okay. So immediately in the next step, we will go with network analysis. Network analysis means first I will find out the sequence currents from this one, sequence currents from this one, convert them into ABC currents. Then we will think about the voltages. Okay. So first network analysis, finding out the sequence currents from network analysis. Sequence currents from network analysis. Simple. What is positive sequence current IA1? What is positive sequence current IA1? See, once after giving this connection, you redraw that network according to your view. You redraw that network according to your view. Means I will say simply, it is a positive sequence impedance Z1 with an EMF as EA1 here, EA1, and this is a negative sequence impedance. I am showing it is Z2, and this is that current IA1, I can say. So what is it current IA1 now? We have only one voltage source in the whole network, that is EA1. We have only one voltage source in the whole network, that is EA1. By how is that Z1, Z2 are connected now? Series. Z1, Z2 are connected in series. So I can say Z1 plus Z2. That's it. That's the positive sequence current. And what is the negative sequence current? Negative sequence current is simply opposite to the positive sequence current. So IA2 is equals to minus IA1, already we have mentioned. And zero sequence current is obviously zero because this circuit is open already. This we got from original sequence currents itself. Without looking at the sequence networks, you can see. You can say that zero sequence current is equal to 0. After getting these currents, convert these currents into ABC currents. Convert these currents into ABC. So I'll write here ABC currents. ABC currents. First, what is IA current? IA. See, if you don't know anything, just use a symmetrical component formula that will tell you. Use the symmetrical component formula that will tell you. IA formula is what? IA0 plus IA1 plus IA2. IA0 value 0, IA1, IA2 are 1 and opposite. So phase A current is 0. That's it. Phase A current is equals to 0. And what is phase B current? Phase B current. IA0 plus alpha square IA1 plus alpha IA2. Phase B current is IA0 plus alpha square IA1 plus alpha into IA2. Okay. IA0 value 0. Alpha square into IA1 you keep here. In place of IA2, you keep minus IA1. You keep minus IA1 in place of IA2. And you take IA1 common, alpha square minus alpha. IA1 you take common, so it will be alpha square minus alpha. So in the next slide, I will what we call simplify this one. So phase B current is equals to IA1 into what is that alpha square minus alpha? Alpha square minus alpha, in the sense it will be minus J root 3. Minus J root 3. So phase B current is equals to minus J root 3 times of IA1 current. Minus J root 3 times of IA1 current. Already you have IA1 current formula, right? Already we have IA1 current formula. So I will substitute that here. So it is minus J root 3 pre-fault voltage EA1 by Z1 plus Z2. Z1 plus Z2. This will be the phase B current. Phase B current. And what is phase C current? What is phase C current? You can write directly it is negative of the phase B current from original ABC network. Else you write with symmetrical components also, you will get the same. Okay, so you get this one minus IB. So this current is plus J root 3 times of EA1 by positive sequence impedance plus negative sequence impedance. Positive sequence impedance plus negative sequence impedance. These are the phase currents ABC. IA current is 0. B current and C currents are equal in magnitude but opposite in sign. Equal in magnitude but opposite in sign. Okay, done. Next thing, let's look at the voltages. What is fault current here? What is fault current? From this diagram you can observe. What is fault current? Fault current is nothing but phase B current only. Fault current is nothing but the phase B current itself. So this phase B current what we have itself is a fault current. Itself is a fault current. Okay, next thing. Sequence voltages I will write. Sequence voltages. Simple. Sequence voltages. Sequence voltages. What is VA1? Just look at this circuit analysis. What is VA1 here? VA1. EA1 minus IA1 general thing. Right? So it is EA1 minus IA1 into Z1. Negative sequence voltage VA2 is minus IA2 into Z2. Negative sequence voltage VA2 equals to minus IA2 into Z2. Negative sequence voltage. What is zero sequence voltage? Anybody? Can you please tell me? What is zero sequence voltage? What is zero sequence voltage? Just look at the circuit. See, it is minus IA0 into Z0 plus 3Zn. That's the formula actually. As IA0 is 0, 0 into Z0 plus 3Zn is equals to 0. So it is minus IA0 multiplied with Z0 plus 3Zn value. IA0 value was 0 into this 0 sequence equivalent. So it will be obviously comes to be 0. Zero sequence voltage will be equals to 0. Clear? Next, you find out the phase voltages. How come it is neutral voltage? Satish? How come it is neutral voltage? Please tell me how it is. Yeah. Next, let's move to the next slide. To take up phase voltages, ABC voltages here. ABC voltages. ABC voltages. What is VA? VA0 plus VA1 plus VA2. VA0 plus VA1 plus VA2. So already you know VA0 value was 0. So it is VA1, VA2. Summation will come to be 2 VA1. It will be 2 times of VA1. Okay, because you know this VA0 value 0, VA2 value is equals to VA1. So it will come like that. What is phase B voltage? Anybody? What is that phase B voltage? So you can write VA0 plus alpha square VA1 plus alpha into VA2, like this you write. And you know VA0 value 0, it is alpha square VA1. You replace this VA2 with VA1 like this. And you take VA1 common. And you get here alpha square plus alpha. Alpha square plus alpha is minus 1. So it is minus VA1. Phase B voltage equals to negative of the positive sequence voltage. Phase B voltage is equals to negative of positive sequence voltage. Okay, next, what is phase C voltage? VA0 plus alpha into VA1 plus alpha square VA2. So from this VA0 is 0, again you replace the things. You can get alpha plus alpha square into VA1. And ultimately phase C voltage also comes to be minus VA1. Phase C voltage also comes to be minus VA1. Like this we'll have the voltages. VB and VC are equal. Already you know from basic network analysis only. Okay. VA1 is equals to VA2. Already we got that from relation of symmetrical components itself. VA1, VA2 are equal. That's why you connected them in parallel, right? That's why you connected them in parallel. Okay, see, for example, if that neutral is not grounded, then how is this situation? How will be these calculations? Look at this one. Look at this. Just I'm moving back to this one. If this neutral is not connected to ground, You no need to write this. You no need to write this. I am copying these things to the last slide, and I will be showing the things. You no need to write this. No need to write this. Just you listen. Anyhow, I will be sending this notes to you now. So just you listen what I am saying. And whatever you have to note down, I will tell you. So I'll say LL fault on ungrounded neutral alternator. LL fault on ungrounded neutral system. Neutral system. Okay. So I am showing this three-phase alternator. And this neutral is not connected to ground now. Neutral was isolated from ground. Right? Like this. Zn is equals to infinite, you can say. Zn is equals to infinite. Do you have any change in the relations what you have taken earlier? Do you have any change in the relations what you have taken earlier? I need your response. Please tell me. VA is unknown. VA is unknown. VB and VC are equal. B and C currents are non-zero. IB plus IC equals 0. IA equals 0. Then how will be the sequence networks connection? Positive, negative sequence circuits will be in parallel. And you get the currents as it is, no change. Currents you are going to get as it is, no change in the currents. Okay? Yeah, if you want, I will copy the symmetrical component, sequence networks also in the similar way. Like this, you will get the sequence networks. Okay, so I'm showing those sequence networks. I'll show in the next slide better. Showing in the next slide. These are the sequence networks for you. But only one change, what we are going to expect here is this 3Zn value, what we are saying now, that will be resulting into infinite. That will be resulting into infinite. You don't get any change in the currents calculation. Currents will be as it is. We don't have any change. Okay? Yeah, you write if you want, no change in currents. No change in currents as compared to previous case, not compared to pre-fault condition. Okay, no change in current equations. Current equations. What about VA1 here? Sequence voltage VA1, EA1 minus IA1 Z1, same number. Whatever the VA1 we calculated in the previous case, same number you have to take here. What is VA2? Minus IA2 Z2, same as the previous one. But you have to identify this change in the VA0, zero sequence voltage. Okay? Yeah. So I'll show in the next slide. Next slide. Positive sequence voltage is EA1 minus IA1 Z1, same as previous number. VA2 is equals to minus IA2 into Z2, same as previous number. What is zero sequence voltage? What is zero sequence voltage? Minus IA0 into Z0 plus infinite. Minus IA0 into Z0 plus 3Zn. 3Zn means it is infinite. Minus IA0 into Z0 plus 3Zn. 3Zn means infinite. See, IA0 value was 0, okay, and this Z0 plus infinite is infinite, right? Z0 plus infinite is equals to infinite. Clear? Z0 plus infinite is equals to infinite. So if that's the case, 0 into infinite we are getting, I can say it is indeterminate. 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 Right? Means what you can say from this? What you can say from this one? Anybody? As VA0 is indeterminate for you, definitely it is not possible to find what is the phase A voltage. Means because it is VA1 plus VA2 plus VA0. I know VA1, VA2 clearly, but I don't know VA0, right? So we can't find phase A voltage. So definitely you can't find phase B voltage, and you can't find the phase C voltage also. So in this particular case, phase voltages, so-called VA, VB, VC are indeterminate. Phase voltages are indeterminate. Okay, so I can write here as VA0 is indeterminate. VA0 is indeterminate. the phase voltages in bracket VA, VB, VC are indeterminate. Indeterminate. Okay, phase voltages are indeterminate. What about line to line voltages? Line to line voltages. If the phase voltages are indeterminate, what will happen to line to line voltages? VAB, VBC, VCA. VAB, VBC, VCA. What will happen? Anybody? Tell me please. What is VAB actually? VAB. I'm doing some rough work here. Kindly observe. VAB means, you know, it is VA minus VB. What is VA? VA naught plus alpha, sorry. VA1 plus VA2. What is VB? VA naught plus alpha square VA1 plus alpha VA2. Means what you can observe now. VA naught will be cancelled out. VA naught will be cancelled out. And this VA minus VB is coming in terms of only VA1 and VA2, right? It's coming in terms of VA1 and VA2. Similarly, if you take VBC also, there again VA naught cancelled. Next you take VCA, VA naught will be cancelled. Means what you can observe is line to line voltages we can determine. Even though phase voltages are indeterminate, but still we are capable to find out the line to line voltages in this case. Okay, so I can write, but still line to line voltages in bracket VAB, VBC, VCA can be determined. But line to line voltages, you know, VAB, VBC, VCA can be determined. So I think all of you getting my point, what I said. Because VA naught value, what you have in A and B will be cancelled in the VAB voltage. In the VBC voltage also, VA naught cancelled out. In the VCA voltage also, VA naught will be cancelled out. Yeah. Next thing. Just answer to the statements what I am saying you further. Answer to the statements what I am saying you further. Just you have to tell true or false here. True or false. Just listen. During LL fault, double line fault, LL fault, phase voltages can't be determined always. Can't be determined always. Is it the statement true or false? That's it. I'm asking you a very simple thing. Whether this statement what I have given on the screen, is it true or false? False. How it is true? It's a false statement, right? False. Just listen, look at the statement. Particularly in the examinations of UPSC, maybe in the GATE also, these terms are very costly. Always. Okay. Only. Always. Only. This type of reasoning terms are very costly. Look here. During LL fault, phase voltages can't be determined always. Is it true? No. Because if the neutral is grounded, we are capable to determine VA, VB, VC. But if it is ungrounded neutral, we can find out the values of we can't find out the VA, VB, VC. So it's a false statement we have to call. It's a false statement. It's not correct. Okay. Next statement I am saying. During LL fault, one more term I have to add. Can't be determined. Mathematically, I have to add that word for you. Mathematically, because we are doing pure mathematical study here. That's why I'll say mathematically always. Okay. Next one. During LL fault, the line-to-line voltages can be determined mathematically determined. Determined. Always. Always. Is it true or false? This statement you tell me. During line-to-line fault, the line-to-line voltages can be determined always, always. Yes or no? Yes. Whether the neutral is grounded or ungrounded. Nikita, what happened? Huh? Gurudatta. See the statement, Gurudatta. Till now, whatever I have discussed, that only I am asking you. Nothing, nothing. It will be a true statement. We can determine the line-to-line voltages all the time, irrespective of the value of zero sequence voltage. Whether the zero sequence voltage is determinate or indeterminate, it's no issue for me because the zero sequence voltage will be cancelled. Is it a grounded neutral or ungrounded neutral? Any case, we are capable to find out this. So this statement will be definitely true. This statement will be definitely true. Okay. Yeah, I am asking one other statement. During LL fault, phase voltages can be determined always. During LL fault, phase voltages can be determined mathematically always. Is it true or false? It will be again false. That statement will be again false. Okay. Yeah. Fine. Good. Okay. This is one question we used to get generally. Okay, you are unable to determine this value mathematically, particularly in this case of ungrounded neutral. You keep these statements aside. Keep these statements in a box and keep this one aside. Okay. Yeah. Next. Listen, please. Next, I am moving to the next slide. I am continuing with the ungrounded case only. Ungrounded case. Else, I can add one more slide here and I can take that comment. Ungrounded case only I am discussing now in a continuation. Look here. See, you are saying that zero sequence voltage is indeterminate, but one thing what I can observe from the circuit, is that whatever the neutral voltage you have here, that will be same as a zero sequence voltage. Is it true or false? Zero sequence voltage and neutral voltage both are equal. Just from circuit analysis. Just from this circuit analysis, we can say VA0 and VN values are equal. Means I can say, okay, mathematically you are saying it is a 0 into infinite, it is indeterminate. That's okay for me. But can you measure that voltage practically? See, measuring zero sequence voltage may not be possible. Look at my words, what I am saying. Look at my words. Measuring zero sequence voltage may not be possible, but you can measure the neutral voltage. Fortunately, that neutral voltage and zero sequence voltage are same in this case. Okay, so we will try to measure the neutral voltage, then we will make that comment in a practical system. Okay, yeah. So let's take practically. Practically, I'll say. Yeah, you tell me how to measure the neutral voltage practically. How to measure the neutral voltage practically? Just by using a voltmeter, which I can say. Okay, so let me copy this diagram. This diagram I am copying. Okay. So what I'll do is, in this case, I will connect one voltmeter. I'll connect one voltmeter between this neutral and ground. Connecting one voltmeter between that neutral and ground like this. Okay. And after connecting that voltmeter between that neutral and ground, how will be your zero sequence network looks? How that zero sequence network looks for you? This is A. Okay, you tell me how much is that voltage shown by voltmeter? Anybody? How much will be the voltage shown by voltmeter? We have connected one voltmeter between neutral and ground. How much will be the voltage shown by voltmeter? In your expectation. In your expectation. It may be 0. We will be expecting that as 0. Okay, I'll tell you. I'm drawing the zero sequence network. A to neutral, we should keep zero sequence impedance of generator. Neutral to ground, how much we have to keep? Neutral to ground, we have to keep 3 times of the voltmeter impedance. 3 times of voltmeter impedance. 3 times of voltmeter impedance we have to keep. And this is ground. Okay. And this is plus minus your zero sequence voltage. And you know, this zero sequence current is 0 that we are getting from basic symmetrical components theory itself. From basic symmetrical component theory itself, you know, zero sequence current is 0. Then what will happen to the value of VA0 here? Anybody? VA0 minus IA0 into Z0 plus 3ZB. How much is voltmeter impedance in your view? How much is the voltmeter impedance in your view? It may be in the order of kilo ohms. It may be in the order of kilo ohms. Kilo ohms in the sense, whatever it is, kilo ohms or mega ohms, whatever it is. 0 into some finite number, right? 0 into some finite number that will result into 0, obviously. That will result into 0. It may be in mega ohms or kilo ohms, doesn't matter. 0 into finite number is 0. So what's the comment we have to make from this now? What's the comment you have to make from this? Tell me, please. Tell me, please. So practically speaking, neutral voltage is equals to 0 as well as zero sequence voltage is also equals to 0. So practically speaking, whether the neutral is grounded or ungrounded, for a line-to-line fault, zero sequence voltage will be equals to 0. Zero sequence voltage will be equals to 0. If that is the case, practically speaking, we are capable to find phase voltages as well as we are capable to find line-to-line voltage also. Yeah. I don't know whether you have understood this statement or not. Have you understood this one? I'm writing in the next slide. Yeah. Okay. Yeah, tell me. That's it. You can say just we have connected a voltmeter. Okay, fine. So 0 into finite number, it is coming as 0 after connecting the voltmeter. So I can say VA0 equals to 0 simply, whether this neutral is connected to ground or not connected to ground. So finally, what you can say is, practically speaking, always VA0 is equals to 0 during LL fault. During LL fault, VA0 is equals 0 during LL fault. Either or. For the case of grounded neutral, or ungrounded neutral. Grounded neutral or ungrounded neutral. For the case of grounded neutral or ungrounded neutral. That implies phase voltages VA, VB, VC can be determined practically, always practically. Practically, we can determine these voltages always. That's the theoretical case which we said Sai Ganesh. Sai Ganesh, that's a theoretical case what we said. Now, why INR is 0? Please cross-check the things, anonymous attendee. Why you are asking me this question again? Why zero sequence current is 0? That we said long back. Zero sequence current is 0 in the LL fault. Again, you are asking me same thing. Please cross-check it kindly. Okay. Yeah. So, these are the things you have to understand. But in the examination point of view, if it's a theory question, please stick to these statements, theoretical statements or mathematical statements. What I said, you have to give your answer in the way of the mathematical statements what I have made. But if it's a numerical problem given to you, if it's a numerical problem given to you, don't bother about the zero sequence voltage value, whether the neutral is grounded or ungrounded. You take the zero sequence voltage value directly 0 and you calculate only VA1 and VA2. Sum of the two is nothing but phase A voltage. That's it. Okay. Yeah. So let's move ahead. So next I will take up the double line fault with a fault impedance of ZF. LL fault with the fault impedance in the sense ZF not equals to 0. LL fault with fault impedance means we can say ZF not equals to 0. Same diagram I will repeat now. We have an alternator like this, right? So this neutral is connected to ground, I will say, with an impedance of Zn. And these are the outcoming terminals, you know, ABC outcoming terminals. And terminal voltages are VA, VB, VC. And the currents flowing out will be IA, IB, IC. And internal EMFs you have as EA, EB, EC. Internal EMFs you have as EA, EB, EC. Pre-fault conditions are as it is of previous. Means currents are 0. First I'll take currents are 0. And terminal voltages are nothing but internal voltage only. That we will copy. Pre-fault conditions are as it is. Let me copy those conditions once. Yeah, this one. This is a pre-fault state. If you want to write, else you can skip, no issue. Okay, right. Next. I'll take a double line fault between B and C conductors. Double line fault between B and C conductors with a fault impedance. So I'll keep some fault impedance between these two conductors. This is ZF impedance I am showing, fault impedance as ZF. So next I'll say LL fault with the fault impedance not equals to 0. Fault impedance not equals to 0. On BC conductors, of course. On B and C conductors. Next thing. Now you write the conditions after the fault has been occurred. You know, VA non-zero because it is open. It's in the open mode. VA is non-zero. What about VB and VC? Also non-zero. VB non-zero value and VC also non-zero value. But what you can confirm here is, but that B to C voltage gap means VB minus VC. This is VB and this is VC. And we have some current flow in this branch, which is nothing but fault current you are feeling. That fault current is nothing but phase B current. That current we are saying as fault current, that fault current is nothing but phase B current. Phase B current. Okay, see, you observe now. So VB minus VC is equals to IF into ZF, else you can say IB into ZF. Anything you can write. It is IB into ZF. IB into ZF, or you can call IF into ZF. Okay, we will keep that one. Next, what about the currents here? Phase A current 0 because it's open. Phase A was open, phase A current 0. What about phase B current? Non-zero. phase C current, again non-zero. But one relation what you can suggest here is, by reaching to this node, IB is entering, IC is entering, sum of the two currents, 0. So IB plus IC current will be equals to 0. You can call this as IB plus IC is equals to 0. Phase B plus phase C currents, that will be equals to 0. Okay. Yeah, next thing. See, if you, or else you say this also, IC equals to minus Q. See, if you compare these actual ABC voltage and currents with ZF equals to 0 case, which conditions are same? Earlier we have written VB equals to VC. But here VB and VC are unequal. If you look at the currents in the earlier case, also, IB plus IC equals 0, IC equals to minus IB. What you can experience? Which relations are same? Current relations are same. Only voltages are different. Okay. So in that view, if you convert these currents into symmetrical components, what we can comment here is zero sequence current will be equals to 0. Observe there. Zero sequence current will be 0. Summation of positive and negative sequence currents will be also equals to 0. Zero sequence current equals to 0, as well as IA1 plus IA2. That value is also equals to 0. And what is fault current you are feeling? Phase B current. Fault current is nothing but phase B current. How much is that? That will be minus J root 3 times of positive sequence current. Equation only have written. By following this relation, if you find out the phase B current, it will come to be minus J root 3 times of IA1. But IA1 in this case may not be same as a previous one. Number is not same. Relation is same. Equation wise it's same. Number may not be same. That's it. Okay. Now we should find out the relation between the voltages from this one. Earlier case, VA1, VA2 are exactly equal. Now we have to get the relationship between VA1, VA2 by following this VB minus VC equal to IB into ZF. Okay, let's move to the next slide. As we know already, phase B voltage minus phase C voltage equals to IB into ZF. You write these things in symmetrical components form. VB in symmetrical components, VA naught, alpha square VA1, alpha VA2 minus, what is phase C? VA naught, alpha into VA1, alpha square VA2. Okay, equal to, what is phase B current? Minus J root 3 IA1. Be clear about this term. IB current already we have written in terms of symmetrical components. That will be minus J root 3 IA1 into fault impedance is Z. Into fault impedance is equals to Z. Okay, now VA0 is cancelled out and you can take VA1 common. You get alpha square minus alpha here. Plus you take VA2 common, alpha minus alpha square. So it is minus J root 3 times of IA1 into Z. And you can take alpha square minus alpha out from this. Alpha square minus alpha, if you take out, you will get here VA1 minus VA2. You get here VA1 minus VA2. So it is minus J root 3 times of positive sequence current into Z. Positive sequence current into Z. What is alpha square minus alpha? Calculate that. Alpha square minus alpha, minus J root 3. So in the next slide, minus J root 3 times VA1 minus VA2 minus J root 3 times VA1 minus VA2 equals to minus J root 3 times IA1 into fault impedance. So that minus J root 3, you can move it off and you can get VA1 minus VA2 is equals to IA1 into ZF. IA1 into ZF. This is a relation what we got. Have a cross check. Have a cross check after getting this relation. If ZF equals to 0, what is the condition between symmetrical components of voltages? VA1 equals to VA2, na? And if you keep ZF equals to 0 here, are you getting the same? Of course. Yeah, cross check I'm saying, cross check. Okay, don't confuse. Don't confuse. Okay, now you apply this, you draw the sequence networks and give the connections and conclude the thing. Okay, sequence networks, we are going to draw. Sequence networks, we are going to draw. First, positive sequence network. Like this, we can show neutral. And this is plus minus VA1 and this current is IA1 we have. Z1 and this is a pre-fault voltage value EA1. And negative sequence network Z2 and this is neutral. And this voltage is VA2 and this current you have as IA2. And zero sequence network up to neutral we should keep Z0, neutral to ground we have 3 times of Zn. Okay, so this is plus minus VA0 and this current it is IA0. Yeah, I forgot to tell one thing to you earlier, maybe in case of ungrounded case. Ungrounded case, just listen to me, just listen to my words. I'm moving to ungrounded case. Little I will tell and I will come back to the discussion what I'm doing. Just look here. See, it's an ungrounded case. We said VA0 is indeterminate practically, theoretically or mathematically, but still line-to-line voltages are determined, and we said these statements. And we have moved into practical case. We kept a voltmeter here. That's okay. And we finally confirmed that it is 0. VA0 value 0. For example, if you don't connect the voltmeter, what will happen? For example, in this case, if you don't connect the voltmeter, what will happen? If you don't connect the voltmeter, what will happen? Can I say VA0 0? Even though if you don't connect the voltmeter, can I say VA0 equals 0? Ungrounded case. In the ungrounded case, I am saying. In the ungrounded case, even though you don't connect the voltmeter, can we say VA0 0? Yes, yes. There is some technique to say that. Practically speaking, between this neutral wire and ground, between the neutral terminal and ground, there is some air gap. Some air gap we have between that neutral and ground, right? And neutral is a conducting body, ground is also a conducting body. There is a formation of capacitance between these two, na? Air capacitance. Air capacitance is going to be formed between these two. Okay, that we call sometimes as stray capacitance. Stray capacitance. Okay, that capacitance value may be very low. Impedance is in the order of mega ohms. Whatever it may be, it's not infinite, right? It's a finite number. If it's a finite number, 3 times of that capacitor impedance will come in between that neutral and ground. As a whole number is finite, you can say zero sequence voltage is equals to 0. All of you getting my point? So I'll say there exists. You write this point after this diagram. After this diagram, we can write this. There exists a stray capacitance between neutral and ground. There exists a stray capacitance between neutral and ground, and its impedance its impedance may be very large, may be very, very large, but still finite. Still it is finite. That implies the overall zero sequence impedance is a finite number. Zero sequence impedance is finite number. Okay, so that implies VA naught is equals to 0 into finite value. 0 into finite value. So it will be obviously equals to 0. It will be equals to 0 practically. We are saying this one practically. So if you want, you can draw that zero sequence network also like this. Up to neutral, you can keep Z0, and then neutral to ground, you keep 3 times of capacitor impedance. Jets. 3 times of the capacitor impedance. Jets. Okay, this current is 0. Obviously, this overall voltage, what we are saying, zero sequence voltage, also 0 practically. I think all of you getting this one. Simple. Between neutral and ground, there will be an air gap. Neutral means a star connection junction of your winding. Okay, between that point and ground, there is some air gap. Neutral point is a conductor. Ground is also a conductor. Between two conductors, we have some air gap. Definitely, capacitance is going to be formed between those two. That capacitance is going to be called as stray capacitance. Okay, that capacitance is going to be called as stray capacitance. Yeah, please complete this one. I will continue with the with fault case. All these things are absence of voltmeter. If you don't connect voltmeter, how you have to say VA naught equals to 0 means this is one way of saying it. Without voltmeter, practically there exists a stray capacitance. Yeah, I know what's the time now. No need to remind. Yeah, so let's move with this thing. And here in the sequence networks, you have to give connection, as I said. VA1 minus VA2 equals to IA1 into ZF. Means you should not connect these two directly in parallel. I will connect these two with some impedance gap. Simply like this. We are connecting some impedance between the positive and the negative sequence networks in that manner. And this is the current flow in this impedance as IA1 here. IA1 is a current flow in that one. And already, as you said, VA1 minus VA2. This is VA1 voltage and this is VA2 voltage. This is VA2 and this is VA1. What is VA1 minus VA2? IA1 into ZF. So this impedance you keep simply as ZF. So whatever the fault impedance exists between B and C, that will appear between the positive and the negative sequence networks. And currents relation, if you call IA1 plus IA2, anyhow 0. IA1 is flowing like this, IA2 is in the opposite direction, sum of the two currents is 0. And zero sequence current is equals to 0. Zero sequence current equals to 0. Now you write quickly what is IA1, IA2. Currents itself is sufficient. You don't need to think about voltages. Similar calculation of voltages there. Okay. So currents I am writing, sequence currents first. Sequence currents. IA1 current. What is the current IA1? EA1 by Z1 plus Z2 plus ZF. Pre-fault voltage EA1 by positive sequence impedance plus negative sequence impedance plus fault impedance. What about the negative sequence current? It will be minus IA1. Negative sequence current IA2 is equals to minus IA1. What is zero sequence current? That will be 0. Zero sequence current will be obviously 0. And what is a phase current? Phase current means phase B current. Phase B current. That is nothing but fault current, as you said. So it is minus J root 3 times of IA1. So you can get this as minus J root 3 times of IA1 means it is EA1 by Z1 plus Z2 plus whatever the fault impedance you say Z. This itself is fault current as well as the phase C current also. As well as the phase C current also. Yeah. So you please complete this one. So I've discussed with a solid faulted condition as well as with the fault impedance also. Fault impedance. So I have to do three things further. First thing is a generalization. Generalization. How to find out LL fault current for the fault at any place in the system. For the fault at any place in the system, that I have to do. After that, I should move to breaker rating calculation with respect to LL fault. How to, with what rating we have to design the three-phase circuit breaker, and then fault level formula. That's it. Fault level formula I'm going to take up. Yeah. So let's take in the next slide. Generalization. 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 So I'll take one bulk system, whatever it is. It may be a generator, transformer connected like this, and this side you have some system, big system, and this side you have a transformer I'm showing, and it's connected to some system. So like this, we have one big power network, right? Like this, we have one big power network. And I'm showing some location as a fault here. This is the fault location I'm showing. With respect to that LL fault location, LL fault, with a fault impedance, of course. Tell me please. With respect to this fault location, we have to find out pre-fault voltage, positive sequence Thevenin impedance, negative sequence Thevenin impedance. Okay. So with respect to the fault location, we have to calculate the pre-fault voltage, and you find out Z1 equivalent, positive sequence Thevenin impedance, and then negative sequence Thevenin impedance, that is Z2 equivalent. Positive sequence Thevenin impedance and negative sequence Thevenin impedance. After calculating these things, if you want, you draw positive sequence network. Positive sequence network, neutral, pre-fault voltage. It is Z1 equivalent, and this is our fault location. And you have negative sequence network. Okay, it is Z2 equivalent. Okay, and it was a current IA2 I am showing. And here I have negative sequence voltage as VA2. Okay, with respect to fault location, you should find out the Z1 equivalent and Z2 equivalent. After getting these two, simply you connect the fault impedance between these two circuits, whatever you have the fault impedance that you connect. Okay, so this is the current IA1 we have, and this will be the voltage VA. That's it. So I think all of you getting this one, and you can write the sequence currents if you want, or you write the directly fault current value. Fault current IF is equals to minus J root 3 times pre-fault voltage by positive sequence Thevenin impedance plus negative sequence Thevenin impedance plus fault impedance. positive sequence Thevenin impedance plus negative sequence Thevenin impedance plus fault impedance here. Okay, that's a fault current. Else you can call that as a phase B current also. Phase B current. Else you can say that as fault current. Both are same. Okay, next thing. See, again, as we said in the earlier class, particularly with respect to LG fault, this is some system we have, and this again some other system we have, and we'll take the 3 wires, phase A wire, phase B wire, and it's a phase C wire connected between these two systems. Between these two systems, we have 3 wires connected. I am showing as ABC wires. Okay, so this is our fault location F. I am saying that's the fault location here. And if BC conductors are experiencing that LL fault like this, BC conductors are experiencing the LL fault something like this. Okay, then what about the current in the phase A conductor? What about the current in the phase A conductor? Will it exist or not? Between phase B and phase C, we have a fault. What about phase A conductor current? Will it exist or not? We can't say exactly, right? Maybe existing, may not be. But we are not clear about it because A is a closed one, right? Circuit A, phase A was closed one. Earlier, we have taken alternator, only one side. Phase A is exactly open. I'll say IA equals 0. But here I can't say that as surely. So in this case, again, with this type of circuit, we can't say this fault analysis, what we have done is exactly adopted. So to adopt whatever the fault analysis we have done to this, what do you have to do? This we have to redraw on the paper. This we have to redraw on the paper. How? How in the sense, this is system 1. This is system number 2. ABC conductors I will show first. It's a conductor A. It's a conductor B. And it's a conductor C. And this is the fault location we have. It is a fault location we have. And these are the conductor names. You can call ABC. ABC. Now, what we'll do? We'll take tappings. We'll be taking tappings. This is a phase A tapping like this on the paper. Phase B tapping. Phase C tapping like this. Okay, after taking these tappings on the paper, between B and C, we have a short circuit fault. You show that short circuit between B and C, LL fault, and this is a C current you have, and this is a B current you have, and what is the A current you have? What is it A current? That is 0. Phase A current is 0. Understanding? So now you can apply the analysis, whatever we have done. Clear? So next, let's take up this quickly. That is circuit breaker rating. Just I will give the formula for breaker rating here. CB rating based on LL fault. So I'll discuss that with respect to generator simply. I'm saying that with respect to generator. So this one generator we have. These are the 3 wires outcoming. Okay. And I'm showing one breaker here, simply a 3-pole breaker. 3-pole, 3-phase breaker, something like this I'm showing. 3-pole, 3-phase breaker. ABC. And we have a fault between BC conductors like this. It's a fault. So B, we have some current, and as well as C, we have some current. Current in the phase A is 0. Current in the phase A is 0. Can you tell me what is the breaker rating here? Circuit breaker rating 3-phase. Circuit breaker rating 3-phase. What I said? 3 into phase voltage in kilovolts multiplied with how much current the breaker has to interrupt. Listen, please. All of you, please listen. All of you, please listen here. All of you, please listen. What current the breaker has to interrupt here? Actually, phase A means pole A, no need to interrupt any current, it is carrying 0. But B has to interrupt IB current. C has to interrupt IC current. Which current I have to consider between these two to design the breaker? To design the breaker, which current among these two I have to consider? Is it IB or IC? Whichever is higher than these two, strictly speaking, whichever is higher than these two. But in this particular case, it is very clear to say both currents are equal. It's very clear to say both currents are equal. Either you can keep IB current or you can keep IC current here. Okay, so I'll write for your information, maximum of IB magnitude, comma IC magnitude in terms of kiloamperes. Okay, but IB and IC currents are equal, so you can call this like 3 into phase voltage in terms of kilovolts multiplied with the B current, multiplied with the phase B current in terms of kiloamperes, it will come with MVA. Don't proceed further to derive any equation. Don't proceed further to derive any equation. You stop at this point and you say this is a breaker rating formula. If you provide me data, I will calculate it. You provide me numbers. You provide numbers. You provide sequence impedances. You provide ratings of that one and all. I will calculate this. Okay. Else, if you want to write this, you can say V phase per unit, phase B current per unit into S base 3 phase. S base 3 phase in terms of MVA. Clear? V phase per unit into phase B current magnitude in per unit form multiplied with the S base 3 phase. Like that also you can write. You can write. Okay, let's take up the fault level also a bit quickly. Just equation only I am doing, right? For the fault level based on LL fault. Fault level based on LL fault or short circuit MVA for LL fault. We are writing this one for LL fault. See, fault level formula for each and every fault, it is same, but numbers will be different. Numbers will be different. What is formula for the fault level in MVA? If you write fault level in MVA, it is nothing but pre-fault voltage magnitude in the per unit form multiplied to fault current magnitude in per unit form multiplied with S base 3 phase. Okay, don't ask me how this equation is coming. I discussed many times till now. Okay, pre-fault voltage per unit, fault current per unit multiplied with S base 3 phase. Okay, so I can call this one pre-fault voltage per unit here. What is fault current per unit? For LL fault, what's the fault current per unit? Minus J root 3 times of pre-fault voltage by what you have? Z1 equivalent plus Z2 equivalent plus Z0 equivalent. This whole magnitude multiplied to S base 3 phase. S base 3 phase. And you can write now root 3 into pre-fault voltage square per unit square by magnitude Z1 equivalent plus Z2 equivalent plus Z0 equivalent magnitude in per unit form multiplied to S base 3 phase. This is a way of writing that fault level in an extended way. Yeah, ZF is also there. I'm sorry, I'm really sorry. It's not Z0 equivalent. It is ZF. I'm really sorry. Kindly excuse me. This is ZF, fault impedance. By mistake, I have written Z0. ZF. Okay, next. See, I will make the assumptions at a stretch and I will write the final equation. Pre-fault voltage per unit value will assume as 1. Okay, and ZF equals to 0, solid fault. And we'll take no resistance for the network. So Z1 equivalent is Jx1 equivalent, Z2 equivalent is Jx2 equivalent, and I'll say final equation. Let fault impedance value 0, pre-fault voltage 1 per unit. Okay. Network is lossless. So I can write from this fault level in MVA, fault level in terms of MVA is equals to, you see, √3 in the numerator into S base 3 phase, by, you can have here X1 equivalent plus X2 equivalent, X1 equivalent plus X2 equivalent, this number per unit. Okay, this will be coming in terms of MVA, provided that you substitute S base in MVA. You substitute S base in MVA, you will get that answer in MVA. That's the meaning here. Okay. Yeah. So we will be stopping the class at this point. Tomorrow class we will do. Tomorrow we have 2 p.m. to 9 p.m. 2 p.m. to 9 p.m. class. Tomorrow we'll do one problem on this LL fault, double line fault, and then we will continue with the double line to ground. Okay. So now you can ask me your doubts, whatever you have. So I'm making all the hands low. Kindly raise your hands if anybody have a doubt. So don't ask me in the Q&A. Don't ask me in the Q&A. Okay. If you have any doubt, you come and talk with me. Tanvi.
Sir, I have a doubt in the single line to ground fault in the lightly loaded phase, sir. I didn't understand how that lightly loaded phase will explain.
That is having more impedance, right?
Yes, sir. More impedance, yes, sir.
More impedance means by means of the voltage division technique that will experience more voltage, right?
Okay, okay. Like voltage division. Okay, sir.
Yeah. That's it?
Yes, sir. That's it.
Yeah. Sai Charan.
Sir, one doubt is clarified now, and in page number 210, sir. 207.
210.
207, sir.
Okay.
Sir, here you told that we will not have a fault current path when it is grounded, sir.
Yeah.
LG fault. When it is not grounded, then we don't have path for fault current in LG fault. But when we took the transformer like earthing, then how did have like closed path, sir?
I didn't get you what you're asking exactly, Sai Charan. Please be clear.
Sir, in transformer we did earthing now, sir.
Okay, we do earthing. Yes, correct.
That is grounding to body.
Yes, correct.
Then in that case, the EMF induced because of that leakage current is leakage flux is
Okay. What's your doubt in that then? If the transformer neutral is grounded, what's the issue with that now?
Then I'm asking that in that case, if you have closed path, then why we don't?
Then why you are discussing about neutral grounding at all? Already you have grounded neutral, right?
No, sir. In ungrounded neutral, you told that.
Ungrounded neutral means transformer neutral is not grounded. Alternating neutral is not grounded. Else you say Z0 equivalent with respect to location of fault is infinite. That's the case. What I am saying to you.
So in this earthing of transformer also, we will have grounding in case of star.
Yes, we have it.
You told that in case of grounded star only, sir.
See, if you are connecting only tank to ground, your neutral will not be connected to ground, right?
And in other case also we did both for common sir, neutral of that and the ground body.
Okay, Sai Charan, in that case, neutral is grounded, then obviously LG current will flow, right? Fault current will flow.
Yes sir, yes sir.
In that case, fault current will flow. Then what's your doubt here?
My doubt is that in alternator, ungrounded alternator only my doubts are in that one.
I have
Why
written,
the
as I have
fault
written
current
unground alternate here. What I have written here?
No, sir. In not this one, sir. Purpose of not in this purpose of neutral grounding, but generally.
Okay. Which slide you have doubt? Please tell me which slide you have doubt, Sai Charan.
Sir, in ungrounded alternator.
Okay, ungrounded alternator. In that
LG
case.
fault.
Okay.
In LG fault.
Do you have a written any apparatus above the alternator in the diagram?
Sir?
Have I shown any apparatus above the alternator in the diagram?
Means what?
No, please be clear at your doubt. What you are asking me. If you have an ungrounded neutral alternator, only alternator, then if you have a LG fault, there is no current flow.
Sir, sir, it is a LG fault means the conductor falls on ground, then ground shows a path, na, sir. Written.
Where it will flow, where that current will flow then. If that current is getting grounded, where it has to flow? It has to circulate and come back to the same position, right?
Yes, sir.
It is not coming because it is not finding any path to flow. Because neutral is ungrounded.
Okay, sir. Yes, sir. Yes, sir.
Getting saturation.
So we should think that if the conductor falls on ground, then ground shows the path for neutral grounded, and this will be the closed path in case of grounded.
Basic principle only, current will flow if there is a closed path. If you don't have a closed path, current will be zero.
Yes, sir.
Okay.
Yes, sir.
Any other doubt you have, Sajaran?
No, sir.
Yeah. Ranjit.
Sir, can you hear me?
Tell me.
Sir, why we are connecting a sequence network in a parallel in a LLG fault, sir?
LLG fault we have not discussed, right?
LL fault. For a LL fault, we are connecting a sequence network in parallel, and for a LG, we are connecting a sequence network in series.
Why we are connecting it?
Yes, sir. Why, sir?
Is there any direct thing what I said in the class?
Sir?
Any direct thing I said without by missing something in the class?
No, sir. That only asking, sir. Why we are connecting?
Why we are connecting? Tell me. You only tell me, please. Why we are connecting in parallel in case of LL fault?
Sir, maybe the fault is in a LL, so that maybe we are connecting the sequence network in parallel.
Why you have connected 3 sequence networks in series in the LG fault?
It is the line is connecting to the ground, so that
if there is no strong reason to connect them in parallel or series, I can connect in my own way. Yes or no?
Yes, sir.
What is the strong reason to connect them in series in LG, to connect them in parallel in LL?
Maybe in a line to ground fault, sir, so that zero sequence all come in series.
What? Maybe, Ranjit.
Sir.
Have you listened LL fault clearly?
Yes, sir.
Don't be ambiguous in your answer. Huh? Okay?
Okay, sir.
Our answer should not be like this. I am saying 11 ones are 11, 22 ones are 22, 33 ones are 33. That's why I am taking voltages 11, 33, 66. In that manner, your answer should not be.
Okay.
Yes or no?
Okay.
There should be a clear mathematical foundation for it. Why you are connecting the circuits in this manner only means there should be a mathematical foundation to that.
Yes.
What is that mathematical foundation in LG fault to say that the 3 sequence circuits are in series?
Sir, IN equal to IA plus IB plus IC, sir.
That's okay. Okay, you tell me LL fault. You asked me for LL fault, right? I connected the two sequence networks in parallel here. Okay,
Yes, sir.
why we have connected them in parallel?
IB will be equal to minus IC, sir. So that we are connecting it in a parallel.
Where is IB and IC in this circuit?
Sir, IA1 and IA2, sir,
IA1 and IA2
will be oppositely equal.
oppositely equal. Okay, what is the other statement?
IB will be equal to minus IC, sir.
That's okay. Any other statement? Voltage statement?
Both voltages will be equal, sir.
Then what's the
VA
doubt you
equal
have,
to-
Ranjit?
Okay.
What's
sir.
the doubt
This
you have
only
now?
I'm-
Tell me.
This only I'm confused with that, sir.
See, we have I drawn this circuit directly just by drawing this LL fault diagram?
After drawing it only advance by
After-
deriving it.
Have I drawn this? I have drawn this one first.
Yes, sir.
Okay, immediately have I drawn this sequence network connection?
Yes, sir. After
In between that, we discussed
Take-
many things, right?
we have taken a conditions about that. What are the pre-fault condition and post-fault conditions?
Okay. Post-fault conditions, what you got, Ranjit?
Uh,
This is one
We
condition,
will-
current condition. This is one condition, so-called voltage condition.
yes, sir.
Based on those conditions only we are giving connection, na?
Yes, sir.
We are not giving ambiguously as
Okay,
our
sir.
wish. Yes or no?
Yes, sir.
Then what's the doubt we have, Ranjit?
Okay,
Huh?
this only I'm confused with that, sir.
What confusion? Huh? I said many times VA1 equals to VA2. That's why I am connecting positive and negative sequence circuits in parallel. Because it is saying to me positive and negative sequence voltages are equal.
Yes, sir.
Okay. See,
Okay.
if I have shown directly, we have a LL fault between DC. Your sequence network connection will be in this manner. If I say, then there is a confusion. How you have connected, sir, positive and negative sequence circuits in parallel? How come you got this circuit from the three-phase network? That's a doubt.
Yes, sir.
In between that, what I discussed, all these things is to connect these two circuits in parallel only. All this discussion what I made is saying me to connect the circuits in parallel.
Yes, sir.
Tell me why you are connecting positive, negative, zero sequence circuits in series in the LG fault.
Sir, in that IN will be equal to IA plus.
In every case, IN equals to IA plus IN plus IC. Go to that LG fault analysis. Check that. Ranjit,
Sir.
have you attended yesterday class?
Yes, sir. Attended, sir.
Okay. LG fault we have no.
Sir, in that IA will be equal to IN, sir.
Okay, that's okay. What is the relation you got between sequence voltages and sequence currents? That you tell me.
IA1 equal to IA2 equal to IA0, sir. So that
Okay.
we are
Sequence
connected-
voltage relation. Sequence voltage relation.
Sir, VA1 will be VA1 equal to EA1 minus IA1 in
That is the end result. That's the end result. Before sequence networks itself, we have written the relation, right?
Yes, sir.
What is that relation between VA1, VA2, VA0?
VA0 plus VA1 plus VA2 equal to 3 into IA0 into VF. sir.
ZF,
ZF.
not VF.
3 into IA0 into ZF. sir.
For that purpose, I connected positive, negative, and zero sequence circuits in series
Yes, sir.
to get summation of the voltage.
Yes, sir.
To make that value equals to 3 into IA0 into ZF, we connected 3 ZF across it.
Okay, sir.
Okay. Have you
Okay.
revised the yesterday class?
No, sir.
Okay. Before coming to the next class, please revise it.
Okay.
Then only you will be clear. Else, this subject will be not that much easy without revisions.
Thank you, sir.
Okay, Ranjit. Okay. Kushal,
Yes, sir.
tell me, Kushal.
Sir, in the types of grounding,
Okay.
the first is equipment grounding.
Hmm.
The transformer winding neutral is connected to the internally connected to the tank nest.
Yeah.
And from outside it is connected to ground.
Yes.
And this ground also is connected to the neutral.
Actually, strictly speaking, Kushal, we have to provide two types of groundings there. One is a tank has to be connected to ground.
Okay, sir.
Next one, neutral has to be connected to ground.
Okay.
Okay. So rather
So
than
they
keeping
are
these
two differently grounded.
two different groundings, particularly in distribution system, I am talking, not with respect to your 33 kV by 11 kV transformer
Yes,
or
sir.
higher
In
levels.
power transformer.
In
it
power
is a,
transformer, you may have a
outside
separate grounding, Kushal.
Okay.
In power transformer,
Yeah.
you may have a separate grounding because a
And
neutral
if it is
grounding should be grounding should be more effective required as compared to the transformer tank grounding. That's why they may go for separate groundings in case of power transformer.
Okay, sir. And
Okay.
in delta connection, there is only outside grounding, sir.
There is no possibility of grounding, right, for delta winding.
Yes, sir. Just earthing tank.
Tank earthing
Yeah,
will be done
earthing is
whether
there.
the connection is in delta star, doesn't matter, right?
Okay.
Tank earthing is independent
Sir,
on winding.
okay, sir. Sir, so this is the earthing, sir. Difference between earthing and grounding.
Earthing means apparatus grounding is called as earthing.
Okay. Any equipment has grounding.
Any equipment apparatus grounding is going to be called as earthing.
Okay.
Even
Yes,
your household fridge, AC, whatever it is, mixer, grinder, whatever it is,
Okay.
that
Okay.
equipment earthing is going to be called as earthing. Neutral point grounding is called as grounding.
Okay, sir.
Okay.
Okay. Sir, and in per phase per unit diagram we have drawn earlier, sir, we have seen. So
Okay.
in that case, if we have taken the base values in the transmission line, and then form the reactance diagram, and taken the base values at the location of generator, so we will get the different reactance diagrams. Is it right?
Kushal, whenever you change the base value, definitely your per unit impedance diagram will change. Means not
No,
diagram,
sir.
numbers.
Base values are same, but the locations are different in generator and in transmission line. I am getting the different reactance.
Obviously, you are changing base, right?
Yes, sir. I mean, between that there is a transformer connected. That's why I will be getting different reactors. Is it right, sir? Means same base value is there, but locations is different.
That's what I'll tell you once. Please listen. See, this is one generator, transformer, and it's a line. Okay. So transformer ratings 11 kV, 200 MVA. And this is 11 kV by 132 kV. And it is also 200 MVA. Let me take. Tell me, what base values you want me to choose, Kushal?
In the generator, sir, 11 kV and 200
Generator,
MVA.
you get. What base values? 11 kV?
200 MVA.
200 MVA. Okay. So after choosing these values as base at the generator location, it will be valid up to primary of this transformer. And after reaching to secondary side, what will be your base? 132 kV, 200 MVA will be?
Yes, sir.
So with respect to these base values, you have calculated the generator reactance, transformer reactance, line reactance.
Yes.
Getting me, Kushal? I need your response.
Yes, sir. Sir, but
Listen
the
to
main
me.
thing is that
Listen to me, please.
yes.
Listen.
Okay.
You can draw the per phase model. You will get some numbers for generator, transformer, line.
Okay.
Okay. Now your doubt is, sir, I will take base values at this location as 11 kV, 200 MVA. Is it?
Yes, sir. Yes, sir.
And
Yes.
obviously you are changing base values, right?
Oh, okay. Yes, sir.
If you are changing base values, per unit numbers will be different, definitely.
Means at the transmission point, the base value actually is changing.
If you are changing here, obviously by reaching to generator, your base MVA will be 200
Yeah.
MVA and the base KV will be 11
into 11
by
by 130.
132 into 11.
Yes, sir.
Thanks so much.
Okay, sir.
Okay, understood?
Yes, sir.
Then automatically you are changing base values for generator as a whole system. All reactances in per unit will change. Your per unit reactance values are completely different, but absolute values will be as it is.
Okay.
Absolute values will not change, even though you are changing the base values.
Okay. Sir.
Okay.
Okay.
Any other doubt you have, Kushal?
Yes, sir. In that home grounding concept you have said you described.
See, home grounding in the sense. I think you can see the 3-pin socket in your house. Like this, you can see 3-pin socket. This is a bigger one, a bit, and we have 2 smaller ones, right? 3-pin socket.
Yes.
Have you seen this type of socket?
Yes, sir.
Yeah. For example, this is one equipment we have, maybe fridge or computer, whatever it is. Apparatus, I'll call. Apparatus. Actually, from this apparatus, you used to get one cable, maybe a 3-core cable. And for this 3-core cable, you will have a plug top. And for that plug top, you have one big pin and 2 small pins, right?
Yes.
This is one small pin, this is one small pin, and this is a big pin. Blue color one is a big pin. So how many wires you have in this cable? In this cable, how many wires you have?
3 wires.
3 wires. One wire is a phase wire. This is a phase wire. And this wire is a neutral wire. And the blue color big wire, what I have drawn there, that's the earth wire. Okay?
Yes, sir.
See, actually, this phase and neutral, for example, if it's a motor to you, for example, it may be fridge or anything, it may be a motor, compressor. Okay, it's a single phase motor. That single phase motor needed a supply of phase and neutral. Are you following me,
Yes.
Kushal?
Yes, sir. Yes, sir. Following.
So, phase and neutral of this winding are connected to these wires in the cable. Okay, whatever the apparatus
Yes, sir.
outer casing or outer metallic bodies you have, that metallic bodies are connected to this earth pin.
Yes, sir. Okay.
Getting me? Okay. Now,
Yes.
this is a 3-pin socket in your house. Now, if you are attempting to put this plug into this 3-pin socket, and you are getting supply from outside, right? Maybe from distribution transformer. It's a distribution transformer. You feel it's a single phase distribution transformer for time being. They will supply one phase wire and one neutral wire to you, to your house. Okay, so this neutral wire is grounded at the distribution transformer. Neutral wire is grounded at the distribution transformer along with the tank. See, whatever this phase and neutral provided by the distribution company to you, this phase wire you connect to one small pin like this. Okay, and whatever the neutral wire you have, that will connect to the another small pin like this. Getting me?
Yes, sir.
Now, if you put this 3-pin plug into the socket, obviously this phase is excited, neutral is also excited by means of the distribution transformer. Okay, whether this apparatus is active. Getting me?
Yes, sir.
Whether this apparatus is earthed or not now. If you are putting the 3-pin plug into the socket, phase wire supplied, neutral wire supplied by the distribution transformer. What about the earth wire?
Yes, sir.
What
Or
about the earth wire?
wire is home. In the home, you have grounding, sir. That is
That's it.
connected
That's
to-
a grounding, what you're doing in your home.
Okay. Sir, my
Okay.
doubt in the system, sir, you have said the neutral line is disconnected in the between. So, but
Okay.
in the generator side, it is connected to the ground. That's why the over voltage problem should not be happen because the ground should clear the potential difference. Means
See, actually, your doubt maybe what I think is, sir, already you provided a ground inside your house. Okay,
no, sir. In the at the generator side, I have doubt, sir.
but still you have a transformer in between that. The zero sequence network
Yes, sir.
is open.
In the transformer, sorry, at the transformer, sir. The transformer.
Okay,
neutral is grounded.
transformer neutral is grounded. Okay,
Okay. So
but your
in
load
between the
is
neutral
not
line is
grounded, right?
disconnected. No, load neutral, load neutral is also grounded, sir, in the
Not grounded,
home
right?
side.
In the home side where it is grounded, neutral wire.
It is grounded to not that neutral, but in the home side.
That's what I am saying you, Shahil.
Okay.
You are in an impression that, sir, already we are providing grounding in our house, even though the neutral wire was cut. What is the problem with that? Is it?
Yes, sir.
Is it your doubt? I'm repeating
Yes, sir,
that
yes,
doubt
sir.
what you have. Neutral wire was cut, sir. Already your what we call transformer neutral is grounded. And you are providing grounding in your home also. Then ground we
Yes,
have,
sir.
right? Then what's the problem of cutting the neutral? But one problem here is this neutral wire, what we are getting from distribution transformer and this earthing what you are providing in your house. These two are not connected, na?
Okay.
Getting that?
Okay, sir.
These two
Okay.
are not connected, right?
Okay, sir. So that difference will be there, sir. Okay.
The difference will be there. For example, if you join these two together, then even though your neutral wire was cut, then you may not experience any over voltage.
Okay.
Getting me?
Yes, sir. Getting.
This we are going to call in modern days as protective earth neutral. Getting the
Okay.
point? What is it? Protective
Yes, sir.
earth
Yes, sir. Getting.
neutral. PEN. You do this type of connection, then even though the outside neutral wire was cut, your house will be safe from damages.
Yes, sir.
Okay.
Okay, sir. Got it.
Can you tell me why this is big pin and why these two are small pins? This is earth pin, right?
Sir,
It's a phase.
Yes, sir, yes.
It's a neutral. Why that? Earth is a big pin?
sir, because of the low resistance, sir, because of the low, you should provide low resistance to be ground.
Low resistance.
Means large current should flow.
Large current.
Means large current should flow if the fault occurs.
So it was a plug, right? It was a plug. So one is of phase, other one is neutral. This big pin is a earth pin, what we are saying. Earth pin. Now, if you are putting this into socket, see, if you make this big pin also as a small one, for example. Yeah, understanding, Kushal, all of you.
Yes, sir. Yes, sir. Getting.
If this big pin also, you make it as a small one, then unfortunately, sometimes, maybe during power cut times or by our laziness, we may put this terminal into phase by mistake. Getting me?
Okay. Yes, sir.
Into the 3-pin socket, it has to accommodate, right?
Yes, sir.
Right? If you make this pin also smaller one, I may adjust this to put this earth pin into the phase.
Okay. Yes, sir.
May not be intentionally, by mistake. It may happen. That possibility is there.
Yeah. Yes,
That's
sir.
why if you make this one big pin, even though you try to put this into the base pin, it won't go.
Yes, sir. Yes, sir.
So that your equipment will be safe.
Yes, so the phase current then will flow through the equipment outer side and it will be
Yeah.
dangerous for.
And one more thing. You observe the 3 pins what you have here, which is whether all the 3 are having same length.
No, 2 are same length, sir.
Which is a bigger one.
Earthing wire. Earthing pin.
So whenever you put this one into the plug, first equipment is earthed, then the supply is given.
Okay, sir.
Understanding?
Yes, sir. Understand.
These are some things what we get in house
So
wiring.
means some residual current in the equipment like that, no?
It may be there. That will be first grounded. Then supply
Okay.
is given to the winding.
Okay, sir.
Okay.
Okay, sir.
Yeah. Fine.
Okay, sir.
Hello, sir.
Got it.
Yeah. Who is this?
Sir, Sai Charan, sir.
Tell me, Sachin.
Sir, if we take in this case, if for the grounded neutral here, if the neutral is open, then how would the current come to the like a return path? It should come to the same position, sir. How this happens
It
here?
will flow through ground only.
No, sir. I'm asking that it should come to the same position, sir, as in ungrounded alternator.
No, this is grounded, right? If, for example, if this neutral wire is open, this is grounded, this is grounded. We have a link through ground, right? For that current flow. Getting?
Then how it come to the same position, sir? Then here.
Sachin, what happened to you today?
Sir,
Tell me, Sachin.
I'm getting doubt in this one only, sir. I think I am not expressing my doubt clearly.
Okay, tell me.
Sir, in this one only, if we talk simply, then how would be the return current?
Return current will flow through ground, right? Like this.
Okay, after reaching ground, where does it flow, sir?
It should flow into the distribution transformer ground.
Here the neutral is open, na, sir. For the
Neutral is
distribution.
open, but you have alternate current path, right?
Yes, sir. Yes, sir.
Through phase it will go and goes into the equipment and comes back neutral, earth, and then grounded.
Okay, so ground means we should take that that ground is common to all the equipment that we have to connect to.
Yeah.
Yes, sir. Okay, sir.
Okay.
Yes, sir.
Yeah. Anil.
Hello, sir. Good evening, sir.
Good evening, Anil. Tell me.
Sir, can you please open the page number 220?
Okay, tell me, Anil.
Sir, before slide.
Okay.
Okay, sir. Sir, ఇక్కడ జనరల్ మనం కంక్లూడ్ చేసాం కదా.
You please tell me in English. Some people are feeling this. Okay. Tell me.
Have a doubt regarding in this symmetrical component of voltages.
Okay.
Okay, sir. Here, voltage VA is equal to VA.
VA equals to
VA.
VA.
Sir.
As it is. Okay, fine.
VB is equal to VB. But VC is equal to minus VB, sir.
Why
we don't write here sign?
Why minus VB?
Because VC is equal to minus VB.
Where we have written? Anil.
Okay, sir. Okay, sir. I confused regarding here. Okay, sir. We are putting in the
confused between voltage and currents.
Yes, sir. Yes, sir.
Okay, fine. Any other doubt you have, Anil?
No, sir. No, sir.
Yeah. Tulsi. Tulsi. Tell me, Tulsi.
Sir, 194F, sir.
194.
Yes.
Okay.
Sir, can I ask in Telugu, sir? Because
Okay, fine.
sir, అక్కడ 11 kV ఎలా వచ్చిందో ఇంకోసారి ఎక్స్ప్లెయిన్ చేస్తారా
That's
సార్?
what I explained in the previous slides, right?
ఓకే, అది కాదు సార్. ఇన్సులేటర్ దగ్గర 11 kV ఎలా వచ్చింది?
What is this B voltage you measure? B
11
means
kV.
B2,
B2 ground,
B2 ground, what you have connected here?
insulator.
B2 ground. Insulator only, right?
Yes sir.
Our impedance is neglected
Okay sir.
because it is a conducting body, galvanized iron or
Okay.
galvanized steel, whatever it is. So as
Okay.
it is neglected, I can say this point itself is ground. So B2 ground voltage is 11 kV, so that will appear across insulator.
Okay sir. Same in C also, no, sir?
Same in C also, yes.
Okay sir. In 196F sir.
Okay.
సార్ ఇక్కడ అదే ఆర్క్ ఫామ్ అయినప్పుడు రెసిస్టెన్స్ కూడా వస్తుంది కదండి సార్ మామూలుగా మనం
Definitely, yes.
అది కూడా కన్సిడర్ చేసుకుంటాము సార్ మనం?
Yeah, this will act as a fault impedance.
ఓకే సార్.
That will act as a fault impedance. RF. Okay.
ఓకే ఓకే సార్. నిన్న 2 జనరేటర్స్ ప్రాబ్లమ్స్ ఒకటి డిస్కస్ చేసాము సార్ మనము.
Yeah, tell me.
అందులో న్యూట్రల్ వోల్టేజ్ కనుక్కున్నప్పుడు సెకండ్ జనరేటర్ లేనప్పుడు ఫస్ట్ జనరేటర్ యొక్క న్యూట్రల్ వోల్టేజ్ ఎంత అని చెప్తాం సార్ మనం?
We don't have second generator.
ఓకే సార్. ఎస్ సార్. సెకండ్ జనరేటర్ లేదు.
Means we have only one generator in the system.
ఎస్ సార్.
Neutral is ungrounded.
ఎస్ సార్.
That's what we have done first problem today.
కాదు సార్, న్యూట్రల్ గ్రౌండ్ అయింది సార్.
Neutral is grounded.
ఎస్ సార్.
Then you do with a single generator analysis. Find out neutral voltage.
ఓకే సార్. ఓకే, సారీ సార్, ఐ గాట్ ఇట్ రాంగ్.
Yeah. Okay.
ఓకే సార్. 1 minute. సరే.
Tell me, Tulsi.
హలో సార్.
Tell me.
197 సార్.
Okay.
ఓకే. ఇక్కడ అర్థమైంది సార్. మళ్ళీ 11/√3 ఎందుకు తీసుకుంటున్నాం?
Yeah.
205 సార్. కప్లింగ్ అక్కడ చెప్పారు కదండి సార్, అది ఒకసారి ఎక్స్ప్లెయిన్ చేస్తాను.
205.
ఇది ఒకసారి సార్.
See, actually, if you have 3 primary windings and 3 secondary windings in your transformer,
ఓకే సార్.
or else you assume it is a single phase transformer, primary winding and secondary winding.
ఓకే సార్.
You kept these windings on a core
ఓకే సార్.
for a proper flux linkage.
ఓకే సార్.
Even though you keep the windings on the same core and assuming that we have a proper flux linkage, but definitely there will be a considerable amount of leakage flux.
ఓకే.
Okay.
ఓకే సార్.
Whatever the leakage flux flowing in the oil, transformer oil, that may link with the transformer tank,
ఓకే.
causing an EMF in that.
ఓకే సార్.
So if we have some EMF induced in the tank, if it touches the tank, there may be a possibility of getting shock.
షాక్.
Okay.
ఓకే సార్. గాట్ ఇట్.
To overcome that issue, we have to connect the tank of the transformer to ground.
ఓకే సార్.
This is going to be called as earthing, which is done for the safety of the person. Means for the staff, whoever is operators, you have lineman or anything. For the safety of them, we have to do that type of grounding.
ఓకే సార్.
So intentionally we don't touch, but by mistake we may touch.
ఓకే సార్.
Okay.
ఇన్ 207 సార్.
Okay.
సార్ అక్కడ రిలే అదొకసారి ఇప్పుడు ఎల్జీ ఫాల్ట్ జరిగినప్పుడు డిటెక్ట్ చేయనప్పుడు రిలే మళ్ళీ ఎలా కండక్ట్ చేస్తుంది సార్ గ్రౌండింగ్ ఇచ్చాక?
After you connect to ground, you have sequence currents flow, right? Circuit
Okay,
will
sir.
be closed.
ఎస్ సార్.
Current will flow. That's a heavy current. Definitely relay will sense it.
ఓకే. టు డిక్రీజ్ దట్ కరెంట్ ఓన్లీ వి ఆర్ పుట్టింగ్ ద ఇంపిడెన్స్.
To reduce that current, later on our what we call a statement is to keep some non-zero impedance so that current will be reduced.
ఓకే సార్.
Even though there is a delay in the
హలో సార్. సార్ వాయిస్ వినపడలేదు.
even though we delay the relay operation, but still our equipment will be safe.
సేఫ్. ఓకే సార్.
Okay.
ఇన్ 216 సార్.
216.
16.
Okay.
సార్ ఇక్కడ ఇప్పుడు సింగిల్ లోడ్ కనెక్ట్ చేసినప్పుడు ఫాల్ట్ జరిగితే మళ్ళీ ఇది ఎలా చేస్తాం సార్ మనం అనాలిసిస్?
It's not a fault, right?
కాదు సార్. ఒకవేళ సింగిల్ లోడ్ కనెక్ట్ చేసి
Hmm.
లోడ్ దగ్గర ఫాల్ట్ జరిగినప్పుడు సార్.
If you have fault on load location,
ఎస్
then
సార్.
your pre-fault voltages will be unbalanced voltages.
ఎస్ సార్.
Then you draw a positive sequence Thevenin network, negative sequence Thevenin network, zero sequence Thevenin networks,
ఓకే సార్.
and connect them in series.
ఓకే.
Across that, you take a short circuit.
ఓకే
But
సార్.
pre-fault voltages are unbalanced voltages.
అన్‌బ్యాలెన్స్.
Okay, means you get positive sequence pre-fault voltage, negative sequence pre-fault voltage, zero sequence pre-fault voltage.
3 వస్తాయి సార్ అప్పుడు మనకి.
Yeah, because your pre-fault voltages are unbalanced, right?
ఓకే.
If
అవి
you convert them
అన్‌బ్యాలెన్స్.
into symmetrical components, you get positive, negative, and zero sequence voltages.
ఓకే. అవి అన్‌బ్యాలెన్స్‌డ్ ఎందుకు అవుతున్నాయి సార్?
What is your pre-fault condition?
ఫాల్ట్ జరగకముందు.
This you want me to take as pre-fault system, right?
ఎస్ సార్. ఎస్ సార్.
Means pre-fault system is unbalanced only, right?
ఎస్ సార్. గాట్
Then
ఇట్.
your VA, VB, VC, what you calculate here before occurrence of fault are unbalanced.
అన్‌బ్యాలెన్స్.
So this VA, VB, VC, what you have with load, those are pre-fault voltages.
ఎస్ సార్.
If those are unbalanced, obviously you get positive sequence pre-fault, negative sequence pre-fault, zero sequence pre-fault voltages.
ఓకే సార్.
What you should keep into the sequence networks.
ఓకే.
Okay.
గాట్ ఇట్ సార్.
Yeah.
Sir,
Any other
230.
doubt you have, Tulsi?
ఎస్ సార్. 213 ఎఫ్ సార్.
Okay.
సార్ ఇక్కడ లాస్ట్‌లో అది ఇంకోసారి చెప్పగలరా సార్? ఎల్ఆర్ ఈజ్ ఈక్వల్స్ టు ఫార్ములా.
This formula, we have a
Deriv-
derivation we have not discussed.
ఓకే సార్.
Okay.
సార్ మరి యెస్టర్‌డే ఒక మోటార్ ప్రాబ్లమ్ 4 మోటార్స్ ఉండి సర్క్యూట్ బ్రేకర్ పెడతాం అది ఎక్స్‌ప్లెయిన్ చేశాం సార్. అది లాస్ట్‌లోనే సర్క్యూట్ బ్రేకర్ పెట్టాలని మనము పర్ ఫేజ్ నెట్వర్క్ డ్రా చేసినప్పుడు ఎలా తెలుస్తుంది సార్ అది?
They have given that in the problem, right?
ఎస్ సార్. అంటే పర్ ఫేజ్ నెట్వర్క్‌లో మనకి ఫస్ట్ దగ్గరైనా సర్క్యూట్ బ్రేకర్ పెట్టొచ్చు కదా అని నాకు డౌట్ వచ్చింది సార్.
No. Where is the location of breaker in your single line diagram?
ఆ సింగిల్ లైన్ డయాగ్రామ్ మనమే డ్రా చేసుకున్నాం సార్. వాళ్ళు జస్ట్
We have not drawn it. That's given in the question.
ఓకే సార్.
See that question.
ఓకే సార్. సార్ మరి ఇప్పుడు మనము నార్మల్‌గా ఎక్స్‌ప్లెయిన్ చేశారు కదండీ సార్. ఒకటి గ్రౌండ్, ఒకటి లైన్, ఒకటి ఫేజ్ ఉంటదని. మరి 2నే ఉన్న దానిలోకి ఏం 2 సాకెట్ అదే 2నే ఉంటాయి కదండీ సార్ కొన్ని దానిలోకి.
Then there may not be any necessity of earth for it.
ఓకే. దట్స్ వై ఓన్లీ దే డిడ్ంట్ గివ్ థర్డ్.
They didn't give. Yes.
ఓకే సార్.
Maybe a low rating equipment,
ఓకే.
a telephone charger.
ఓకే సార్.
Yeah.
సార్ ఇంకొకటి ఉంది సార్. ఇప్పుడు ట్రాన్స్‌ఫార్మర్ బ్యాంక్ న్యూట్రల్ కట్ అయితే ఏమవుతుంది సార్ మళ్ళీ? 213
Transformer bank neutral cut means obviously you say neutral earth earthing, neutral earthing was cut, right?
ఎస్ సార్.
Then obviously induced EMFs itself might become unbalanced. That will also lead to unbalanced operation.
ఓకే. అప్పుడు లోడ్ సైడ్ కూడా అన్‌బ్యాలెన్స్‌డే అవుతుంది సార్.
Unbalanced voltage we may get. Yes.
ఓకే. థాంక్ యూ సార్.
Okay, fine.
థాంక్ యూ.
Ubin.
Sir,
Tell me, Ubin.
sir, I'll ask after some people because I'm just revising everything.
Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, in case of isolated neutral LG fault current, sir, alternate is not neutral. Alternate is not connected to ground, sir, neutral.
Yeah.
And system consisting of alternator, transformer, and transmission line, sir.
Okay.
Transformer neutral is connected to ground, sir. That so by ante it can carry zero sequence current, sir.
It may not be, right?
Sir, means delta star ground transformers, sir.
Delta star ground means star ground will carry. Okay.
Yes, sir. Secondary will carry, sir.
Primary also will carry.
Yes, sir. Sir, in that case, if fault is occurred at transmission line, single line to ground fault, sir.
Then you have a zero sequence circuit closed one, right?
Yes, sir. That means alternator will drive only load current or both. Pre-fault system is loaded one, sir.
Alternator will drive positive and negative sequence currents only,
Yes, sir.
but your zero sequence current will start from transformer.
Okay. That means it should carry fault current. That means in fault
Generator
component
will also carry the current, definitely.
only two components of fault current it will carry, sir.
IA1, IA2 it will carry.
IN0 will be carried by transformer, sir.
Transformer and line fault.
That thing can happen. That thing also can happen, sir. Means two
Happen.
components can be driven.
Yes, yes, may happen.
Okay. Sir, I have three conclusions, sir. Is that right or not? Can you say, sir?
Tell me.
Sir, if the pre-fault system is this is regarding to pre-fault calculation, sir. If the pre-fault system is unloaded, then we are taking V per pre-fault voltage, V pre-fault voltage as EA1, sir. Positive
Okay.
sequence voltage as EA.
Okay.
So if pre-fault system is loaded and unbalanced, sir, we have to calculate the pre-fault voltage in terms of by applying symmetrical components. We have to get VA1, VA2, and VA0 by adding VA1 plus VA2 plus VA0. So VPF we should write now, sir.
No. We have to show pre-fault voltage of positive sequence in positive sequence network, negative sequence pre-fault voltage in negative sequence network, zero sequence pre-fault voltage in zero sequence network separately.
Separately, we should write and we should calculate the fault current, sir.
Yes.
Sir, if pre-fault system is balanced and loaded one, sir, then pre-fault voltage is EA minus IA into Z1. Means I'm taking only single line to ground fault condition, sir. Pre-fault voltage is EA minus IA into up to what location Z1 equivalent.
Okay. IA1 into Z1.
Yes, IA minus yes, sir, IA1 into Z1 equivalent.
Yeah.
Is that right only, no, sir?
You can write it like that. EA1 minus IA1 into Z1 equivalent. That is VA1 at the fault location.
Okay, sir. Only VA1 only will exist, no, sir, because it is balanced.
Yes.
Okay, sir. Sir, if in case in question they have given terminal voltage, sir, rated terminal voltage, that we should take it as line to line or phase, sir.
Generally, line to line they will give. If they have given in absolute form, it will be line to line.
Okay, means terminal
Check the
voltage is
ratings.
not.
You check the ratings by common sense.
Okay, sir.
For example, if I say what we call rated voltage of the system is 11 kV, terminal voltage is 6.1 kV.
Okay, sir. 11 by.
Common sense, it may not be line to line, it may be phase. But generally they will give line to line voltage only.
Okay, sir. Sir, in CB name circuit breaker nameplate, we have breaking current and making current, no, sir.
I don't think so. You have braking capacity.
Okay, so break.
Only symmetrical braking capacity you have on that.
Okay, so then it is designed only for symmetrical braking capacity, or means making current is high, no, sir, compared to braking current.
Designed may be different.
Yes, sir.
It might be designed for asymmetrical braking capacity, not making capacity. It will be designed for asymmetrical braking capacity.
Sir, but it will carry making current for 2 cycles, no, sir. Means that in that period it should not be damaged, no, sir.
Why it will damage? Generally, you tell me, Pratyush. Why the breaker will damage if it is getting opened?
Sir, I didn't understand, sir. Once you repeat, sir.
So whenever the breaker is getting opened, we are bothering that the breaker is going to be damaged, right?
Yes, sir.
Why?
Sir, due to high thermal stress, sir.
High thermal
stress on the contacts, sir.
High thermal stress on contacts means, can you elaborate? High heat.
Yes, sir.
Simple. High heat.
Yes, sir.
Who is going to decide heat?
Sir, current that arc resistance, current flow, sir. In
current. Which current?
Braking current, sir.
What means, is that braking current?
Means sir, అంటే ఆ కాంటాక్ట్స్ మధ్యన మనం అంటే ఇప్పుడు ఫాల్ట్ కరెంట్ వచ్చినప్పుడు సర్క్యూట్ రిలే అనేది అనలైజ్ చేసినప్పుడు సర్క్యూట్ మూవింగ్ కాంటాక్ట్స్ ఫిక్స్డ్ కాంటాక్ట్స్ సపరేట్ అయినప్పుడు
Okay, that and all okay. Breaking current you said, na?
ఎస్ సార్.
What is the nature of that breaking current? Is it RMS current or peak?
సరే ఆర్ఎంఎస్ కరెంట్.
That's it. You are only saying the answer. So based on what current I have to design the breaker context? RMS current or RMS breaking current or making current?
సార్ ఆర్ఎంఎస్ బ్రేకింగ్ కరెంట్.
Making current is instantaneous value.
ఎస్ సార్.
Breaking current is RMS value.
ఎస్ సార్.
So we have to design our breaker based on RMS current.
ఎస్ సార్.
RMS breaking current.
ఓకే సార్.
Which breaking? Symmetrical or asymmetrical?
సార్ you should carry both DC and AC.
Asymmetrical.
Yes sir, asymmetrical.
Because we have to involve DC component also.
Yes sir.
So for example, if they said it's a 2000 MVA 30 kVA 30 kV circuit breaker,
Yes sir.
what is this 2000 MVA? Symmetrical breaking capacity, which they will give in a nameplate. Okay.
Okay sir.
And if you multiply this with 1.6, you are going to get the momentary breaking capacity of the circuit breaker.
Okay sir.
Momentary breaking capacity of the circuit breaker.
Okay.
And you might be having a doubt that, sir, why they are giving 2000 rather than directly 1.6 into 2000 on the nameplate?
Yes sir.
They can give 1.6 into 2000 also on the nameplate, right? Why they are not
Yes.
giving it? Why they are giving only 2000? Getting me?
Sir, yes sir.
Because this number is not constant. It will vary with respect to cycles.
Yes sir.
That is one reason.
Okay sir.
Other reason is DC component is not same in all the three phases.
Yes sir.
But AC component is same in all three phases.
Yes sir.
All the three phases will have same breaking capacity as a symmetrical one.
Yes sir.
2000 MVA symmetrical breaking capacity for all the three.
Yes sir.
But asymmetrical breaking capacity might be different for each and everyone. In
Yes,
the
sir.
operation, actually. In the operation, not in
Yes,
the
sir.
design. In the design, all the three might be designed with 1.6 into 2000 for safety reasons.
Yes sir.
But during operation, if phase A is having 1.6 into 2000, phase B may not have that.
Yes sir.
Phase B might have a different number. Phase C might have a different number.
Sir, yes sir.
What is common thing for all the three phases means symmetrical breaking capacity is common.
Yes. Okay.
That's why
Sir,
they
can
will put this on
sir
the
can okay sir. Sir, can we say this reason sir? This symmetrical this as DC component is will be there for some cycles. Means heat generated is I square RT, no sir. So for that
beyond some cycles, what we call breaking, interrupting capacity of breaker is going to be reduced. But the design value, what you have to remember, Pratyush,
Yes sir.
the design value, but operating value should be lower than this. Then only your breaker is safe.
Yes sir.
How much MVA it is interrupting? Practically, that number should be lower than 2000. Then only your breaker will be safe, right?
Yes sir.
Else it's going to be damaged.
Okay.
Okay,
Okay, sir.
tell me what's your doubt?
సార్ సో అంటే ఇప్పుడు 1.6 into 2000 అనేది అంటే DC కాంపోనెంట్ ఉన్నదని జస్ట్ 3 or 4 సైకిల్స్ 5 సైకిల్స్ ఉంటది కదా సార్. సో అంత తక్కువ సైకిల్స్ అనేది హీట్ జనరేటర్ అనేది తక్కువ అంటే చాలా తక్కువ టైం ఉంటది కదా సార్. సో దట్ అంటే దాన్ని బేస్ చేసుకుని మనం డిజైన్ చేయాల్సిన అవసరం లేదని చెప్పొచ్చా సార్?
You should not say that. You should not say that. Because who knows? Unfortunately, by mal operation also breaker may open, irrespective of relay signal.
Yes sir.
So to overcome those issues and all, we should consider that DC also in that.
Okay.
Okay.
Yes sir. Sir, normal doubt sir. Sir, ఇప్పుడు అంటే ఇప్పుడు న్యూట్రల్ వైర్ కాకుండా మన ఇంట్లో ఉన్న గ్రౌండ్ వైర్ అనేది రిటర్న్ పాత్ కింద యూజ్ చేస్తే ఏమవుతుంది సార్?
If you use it, there is no problem actually, which I feel.
Means stability issues they do not be there sir.
No, nothing. Provided that your grounding is perfect. Your home grounding is perfect. Okay, I have shown this also to you, right? Protective earth neutral.
Yes, sir.
That's a modern technique of providing grounding in house.
Okay, sir.
Okay.
Yes, sir. Sir, last one, sir. Sir, in case of preferred
1
system
minute,
is bad.
please. 1 minute.
Yes.
Tell me.
Sir, in case of preferred system is balanced, the default voltage what we write is EA1 only, no, sir. Default voltage used to be write in EA1, no, sir. That
Okay,
positive
yes.
sequence network.
Yes.
Okay, sir. That's that conclusion only I want. That's it. Sir.
Okay.
Thank you, sir.
Imtiaz.
Good evening, sir.
Yeah, tell me, Imtiaz.
Sir, in neutral grounding, I have one doubt, sir. Sir, in normally, if a transformer is ungrounded, means they have the root 3 times of the preferred voltage, no, sir, in other phases. But in the diagram, unbalanced voltage you showed me, sir, diagram at 20 kilowatt and 100 kilowatt.
That's a load you have shown.
Okay, sir, that's a load. But there is a neutral is connected to the transformer node, sir.
Yeah.
At that time, we don't get root 3 times of the preferred voltage in the B and C.
Even if you don't get,
then loads will be not disturbed, no, sir, at that time.
can you repeat again, please?
Sir,
If you connect a line-to-line load, there is no issue.
Sir?
Imtiaz, if you connect a load between AB, BC, CA.
Sir, my doubt was in that diagram, the transformer is grounded, no, sir. At that time, we don't get the root 3 times of the preferred voltage in the B and C.
Default voltage, why you are talking here?
Sir, I am getting the fault in the phase of A, LG fault.
If this is a system you have.
Yes, sir. I am getting the fault in the A phase.
Okay.
At the time, B and C will be undisturbed, no, sir, because of the neutral is grounded of the transformer. But you are saying that the neutral is open, no, sir, in that last one.
Neutral is open, but you have a ground connection like this, right? For phase A to ground fault, you have a ground connection, right?
Yes, sir.
Then you have current circulation, fault current circulation.
Yeah, but B and C will be undisturbed, no, sir, at that time.
B and C, we can't say these are undisturbed.
Because we have connecting the neutral to the transformer.
Why neutral to the transformer? What you are connecting?
Grounded, sir. Sorry, neutral.
Okay.
Neutral is
I got
grounded.
it. See, phase A is getting grounded.
Yes.
Okay, you are saying that, sir, this load is grounded. Is it?
No, sir.
Whenever phase A is grounded, you are saying that neutral is grounded. Is it?
No, sir. Actually, doubt ఏమంటే phase A లో fault వచ్చింది, sir.
Okay, phase A to ground you have a fault. Okay.
Yes, sir. Our transformer is neutral is grounded.
Grounded. So we have a fault current circulation like this.
Okay, then B and C will be undisturbed.
Why B and C are undisturbed? What is this neutral voltage?
It's connected, no, sir.
Where?
Connected to our transformer.
Where it is connected to our transformer?
Sir, if you connect that the neutral is connected to the transformer grounded.
Okay, you are saying me in the original case?
Yes, sir.
Without neutral cut?
Just neutral is connected to the ground of the transformer.
Is this case you want me to discuss?
Yes, sir. Yes, sir.
Neutral was connected already.
Yes, sir.
Okay, now tell me. If phase A to ground fault active.
Yes, sir.
Then B may experience as it is of B voltage, C may experience as it is of C voltage by the application of KVL.
Yes, sir.
Yes, correct. What's the doubt in that now?
Okay, if you open that neutral.
If you open this neutral.
then B and C will be just off load now, sir. Because of the
B
no
and C?
return path. No return path.
No return path.
We can say B and C will be undisturbed.
Why you say undisturbed? Your neutral voltage is changing at the time, right?
Sir, there is no return path now, sir, at that time.
What is no return path?
Sir,
You have return path between B and C, right? B and C are close, na?
yes, sir.
Then you have a return path between B and C.
అంటే B
Then
నుంచి
what you should say is, sir, whenever this neutral wire was cut, where is it? Whenever the neutral wire was cut, am I saying that we don't have a written path for A, written path for B, written path for C?
no.
No. Where is the written path for A now? Where is the written path for B? Where is the written path for C?
There is no neutral path, sir.
It is within. Some of the three currents by reaching to this node will be 0, right?
Yes, sir.
Then what? If A is forward, B and C are written. If C is forward, A and B are written.
Okay, in that way we are transferring.
Not transferring, that is adjusting on its own.
Yes, it's adjusting.
Okay,
Sir,
tell me. Imtiaz, have you understood this?
sir, actual ga
In a three-phase system, if it's an ungrounded neutral system, sum of the three currents will be equals to 0.
yes, sir.
Okay, if sum of the three currents is equals to 0, if you are saying IA plus IB plus IC equals to 0, if you say like this, then what I'll say is IB equals to minus IA minus IC.
Yes, sir.
Means if B current is forward, I will feel that A and C will be written.
Yes, sir.
Then if A is forward, B and C will act as written, obviously.
I thought that there must be neutral.
Unless you take two conductors forward, other one will become written.
Okay, sir.
That's your way of analysis. That's it.
Okay. Sir,
As
one
some
more.
of the three currents are 0.
Okay, sir.
Okay.
Sir, one more.
Tell me.
Sir, actually, normal ga delta phase voltage will must equal to delta line voltage, sir.
Winding, for winding.
Yes, sir. In winding. ఒకసారి డ్రా చేస్తారా సార్?
Tell me what you have doubt in that.
అంటే ఒకసారి డెల్టా కనెక్షన్ ఒకసారి డ్రా చేస్తారా?
Okay.
The line voltage.
Line voltage?
Line voltage, for example, line voltage will be 11 kV.
Okay.
It's a delta of the. అంటే ఈ లైన్ టర్మినల్ మస్ట్ బి కనెక్టెడ్ టు ద లైన్ ఆఫ్ ద transmission line.
Between these two, you have 11 kV.
Yes, sir.
Means this winding will experience a voltage of 11 kV.
Yes, sir.
What is this conductor A voltage?
It's a 11, sir.
Why 11? Conductor A voltage means, will you measure with respect to B?
No, with respect to ground must be measured.
If you measure with respect to ground, how much will be?
11/√3.
That's it.
I thought the transmission line will be separated and delta will be separated.
No, delta winding, line to line voltage, phase winding voltage are equal. After crossing the delta, terminal voltage will be 11/√3 only, right?
Okay, sir.
If you have that type of doubt, simply you convert this delta to star and try to understand it. Imtiaz.
Okay.
Okay.
Sir, one more doubt.
Tell me.
Actually, LG fault will occur at the phase A. And the phase B, phase C will be √3 times of the preferred voltage, no, sir. In ungrounded system. In ungrounded.
Okay, okay.
Okay. The relay will be sense the 1.1 times of the full fault current, no, sir. Normally. Relay will sense that current, no, sir. More than the.
A is not carrying any current, you are saying, na?
Yes, sir. B and C, sir. I'm talking about.
B and C are open already. not carrying any current.
సార్ ఇంతవరకు చెప్పింది కదా సార్, అంటే √3 times of the
Voltage was increased by √3 times.
yes sir, sorry, voltage sir.
That does not mean that current is increasing.
అంటే రిలేవల్ సెన్స్ కాదు సార్ ఇప్పుడు, అంటే √3
Current is
times
zero, na? What relay you are keeping? Over current relay.
over voltage.
Over current relay, not over voltage.
Okay sir.
If you keep over voltage relay, it may sense it. That's okay. But now we are discussing about only over current relays.
Okay, if we kept the over voltage relay, at that time we
It may sense, definitely.
Okay sir.
Okay.
Yes sir. Yes, sir.
Tell me any other doubt you have, Imtiaz?
No sir.
That's it. Can I mute you?
Yes sir. Yes sir, thank you sir.
Anil Kumar.
Sir, good evening, sir.
Good evening. Tell me, Anil.
Sir, in 197.
197,
sir.
Okay.
Sir, the next slide, sir.
Hmm.
The point you explained that I did not get, sir.
A is grounded.
The whole, yes, sir.
VI
Ground
equals
by
0.
root, sir.
Then what is VC? C means C to ground, na?
Yes, sir. C to run this also.
Already this is ground.
Sir. Yes, sir.
Ground is nothing but A.
Yes, sir.
You think from C to A now. That will be 11 kV.
Yes, sir. 11 kV.
That's it. Hmm.
Okay, sir. Sir, next slide, sir. That statement you explained that in delta winding there will be a possible of arcing.
Yeah,
The point
because remaining terminal voltages are increased by √3 times, right?
Yes, sir.
In the healthy condition, B and C voltages are 11 by √3, 11 by √3.
Yes, sir.
If you have a fault from A to ground, BC voltages are increased to √3 times of that.
Okay, sir. Okay.
Okay? Anil,
Yes, sir. I got it.
tell me. Have you cleared your doubt?
Yes, sir. I cleared my doubt, sir.
Any other doubt here?
No, sir.
Yeah.
Thank you, sir.
Hello, sir. Sir.
Tell me, Pratyush.
Sir, that unbalanced case, sir, neutral cut case. Sir, magnitude of that unbalanced voltage find చేయడం అంటే ఎలా ఫైండ్ చేస్తాం సార్? ఒక్కొక్క
You have to do network analysis for it. Applying KVL, KCL, these things you have to do.
Sir, అంటే న్యూట్రల్ పొటెన్షియల్ అంటే ఆ న్యూట్రల్ పొటెన్షియల్ అంతా తెలియదు కదా సార్.
Neutral potential we can't find. Okay, we can do it by doing three-phase network analysis. You apply KVL for AB loop, BC loop, CA loop.
Okay, sir.
You find out those currents first.
Okay, sir.
After getting those currents, you attempt to get that neutral voltage.
Okay, sir. Okay, sir.
Try it, Pratyush once. Okay.
Okay, sir. Okay, sir. Thank you.
Mukesh.
Hello, sir.
Tell me, Mukesh.
Sir, you told about straying capacitance, no, sir?
Stray capacitance, huh?
If you use straying capacitance, we can have a zero sequence impedance
Voltage
as
is zero. Yes.
definite value, no, sir. We'll get definite value, no, sir.
Yeah.
So, in LG fault, you told that arcing ground. You told about arcing ground, no, sir. The reason for arcing ground is when you have zero impedance, effective zero impedance value as infinite, we'll have arcing ground, no, sir. If you consider straying capacitance, we don't have that.
Then still that number is very large impedance, right?
Oh, straying capacitance, or your
Stray capacitance impedance is very high. It may be in mega ohms.
Okay.
Then obviously it will act as a virtual open circuit. Compare it to other impedances in your circuit.
Okay, sir. Sir, another note, sir. Another note, sorry to ask you again, sir. I'm
Metal
still confused with that delta connection. When you are saying phase voltage equal to line voltage.
for your winding, for delta
Ah.
winding, phase winding voltage, line to line voltage are equal.
Okay, sir. But
But at
terminal
the
voltage will
terminals
come.
we are considering, at the terminals we are considering, the terminal voltages will be by √3 times of line to line.
Okay, sir. That's all, sir.
Okay.
Yes, sir.
Yeah. Yogashri.
Sir,
Tell me.
sir, I'm general doubt, sir. Sir, previous year, last year, వర్షం పడినప్పుడు ప్లగ్ కి కనెక్ట్ చేసింది సార్ హీటర్. అప్పుడు స్విచ్ వేయక ముందుకే అది వైబ్రేట్ అయ్యి షాక్ వచ్చింది సార్. ఎందుకు అలా వస్తుంది సార్?
Maybe problem with the switch.
స్విచ్ ఆఫ్ లోనే ఉంది కదా సార్.
Yeah, that's what I'm saying. It may be problem with switch. Maybe a over voltage.
ఓవర్ వోల్టేజ్ వస్తే అలా వస్తుందా సార్?
Because of over voltage, you may have a short between phase and neutral.
Okay, sir.
In the switch itself.
Okay, sir.
Okay.
Phase
Or
and
a
neutral-
misconnection may be possible.
ఓకే సార్. స్విచ్ అనేది ఆఫ్ లో ఉన్నప్పుడు ఓపెన్ స్విచ్ అవుతుంది కదా సార్.
That's what I'm saying. Open switch only, but you may have a misconnection in your board. Maybe because of water dropping into the board.
Okay.
That phase neutral may be shorted. That thing might have caused that vibration.
Okay, sir. Okay, sir.
It has happened, as you are saying, it's in rainy condition only, right?
Yes, sir. In rainy condition only.
If you open that switchboard once, check, is it dry or wet?
After one day or 2 days, it is not, again nothing. It is there, sir.
Then it might have dried up.
Right. Okay, sir. If
Okay.
the voltage phase and neutral is short means మళ్ళీ బోర్డ్ చూసి కనెక్ట్ చేయాలేమో సార్.
Yes, we have to reconnect it.
ఓకే సార్.
Main problem is loose connections.
ఓకే. లూజ్ కనెక్షన్స్ ఉన్న వోల్టేజ్ ఎక్కువ ఉన్న మళ్ళీ బోర్డ్ తీసి మళ్ళీ చెక్ చేసి చూడాలి.
Yes.
ఓకే. అలా కాకపోతే వాటర్ వచ్చినట్టు.
Yeah, water might have dropped into the board.
Okay, sir.
That is one major probability of getting that. Because in my home also, we used to get a shock nearby a wall, particularly during rainy season.
Okay, sir.
The reason is due to the water drop into the switchboards.
Okay, sir.
Okay.
Okay, sir.
Yeah. Rayapreddy.
హలో సార్.
Tell me.
సార్ ఒక ఎంటీ పేజ్ తీసుకోండి సార్ ఒకసారి.
What is it?
ఒక ఎంటీ పేజ్ తీసుకోండి.
What do you want? Tell me, please.
సార్ యాక్చువల్ గా ఒక సోర్స్ తీసుకున్నాం సార్ మనం.
You please tell me in English. Many people are
suppose we are taking a source, a single phase AC source.
Single phase AC source you want?
Okay, sir.
Okay.
So connect make a line to AC source and connect it to two resistors.
Single phase AC source you have?
Yes, sir.
Connected to
two resistors
connected in parallel series.
Parallel, sir.
Okay. Tell me.
Suppose they are grounded, sir.
Grounded.
Sir, if it is having a value of 400 ohms and 100 ohms.
Okay.
So make another circuit of same parameters. Assume that 100 ohms is a human body.
Same circuit.
Assume 100 ohms as a human body.
Okay.
So suppose 100 ohms body, 100 ohms is an human body. So is there any chance of affecting of human body for current?
I didn't get you what you're asking exactly.
Sir, suppose manam
Are you seeing the screen?
Yes, sir, seeing the scene.
First circuit is okay with you?
Okay, sir.
You want me to draw second circuit also in the similar way?
Yes, sir. Grounded.
Fine. What I have to do in the second circuit?
400 ohms చేయండి సార్ అక్కడ.
Okay, 400.
Suppose sir, ఇప్పుడు మనం 100 ohms.
Is it required to be grounded?
Yes, sir, grounded. Grounded, sir.
Grounded. Okay, tell me now.
Sir, ఇప్పుడు 100 ohms హ్యూమన్ బాడీ అనుకోండి సార్.
This one.
నా సెకండ్ సర్క్యూట్ సార్.
First one or second circuit, 100 ohms is a human body.
హ్యూమన్ బాడీ సార్.
Okay.
ప్రాక్టికల్ గా ఇప్పుడు మామూలుగా ఫస్ట్
1 minute, wait. Okay.
సార్ ఫస్ట్ సర్క్యూట్ లో చూసుకోండి సార్, ఇప్పుడు 100 ohms లో 400 ohms లో కరెంట్ ఫ్లో అవుతుంది.
Yes, it will flow.
సార్ సెకండ్ సర్క్యూట్ లో చూసుకున్నప్పుడు హ్యూమన్ బాడీ వేస్తున్నప్పుడు ఇక్కడ కూడా కరెంట్ ఫ్లో అయ్యే ఛాన్సెస్ ఉంటాయా సార్?
ఖచ్చితంగా ఫ్లో అవుతుంది. మరి డౌట్ ఏంటి దాంట్లో నీకు?
సార్ ఇదే పాతో ఒకవేళ 400 ohms విడిగా గ్రౌండింగ్ వేసుకున్నాం అనుకోండి సార్.
Okay, 400 ohms you have grounded separately.
Separately, sir.
Okay, you grounded this one separately. Okay.
ఇప్పుడు హెవీ కరెంట్ ఫ్లో అయింది అనుకోండి సార్, ఇది గ్రౌండెడ్ టెర్మినల్ సార్, ఇది హ్యూమన్ బాడీ సార్. మనకన్నా ముందు ఆల్రెడీ గ్రౌండ్ అయింది కదా సార్, మనకు ఫ్లో అవ్వకూడదు కదా. అంటే హ్యూమన్ బాడీ కన్నా ముందు 400 ohms ఆల్రెడీ గ్రౌండ్ అయింది కదా సార్.
Yes.
అప్పుడు ఫ్లో అవ్వకూడదు కదా సార్.
What is the condition for current flow?
మినిమం రెసిస్టెన్స్ ఉండాలి సార్.
Closed path.
Closed path. Okay. Closed path.
Are you finding closed path with human body here?
Yes, sir. Ground అవుతుంది కదా సార్ బాడీ.
Okay, then still you have a closed path here, right?
Yes, sir.
Then it will flow.
సార్ అప్పుడు ఒక లైవ్ కండక్టర్ పెట్టుకున్నప్పుడు మనం గ్రౌండింగ్ ఇచ్చిన వేస్ట్ కదా సార్ 400 ohms కి. కరెంట్ గా డైరెక్ట్ గా బాడీకి వచ్చేస్తుంది కదా సార్ మనకి.
If you touch a phase conductor, definitely you get a shock.
అంటప్పుడు గ్రౌండింగ్ ఇచ్చిన వేస్టే కదా సార్ అంటప్పుడు. 400 ohms కి.
Waste. Yes, sure.
మామూలుగా
then who will ask you to touch phase conductor? Nobody will ask you to touch phase conductor, right?
Yes, sir. Yes, sir. మనం
whatever the grounding they are providing, it is to protect you if you touch the apparatus.
Okay, sir.
Not directly phase conductor, right?
అవును సార్, ఇప్పుడు ఒకవేళ 100 ohms 400 ohms రివర్స్ చేసాం అనుకోండి సార్, మనం లో రెసిస్టెన్స్ పాత్ లో కరెంట్ ఫ్లో అవుతుంది అని చెప్తారు కదా సార్. ఇప్పుడు సపోజ్ అది షార్ట్ సర్క్యూట్ అనుకోండి సార్, అప్పుడు మనకి వరకు రాదా సార్? షార్ట్ సర్క్యూట్ అయితే అక్కడే ఫ్లో అవ్వాలి కదా సార్ కరెంట్.
For example, if this impedance is, let us say, load, this is your load.
Okay, sir.
You consider your load as, let us say, 4000 ohms.
Okay, sir.
And this is your human body. It may not be 100. Practically speaking,
300,
it will be in the range of
300 to 1000 ohms.
500 to 1000.
Yes, sir.
Depends on the body structure. Let's say 500.
Okay, sir.
Now, if this is a single phase AC voltage source and it is supplying some current according to these two. Okay. So, for example, if this source is some 250 volts, let us say.
Okay, sir.
Okay, tell me quickly, what is 4000 in parallel with 500?
4000 in terms of 500, sir.
4000 in parallel with 500.
Lower than a value of 500, sir.
Calculate it and tell me. Over.
Yes, sir. 500 into 4000 by. I don't have books, sir. 5,000. 500 into no, sir. 500 into 4000 by 4500. By
222. Good.
Yes, sir.
222.22 ohms. Tell me, Yogeshri, what is this 250 by 222? Correct? 250 by 222.22. Yeah, tell me, Yogeshri, how much is this current? Is it 200 or 400? I think
Sir, that's
400.
404. 444 sir are required.
R equivalent equals to 444.44.
44.
Okay, fine. Current, you tell me, Imtiaz. Current. 250 by this number.
0.5 sir. 0.5.
0.5. That's it?
Yes sir. Yes, sir.
Exactly, or having some
0.5625 sir.
562 amperes.
Yes sir.
Okay. Manohar, this 0.562 amperes will be divided between these two. Okay. How much current we will get in this 500 ohms means it will be 0.5 amperes. Manohar, are you there?
Oh, no. Okay, sir. None, sir. సార్ సపోజ్ 4000 ohms అనేది షార్ట్ సర్క్యూట్ అయినప్పుడు ఒకవేళ షార్ట్ సర్క్యూట్ చేయండి సార్ దాన్ని అప్పుడు హ్యూమన్ లోకి బాడీలోకి కరెంట్ వచ్చే ఛాన్స్ ఉంటుందా సార్?
Definitely, you will have a chance, but for how much current, beyond how much current we are going to get an effect. That will decide whether you are going to get a shock or severe shock or death.
ఓకే సార్. అంటే మనం ఇప్పుడు సపోజ్ రెసిస్టెన్స్ తీసుకున్నాం అనుకో సార్, ఇది షార్ట్ సర్క్యూట్ అయిన తర్వాత అవతల రెసిస్టెన్స్ ని మనం లెక్కలోకి తీసుకోం కదా సార్, షార్ట్ సర్క్యూట్ అని చెప్పారు సార్.
This resistance, let us say, 20 ohms you take. You take 20 ohms and 500 ohms.
Okay.
Okay, still you carry 0.5 amperes, right?
Yes sir.
And 20 ohms will carry its own current, whatever it is.
Okay.
Then definitely you are going to get a shock if you touch a 250 volt wire.
Okay, sir.
Okay?
Okay, sir.
Tell me your doubt, Manohar, now.
అంటే మనం ప్రాక్టికల్ గా అయితే తగులుతుంది, షాక్ తగులుతుంది, కానీ మనం థియరిటికల్ గా వేసినప్పుడు షార్ట్ సర్క్యూట్ వేసినప్పుడు IF మొత్తం టోటల్ కరెంట్ అనేది ఆ షార్ట్ సర్క్యూట్ లైన్ లో ఫ్లో అవుతుందని చెప్తాం కదా సార్.
Very short circuit for you.
Suppose 20 ohms short circuit చేయండి సార్.
Why? We do have that practically short circuit?
ప్రాక్టికల్లీ షార్ట్ సర్క్యూట్ అంటే ఒక లైన్ డైరెక్ట్ గ్రౌండ్ పోయింది సార్. మన హ్యూమన్ బాడీ కన్నా తక్కువ రెసిస్టెన్స్ ఉందేమో సార్, మినిమం రెసిస్టెన్స్ ఉంది అనుకోండి సార్.
Then still, as you have appeared across exactly 250 volts or 220 volts, definitely you have your own current, right?
Yes sir. Yes sir. Yes.
Then
okay sir.
See, in this view, what you have to understand exactly is, Simon over.
Yes sir.
Even we touch a phase wire in our house.
Yes sir.
Okay.
Okay sir.
Phase wire of your distribution transformer, you will experience same sort of shock.
Okay sir.
Understanding?
Yes sir.
Because
yes,
both the places voltages remain same.
yes. Okay sir, thank you sir.
Yeah. Any other doubt you have, Simon over?
No sir, no sir.
Yeah. Bharati.
Hello, sir.
Tell me.
Sir, I have a general doubt. Like in our power electronics lab, while connecting DSOs and CROs, we use isolated supply, sir.
Okay.
So, how, like, from the transformer, how will they connect the isolated supply and our experiment grounding and neutral? How will that network be, sir? Like you have drawn for our home, no, sir, like that, how it will be?
Isolated supply means, are they creating separate supply instead of taking from distribution company?
I don't know, sir, that.
What do you mean by isolated supply there?
No, in labs we used to connect that, like for DSOs, like we have to separate the our power electronic like laboratory apparatus, that setup, and this CROs and DSOs will connect it in isolated supply. So
It may be with isolation transformer, I think. They will keep one isolation transformer. Okay.
Okay, sir.
From this, they might be connecting the equipment by providing grounding for this neutral.
So the ground will be the ground will be same, sir, for both at this.
This also grounded, you feel.
So you have only separate neutrals, sir.
Separate means actually, if you provide this isolation transformer, this network we feel as an isolated one with respect to the distribution system or distribution transformer.
Okay, sir.
You just inquire about what is that isolated supply exactly, whether they are generating their own voltage for the lab purpose or whether they are taking it from distribution company only by means of isolation transformer.
So if they use this isolated transformer means like grounding will be the
We
same.
have a disconnection between these two electrical circuits, right? By means of direct contact. You don't have direct contact.
Mm-hmm. So rester, this primary that will give it like from the distribution transformer
Primary
and
transformer.
Okay, sir.
And secondary, your lab equipment and all might be connected.
Okay, so if fault happens, it will be safe. Like that.
It may be safe. Yes.
Okay, sir. That's the doubt. Thank you, sir.
Yeah. Fine.
Sir.
Yeah, Imtiaz, tell me.
Sir, and before someone asks about the grounding, no, sir. Everything of the that thick size of the conductor.
Yeah.
అంటే నార్మల్ గా లో వోల్టేజ్ కి మనం అది ఉండవు కదా సార్.
Okay, very low voltage means ratings. Very low rating equipment, you may not have it. Okay.
But you said in this situation, the lightly load phases will be experienced over voltage, no, sir.
Okay, then how we are interrelating these things?
అంటే ఆ ఎక్విప్మెంట్ మొత్తం లో వోల్టేజ్ కే కదా సార్ డిజైన్ చేస్తాం.
Okay, then how you are interrelating these things, sir? Tell me, Imtiaz.
Okay. If a neutral is
all are connected in parallel, whether it is a low rating or high rating, whatever it is, all are connected in parallel, right?
Yes, sir. అంటే న్యూట్రల్ కట్ అయినప్పుడు మాకు అర్థింగ్ యూజ్ అవుతాయి కదా సార్ అప్పుడు.
If you connect your earth and neutral together in your house, then earthing will help you.
కానీ లో వోల్టేజ్ కి అది ఎర్థింగ్ స్విచ్ ఇయర్ కదా సార్.
Then where you got that neutral?
అంటే న్యూట్రల్ కట్ అయినప్పుడు మాకు ఎక్స్ట్రా వోల్టేజ్ వస్తాయి కదా సార్.
Distribution box in your house, sir.
Yes, sir.
DB. Okay. And you are taking phase as well as neutral. You are taking one phase wire and one neutral wire from company.
Yes, sir.
Okay. And you are providing your own earth wire here. Inside your house, you are providing your own earth wire.
Yes, sir.
Earth wire. Okay. And you have the phase wire, as we said, like this. And you have the neutral wire here, something like this. Okay.
Yes, sir.
And what I am saying is, you join this, this earth wire what you have, this is connected to the box, a DB box, metal box, and that is connected to ground inside your house.
Yes, sir.
Okay. And you see, you have two types of loads here. One is a 2-pin load, other one is a 3-pin load. Okay.
Yes, sir.
This phase wire, what you call here, that will be connected to this pin, and that will be connected to this pin.
Yes, sir.
Neutral wire, what you have here, is connected to this pin as well as this pin also.
Yes, sir.
Earth wire, what we have, that is connected to only this big pin.
Yes,
Getting?
sir.
Okay. So this is a load 1 and this is a load 2 here.
Yes, sir.
Now, if you join phase and neutral together, this is a neutral and this is a phase, neutral and earth together like this.
Okay.
If you join these two together like this, and that is grounded.
Yes, sir.
And this neutral, whatever you say here, is coming from distribution company to you.
Yes, sir.
Phase, whatever you say here, again coming from distribution company to you.
Yes, sir.
Now, unfortunately, that neutral wire was disconnected. Where? In the supply. In the coming supply, it was disconnected. This is your distribution transformer. Okay.
Okay, sir.
From this distribution transformer, you are getting this phase wire and you are getting this neutral wire. And that neutral wire is already grounded in the location of the distribution transformer.
Yes, sir.
Now, in the coming supply, if this neutral wire was cut,
Yes, sir.
tell me, do you have a closed path for this L2 load?
Yes, sir. Is there through earthing?
Just check this. Current is coming through the phase wire like this.
Yes, sir.
Going out in this neutral. Look here,
But
look
it's
here.
open path.
Look here. Going through this neutral.
Yes,
This is
sir.
a phase. Equipment is connected and going through the neutral. Yes, I need your answer.
Yes, sir. Yes, sir.
Flowing to neutral and come to this point, neutral point. And it will try to go like this. But this is open here.
Yes, sir.
It won't flow in this. Okay. So that current may go into the ground here.
Yes, sir.
And that ground and this is grounded.
Yes, sir.
And that will jump in this manner and it will go into the transformer.
Okay.
Because your phase current is coming from transformer, right?
Yes, sir.
Phase current is coming from transformer, going like this. Going in this manner. Going into this pin.
Yes, sir.
Returning back to neutral, coming like this. Grounded. And this is ground. Going into transformer. Circuit was
Okay.
closed.
Yes, sir.
Whereas if you think about L1 load now, L1 load. This is the point where you have doubt, right?
Yes, sir.
Okay. So phase wire is carrying current. Coming like this in the phase wire. Reach it to this point. And I'm going in this load now. Phase current is flowing like this. Reached here.
Okay.
Entered into equipment.
Yes, sir.
Come back to neutral.
Okay.
And it's coming through neutral like this. And it's grounded. Going into ground. Again ground. Entered into transformer.
Okay, sir.
That's it. It was closed, right?
Due to lack of concept of the earthing and neutral at short circuit, sir. That's
Okay.
all. Okay, sir.
That's it.
Sir, thank you so much, sir.
Yeah.
Sir.
So anybody have doubts? So please raise your hands.
Yes, sir.
Move in. Tell me.
Sir, while calculating short circuit MVA, we take pre-fault voltage, na, sir. It means the point at which we are getting fault at that location only we have to take, na, sir.
Yes, yes.
Okay, sir. And in calculating circuit breaker rating, we are taking phase voltage, na, sir. It means in
That's
that
a general rating only, right?
in that whole system, what is the line to line given? From that we have to take phase.
Wherever you are keeping breaker, at that location, what is the rated voltage?
At that location, sir.
Wherever you are keeping, where you are keeping breaker.
Sir, please take any alternator circuit breaker transformer like that. And
Oh, see, you are designing your breaker rating at certain place, right?
yes.
Wherever you are keeping breaker, what is the rated voltage at that location?
Okay.
That voltage you should consider.
Okay. At that point only. Okay. While calculating short circuit MVA, we have to take pre-fault. While
Pre-fault voltage also at the fault location.
fault location.
If it is absolute value, how much is the absolute value of pre-fault voltage you have to take?
Okay.
If it's a per unit, you can go with per unit formula.
Sir, can you please take any system like 11 kV, 12 kV? Sir, I'm thinking that both will be same, sir. That's why I'm getting doubt.
What both will be same?
Pre-fault voltage means before fault, if we assume the circuit to be open, then the whatever the phase voltage is there.
Yeah, it may be equal, may not be equal.
Sir, in what case it will not be equal?
If it's a loaded system.
If it is a loaded system, then
it is not sure that your operating voltage and rated voltage is equal. Operating voltage may be more than rated voltage or maybe less than rated voltage.
Operating voltage will change.
Operating voltage is pre-fault voltage, right?
Okay. Yes, yes. But phase voltage will be as the
Not phase, not rated voltage will be as it is.
As it is. Okay. Done, sir. Sir, in first assumption of fault analysis, we have taken alternator with EG double dash, sir, and XP double dash. Sir, today we have discussed about that steady load, single phase load, and the two remained open.
Yes, yes.
That also we have to take EG only, sir, not EG double dash.
EG only we have to take, not EG double dash.
Sir, how
EG will be remain same, right?
Which EG,
that will be the rated voltage only. No load EMF only you have to take.
Sir,
because before keeping that load, you don't have any current flow in your circuit.
Before that, yeah, no currents. Yes, sir.
And it will be remain same.
Remains, yes, but I have doubt in how to differentiate between EG double dash, EG dash, and EG in the question. Not theoretically, we have discussed everything that before between 1 to 2 cycles, it's EG.
If he is asking fault analysis, we have to take EG double dash.
Okay.
Interestedly, sometimes they may ask you what is sustained current.
At that
sustained current. In that case, we have to calculate the value of EG with XD in the pre-fault condition.
Okay.
Okay. Then fault you have to take with the same value of EG and XD, and you have to find out the sustained fault.
Okay. Sir, we have to. Okay, I'm cleared, sir. That. Sir, and we have discussed about flashover also. Sir, how it is different from puncture, sir? I have heard these words many times.
What do you mean by puncture?
Generally, it's. I don't know exactly, sir. That's why I'm asking.
No, just you say tube puncture, right?
Yes.
Tire puncture.
Yes, sir.
What is that puncture? Brake.
What is
broken?
That? Yes.
Broken, we can say puncture means broken.
Yes, sir.
So if the insulators are broken, it is a puncture.
Then
mechanical breakdown.
It will okay. Then flashover means electrical.
Without mechanical breakdown, there is an electrical breakdown. Flashover.
In both the cases, there will be become useless, no, sir.
No, in the electrical breakdown case, insulators will be useful further also.
Okay. Only we have to change
electric strength may be little deteriorated, but still we can continue with the same insulators further.
Okay. So, okay, sir. Sir, in that only, sir, that if we replace, if flashover occurs, then if that middle rod we call as pin or something, sir. If we replace that, then they'll be useful only, no?
Pin.
PIN, pin insulators.
Pin. Okay. Pin insulators.
That pin, if we replace, I mean, you're telling that only the problem, sir, during flashover. Insulator will remain safe.
See, actually, arc will be formed only in the gaseous medium.
Yes.
Arc, flashover, whatever it is, it will be formed only in the gaseous medium. So whenever you have a over voltage on the conductor, arc will start from conductor.
Yes.
But if the insulators are broken, we have some air gap, right?
Yes, air gap.
In that air gap, it will pass.
Yes.
That's a puncture or mechanical breakdown.
Okay.
If that over voltage is not up to the mark of making the puncture,
then it will flash over.
It will jump to the pin.
Yes.
It won't pass through insulator.
Now got it, sir.
It will jump to the pin and then touches to the tower.
Yes.
That's a flashover, or you can say electrical breakdown.
Okay. Thank you. Clear very much, sir. Sir, one
Yeah.
more. Sir, while discussing about that switching angle, we have said that if a system has a voltage V equal to Vm sin omega t, then we get that fault at alpha angle. Sir, if Vm is at 90 degrees and we got fault at that point, then alpha is equal to 90 degrees. We can take like that. Sir. He's mentioned in the
alpha, it's completely in your control.
alpha is in our.
In our control means for mathematical analysis sake, that is in your control.
No, sir, I am just to analyze alpha. I'm thinking in this way. Am I correct or wrong? Please tell. We have a sinusoidal waveform Vm sin omega t, which is sinusoidal only at omega t equal to 90 degrees. We are closed that switch or we got fault.
Okay.
Then alpha equal to what? I have doubt in this in my mind since long.
Alpha will be 0.
We have to take alpha 0 now, sir.
You already said omega t equals 90.
Yes. If omega t is not mentioned, then we should assume something like that.
Something, Mubin, you tell me at what time we have the fault. Is it a time t equals 0 or not equals 0?
Sir, with respect to voltage, I am telling at t omega t equal to 90 means t equal
omega
to
t equals 90 means you have some time, maybe 5 milliseconds.
5 milliseconds, yes.
Okay. You have fault at 5 milliseconds. That's it. Matter is over. Why you are thinking about alpha now?
He will ask now, sir, switching. Then we have
We
to
don't
take...
ask switching angle in the problem.
Okay, sir. Okay.
What he will ask is, what is the switching angle to get the maximum positive DC component? What is the switching angle to get the maximum negative DC component? Okay. Provided that they will give at what time the fault is.
Okay.
Fault occurred at time t equals 0 plus, or fault occurred at time t equals to 5 milliseconds. Like that they will give in the problem.
We have to take that in our voltage equation and solve us.
And solve it. Yes.
Sir, if the pre-fault voltages are balanced and if pre-fault voltages are unbalanced, you have said some statements while some
The pre-fault voltages are balanced. You have only pre-fault positive sequence voltage.
Yes.
You don't have any pre-fault negative and zero sequence voltages.
Yes.
If the pre-fault voltages are unbalanced, you have all the three.
All the three.
In your sequence networks.
Yes. That's it.
Yeah.
Okay. Sir, and one problem, sir. Sir, while discussing about this alternator momentary current, maximum DC current, we have explained with respect to IF double dash, na, sir. Why so, sir? I mean, momentary current means 1.6 times of IF double dash. In transformer, we have taken 1.6 times of I symmetrical and √2 times of
IF double dash and I symmetrical both are same.
IF
double dash and I symmetrical both are same.
Sir, IF double dash means during subtransient period we have
that's the initial symmetrical current, right?
How can we say that initial symmetrical current?
Initial means what?
Subtransient only.
That's it.
But at that time we have DC and AC, na, sir. That's I'm thinking.
Yeah, we are writing only AC component here. That's why we are called symmetrical, right?
Okay.
To account the DC only, we are multiplying 1.6.
That you have explained while transformer, sir. But here IF
same thing we have to adapt here also.
Same thing. In transformer, everything is clear, sir. While coming to alternator, that notations change, sir.
Same equations you have to extend here also. Same multiplication factors and all. Multiplication factors particularly.
IF double dash, which we solve from the sequence circuits, that is the initial symmetrical RMS current.
Or you say subtransient RMS current. AC component of subtransient RMS.
Okay, done, sir. Sir, and one more, sir. We have solved a problem, an alternator on no load, alternator resistance and reactance given. We have solved in per unit, sir. But I am solving in actual, it's not getting, sir. It means values are different. Sir, the statement is You got 31.85 kiloamperes. I'm getting 50 like, sir.
Why? Why the difference is coming?
Can you please give a hint? I'll solve. The RA is 0.1 per unit. XT double dash is 0.25 per unit.
Okay.
And the alternator ratings are 11 kV, 150 MVA.
Okay.
And operating at 12 kV.
Okay, 12 kV.
Alternator, no load, and short circuit, 3-phase short circuit occurred, sir. So I am taking 12 kV now, sir. 12 kV by first converting RA into R actual and XT double dash into X actual by taking Z base equal to V line to line base square by S base.
What is that V line to line base?
11 kV whole square by 150 MVA.
Okay. You will get the impedance in absolute form. Okay.
Absolute form. Then 12 kV is operating voltage, na, sir. 12 by that actual value, actual base. I'm sorry, actual impedance. I'm dividing the value.
What circuit you have drawn there?
Same, sir. Generator and RA of generator, XL of XT.
That's okay. I also know it means what circuit you have drawn. Per phase.
Per phase only, sir. Yes.
What is 12 kV?
12 kV is the operating voltage, sir.
What is that?
At that point, the operating voltage.
That's okay. What is that? 12 kV. What is that? Is it line to line or phase?
Line to line. Okay.
Then what voltage you have to take there?
12 by root 3.
Do it.
Done.
Okay.
Done. Sir, one more, sir. Sir, these while calculating these fault, motor will supply fault current, na, sir. While calculating those things, we should take pre-fault voltage across the motor and then calculate, sir.
Why? Wherever you have a fault, that location voltage only you have to consider.
Sir, we have 4 motors. That question is there, na, sir. How we calculated the motor current, sir? And
what is pre-fault voltage for you?
At that point, pre-fault voltage is here. 11 by
not given. We assumed as
given 11 by root 3. Pre-fault voltage is 11 by root 3.
Assumed as 11 by root
3. System is given as 11 kV, sir. Alternator connected to 4 motors. Okay. So pre-fault voltage will be 11 by root 3 only.
Okay.
Then
that 11 by root 3 will be taken as internal EMF of all machines.
So we have to calculate separately. Like I mean, how to calculate that current? I'm not clear, sir. And you have taken in the PDF. I've just now checked it, sir. In that you have given like this.
What's the doubt you have in that? Exactly, you tell me.
Sir, I want to know how you calculated that IM from motor, sir.
Voltage will be 0 at the motor bus, right? After having the fault.
0, sir. Okay.
Then motor 1 will supply its voltage by its impedance current.
Yes. Okay. Now got some idea. And similar to EG also similar, na, sir? Then
similar. Yeah.
Okay. Sir, just one last, sir, in that only. Sir, EG will EG. I want to calculate the current supplied by generator, sir.
Okay.
So I have to take IG equal to
EG minus 0 by that ZG plus ZM.
ZG plus ZM. Okay.
ZL.
I didn't take that ZM, sir, while solving that.
ZL line.
ZG plus ZL, sir.
L line. There is one line, right?
Yes, sir. Transmission line is there.
That line impedance you have to consider.
Okay, sir. Okay.
That's it?
Yeah, I'll solve it. Thank you, sir.
Okay. Bharati, do you have any doubt, Bharati?
Yes, sir. Like regarding flashover, in rainy seasons, we'll see in street transformers, it will have corona discharge, no, sir? The hissing sound and sparks.
It's not corona discharge. It may be due to some leakage. Yes, sorry, loose connection.
Like mainly in rainy seasons, I see that, sir.
Because the direct push strength of air is very less, right? At the time.
So what is corona discharge and what is flashover, sir? Like what is the difference between?
Corona discharge means due to over voltage on the conductor surface, electric field intensity becomes larger. That will cause for the ionization of the surrounding dielectric medium.
Okay, sir.
That's the corona discharge.
Okay, sir.
Okay. Flashover means because of over voltage, that complete air is going to be breakdown.
So if corona discharge is high, means
Then there is a
can it cause
flashover between the conductors.
Okay, sir. Okay, sir. That is it. Thank you, sir.
That's it. Yeah.
Yes, sir.
So does anybody have doubts? So I think I can leave. Murali Krishna.
Hello.
Tell me, Murali Krishna.
Sir, good evening, sir. Ravi, sir.
Tell me.
Sir, ఒక 4 డౌట్లు ఉన్నాయి నాకు. సార్ ఫస్ట్ ఆఫ్ ఆల్ మీ ఓపిక చాలా బాగుంది సార్, మాకు చాలా ఉపయోగకరంగా ఉంది. ఇదివరకు మాకు బ్యాచ్ స్టార్ట్ అయ్యి 3 months అయింది, కానీ ఇదివరకు ఇంత టైం వరకు మాకు ఎప్పుడు క్లాసులు కానీ డౌట్ డిస్కషన్ కానీ జరగలేదు.
ఓకే ఓకే.
మీ టైంలో జరిగింది, దానికి అప్రిషియేషన్ సార్. సార్ డౌట్ ఏంటంటే మీది అది లైన్ టు లైన్ ఫాల్ట్ అప్పుడు ఫేస్ వోల్టేజ్ కెనాట్ బి డిటర్మిన్ ఆల్వేస్ అని చెప్పి అది ఫాల్స్ అని ఇచ్చారు కదా సార్. ఓకే, ట్రూ అయితే అంటే అప్పుడు ఆల్వేస్ అనేది తీసేస్తే ట్రూ అవుతుందా?
కాన్ బి డిటర్మైన్డ్ అన్నప్పుడు మనకు ఖచ్చితంగా కండిషన్ చెప్పాలి.
సార్
ఇట్ కాన్ బి డిటర్మైన్డ్ అంటే మనకు 2 ways ఉన్నాయి. కెన్ బి డిటర్మైన్డ్ ఒక కేసు ఉంది, కాన్ బి డిటర్మైన్డ్ అనేది ఒక కేసు ఉంది.
ఓకే.
సో వాళ్ళు ఆల్వేస్ అని లేదంటే కండిషన్ చెప్పకపోతే ఇట్స్ నాట్ కరెక్ట్ వన్. ఓకే, సో ఆల్వేస్ అని ఖచ్చితంగా చెప్పాలి వాళ్ళు. లేదంటే దే షుడ్ టెల్ న్యూట్రల్ ఈజ్ గ్రౌండెడ్ అనో న్యూట్రల్ అన్గ్రౌండెడ్ అనో ఏదో ఒకటి చెప్పాలి.
అదే సార్, ఇప్పుడు ఆ స్టేట్మెంట్ ట్రూ అనేది ఎప్పుడు అవుతుంది సార్?
ట్రూ ట్రూ మీన్స్ phase voltages during double line fault.
Okay.
Phase voltages can
sir.
be determined only if neutral is grounded.
Okay sir.
Then it's correct.
Okay sir. Okay sir.
Phase voltages can't be determined only if the neutral is ungrounded.
Sir.
That's also correct.
Okay sir. అదే న్యూట్రల్ గ్రౌండింగ్ అంటే అప్పుడు ట్రూ అన్నట్టు.
True. Yes.
మిగతా ఏ టైంలో ఫాల్సే.
False. Neutral ungrounded means it's a false.
ఓకే సార్. సార్ ఇంకొకటి, ఈ WLG గ్రౌండ్ ఫాల్ట్ లో మీరు అది సర్క్యూట్ బ్రేకర్ మేకింగ్ కెపాసిటీ వచ్చింది కదా టాపిక్.
Yes, yes.
మరి అదే టాపిక్ ఇక్కడ లైన్ గ్రౌండ్ ఫాల్ట్ అప్పుడు రాలేదా సార్? రాదా సార్?
Yes, we have discussed in line to ground fault also.
అంటే అవునా సార్? లేదు సార్, నేను మధ్యలో వినలేదు. అంటే ఐ మీన్ అదే ఉందా లేదా అడుగుతున్నా.
Murali Krishna.
సార్,
based on what fault you want to design the breaker? Is it LG fault, LL fault, LLG or triple L? We don't know right now.
Okay sir.
So we should study all the 4.
Okay sir. Okay.
And for a particular location of short circuit fault, we should calculate all the 4. Then whichever is coming high, based on that you design your breaker and keep it there, so that your system will be safe for any interruption.
ఓకే ఓకే. అంటే ఇప్పుడు ఐ మీన్ లైన్ టు లైన్ ఫాల్ట్ అప్పుడు ఎక్కువ
No, we can't say. అది మనం చెప్పలేం కదా.
సార్.
But we should be ready with the calculation, right?
Okay sir. Okay.
For that purpose we discussed it. Maybe in the examination they will ask you select the circuit breaker rating based on double line fault and
Okay,
what
sir.
is the rating of what is the symmetrical breaking capacity of breaker. If that
Okay,
type of
sir.
question comes, we should do it definitely on LL fault only.
ఓకే సార్. ఓకే సార్.
They may ask based on the LG fault also. We don't
ఓకే
know.
సార్. ఓకే ఓకే.
Okay.
ఓకే సార్. సార్ ఇంకొకటి, ఒకటి సాకెట్ గీసి సింగిల్ ఫేస్ సప్లై గీసి అది మామూలుగా న్యూట్రల్ ఫెయిల్ అయితే గ్రౌండ్ ద్వారా మనకు కంటిన్యూటీ ఉంటుంది అన్నట్టు చెప్తున్నారు కదా సార్.
Yes, yes.
ఇప్పుడు యాక్చువల్ నేను అడిగేది సిల్లిగానే అనుకుంటున్నా. అయితే విషయం ఏంటంటే ఇప్పుడు సింగిల్ ఫేస్ లాగా అట్లా 3 phase ఒకవేళ ఇన్ కేసు ఏమైనా న్యూట్రల్ ఫెయిల్ అయితే ప్రాబ్లం ఏమవుతుంది సార్?
we don't have any problem if neutral was cut.
ఒకవేళ త్రీ ఫేస్
But
Sir.
your voltages will be raised, and there also it will act. This will take care of the things.
ఓకే సార్ అదే
To
న్యూట్రల్ అక్కడ
connect your neutral wire with the earth pin,
ఓకే సార్
not earth pin, inside your home.
సార్
Inside your home, you should not connect it.
ఓకే సార్
Outside means DB box, you have a distribution box.
సార్ సార్
In that distribution box, you can join the neutral wire, main neutral, common neutral wire, and earth wire together.
నేను అడిగేది ఏంటంటే సార్ ఇప్పుడు మన మామూలుగా హౌస్ హోల్డ్ పర్పస్ సింగిల్ ఫేసే కదా ఇన్ కేస్ త్రీ ఫేస్ సప్లై ఒకవేళ ఇన్ కేస్ యూజ్ చేస్తే ఆ కేసులో మన న్యూట్రల్ ఫెయిల్ అయింది.
ఎక్కడ ఫెయిల్ అయింది న్యూట్రల్?
ఇప్పుడు మామూలుగా
లైన్ ఇన్సైడ్ హౌస్
బోత్ కేసెస్ అనుకోండి సార్.
అవుట్కమింగ్ లైన్ అనుకోండి. ఇన్సైడ్ హౌస్ మనకు అసలు పాసిబిలిటీ ఉండదు, ఎందుకంటే మనం వాడేది కాపర్ కేబుల్ కాబట్టి ప్రాబ్లమే ఉండదు ఎక్కడ కూడా.
సార్
ఓకే, దెన్ ఆల్సో ఇట్ విల్ వర్క్ సేమ్ నా మురళీకృష్ణ.
సార్
అదర్ దాన్ దిస్ ఫేజ్ యూ డ్రా వన్ మోర్ ఫేజ్ వైర్
సార్
బ్లూ అండ్ వన్ మోర్ ఫేజ్ వైర్ yellow.
సార్
దట్స్ ఇట్, కామన్ న్యూట్రల్ వైర్ నా.
ఓకే సార్
న్యూట్రల్ విల్ బి కామన్ ఫర్ ఆల్, రైట్? ఆల్ ఫేజెస్.
అదే సార్ సింగిల్ ఫేస్ అయినా త్రీ ఫేస్ అయినా
it will work in the similar way.
ఓకే సార్.
Circuit will be closed.
సరే లాస్ట్ డౌట్ సార్. సార్ అది అదే ఐ థింక్ ఇది సెకండ్ క్లాస్ అనుకుంటా, అదే మన పాజిటివ్ సీక్వెన్స్ నెగిటివ్ సీక్వెన్స్ వోల్టేజ్ ఫేజర్ డయాగ్రామ్ గీసినారు కదా సార్. అది కొంచెము అంటే ఐ మీన్ కొంచెం ఏమన్నా అదే నాకు నేను అర్థం చేసుకోలేదు, లేకపోతే ఏమన్నా అదే నోట్స్ ఏమన్నా అదే మీరు చెప్పడం ఏమైనా కన్ఫ్యూజ్ అయిందని అర్థం కావట్లేదు. ఒకసారి ఏమైనా పాసిబుల్ అయితే అది ఏమన్నా అదే
you have phase voltages, right? VA1, VA2, sorry, VA1, VB1, VC1.
Okay sir.
So these are the three phase voltages you have. VA1.
Okay sir.
And it is VB1.
Okay.
Look at your notes if it's possible. Okay.
Okay sir.
It is VC1.
Okay sir.
Now we have to calculate VAB1, right?
Yes sir.
It is VA1 minus VB1.
Sir.
So you take minus VB1 like this. Okay, it is minus VB1.
Okay sir.
Now you add VA1 and minus VB1 together, that is VAB1, right?
Yes sir.
So if you do that addition like this, if you do,
sir.
and finally you will get that VAB1 something like this.
Yes sir.
Okay.
Okay sir.
And this overall angle is 120 degrees. This one between A1 and C1 angle is 120.
Okay sir.
And this angle will be half of that 120.
Yes sir, 60 degrees sir.
And what is this angle?
30 degrees sir.
30 means what you can say now, VAB1 leads VA1 by 30 degrees.
Okay
That's
sir.
it. Okay, and what he said is VAB1 value x at an angle theta1 is it in per unit form.
Okay sir.
And in per unit form, magnitude of line to line voltage, phase voltage will be same.
Okay sir.
So it will be x only, but angle will come theta1 minus 30 degree in per unit.
Okay sir.
And x value in case of line to line is on line to line voltage base. X value in case of phase is on a phase voltage base.
Okay sir. Okay.
That's it.
Sir sir. Sir.
Similarly, you do for negative sequence also.
Sir.
You take minus VB2.
Yes sir.
Add minus VB2 to VA1, you will get VAB2.
Okay sir.
That will come 30 degree lag.
Okay sir. Okay sir.
Understood, Murali Krishna?
Yes sir. No, understood sir.
Now, just by closing your notes, you try to draw these networks once again.
Okay sir. Okay sir.
Then it will give a clarity to you. Okay?
Okay sir. Okay sir.
Yeah.
సార్ ఇంకొకటి సార్ అదే సార్ అది అదే మాకు రివిజన్ చేసుకునేకి కొంచెం అదే షార్ట్ నోట్స్ టైప్ అరేంజ్ చేస్తామంటారు కదా సార్.
If possible,
బాగుంటుంది సార్.
I will give, but it will take some time. Okay.
Okay sir. No problem sir.
Yeah.
Okay sir. Thank you very much sir.
Yeah.
Good night.
Bye.
Bye sir.
Yeah. So anybody have doubts? So I think we can close the session. Many of you have left already. Thank you.